types of such phenomena. Some of them are those that allow you to say, to define an arrow of time, but they usually create so much entropy that it's impossible to observe the reverse. And then there are those that don't allow you to define forward and backward, like an harmonic oscillator, and then they can happen in both orders. But in the microscopic world, the situation is a little bit more subtle, because you can have phenomena that, even though there is, for instance, a production of entropy, and so you can tell, well, I'm observing the forward process or I'm observing the time reversal process, nevertheless, they can actually occur both. So I will now, with this talk, tell you a little bit more about this option and about possibility of quantum superposing these two. So what I will be focusing on is the thermodynamic definition of the arrow of time. So in thermodynamics, we define the arrow of time according to the second law. So the second law tells us that the total entropy of the universe can only either increase or remain constant. So I will be focusing on processes where we can observe either an increase in entropy or a decrease in entropy and try to build quantum superposition of the two. So the question I will be asking is, suppose that in nature, we have some physical phenomena where we can actually have such superpositions. Could it be that when we try to observe those phenomena, when we try to, I don't know, evaluate the entropy of such processes, we actually end up projecting these processes in either the forward or the time reversal, and therefore we end up not observing quantum superposition of forward and backward. And what would a signature of such superposition be? So this was basically to tell you a little bit about the motivation that was behind the study that we pursued. And now I will enter in the main part of the talk. So I will start with providing you some background information on fluctuation theorems. This is a state-of-art concept in quantum thermodynamics, but I just want to remind you about it so that you can then easily follow what we have built upon that. And then I will present you two of the results that we have in our paper. So basically, these two that I was just introducing before, the effective projection onto a definite times arrow and the signature of the existence of these superpositions. And then I will just conclude and give some outlook. So let me start with fluctuation theorems. So when I started this talk, I was showing you these movies, right? I was showing you either the harmonic oscillator or the drop in the ocean. Now, let me start again from that example, but let me formalize it a little bit better. So suppose that we have a physical phenomenon in front of us, and I record it with a camera. And then I flip a coin, and depending on the outcome of the coin, I decide either I show you the movie in the forward direction or I show you the time reversal of the movie, okay? And I ask you to guess which of the two I'm showing you. Am I showing you the forward or am I showing you the rewind of the movie? Suppose also that I give you the full information of the Hamiltonian of the system, the free energy of the system, and so on. So what's the best strategy for you to guess correctly? If the system is a macroscopic system, then as I was saying before, the only thing you have to do is to use the second law of thermodynamics. So in particular, what you will do is that you will look at the average work performed on the system by the external driving mechanism and at the difference in free energy before and after my thermodynamic quench. And then you will look at the sign of this. If the sign is positive, you will be able to tell me, you're showing me the movie in the right direction. If it's negative, you will tell me you're showing me the rewind of the movie. And this would be correct. You would be always guessing correctly with this strategy. Now, let's suppose instead that instead of recording a macroscopic phenomena, I'm recording a microscopic one. Now, in the case of a microscopic system, you cannot just use the second law of thermodynamics as you would have done for the macroscopic one, but actually you should also take into account the existence of these fluctuation theorems and the Bayesian probabilistic reasoning. Indeed, fluctuation theorems tell us that in a single shot of the movie, so just one round of this quench, I record and I show you, in this single shot, the probability that the work W is invested in the forward the evolution, over the probability that the work minus W is invested in the backward of this evolution is as an exponential dependence on beta, which is the inverse temperature, and the dissipative work, WDIS, where the dissipative work is just the quantity I was showing you before. So the work minus difference in free energy, okay? So this is one of the main formulations of fluctuation theorems. What does it tell us? What does this formula tell us? It says that basically total entropy decreasing events vanish exponentially in the forward evolution, the bigger the entropy variation. Where by entropy, I am referring to this beta WDIS that was presented in the previous slide. Instead, in the backward evolution, we will have that total entropy increasing events are those that vanish exponentially with increasing the size of the entropy variation. So maybe because this sounds very abstract, let me make you a sort of concrete example. So let's consider a gas inside the chamber, okay? And let's suppose that there is a piston in the middle of this chamber so that my gas is, as you see here, confined in 1/2 of the vessel. And then suppose that for instance, I call my forward quench when the piston goes from the middle to the outside, okay? Now, if, for instance, I pull the piston very fast, what will happen is that I pull it outside very fast, the gas is still actually in 1/2 of the chamber, but then it will equilibrate and it will occupy the whole chamber. If I was showing you the time reversal of the movie, if I was recording this movie and I was showing you the time reversal, you would very easily be able to tell, well, this cannot happen. I mean, it's very unlikely to happen because you will have that in the movie, you would observe this spontaneously. The gas from occupying the full chamber, it will spontaneously start to occupy just 1/2 of the chamber, and then you would observe the piston to move to the 1/2 of the vessel. Vice versa, if instead, so in the previous slide, the forward would be the most probable quench. Instead, you could have also situations in which instead of pulling out, I'm pushing in. So you would have that the most probable quench, because I was calling forward whenever the piston moves from the center to the border, you will have that the forward quench is border to center. But this time I am pushing. So it is the most likely to happen, the backward one. And so you will have that the backward one, well, you will observe in the backward one something that is very likely to happen. I'm pushing, and the particles of the gas, due to the inelastic collision with the piston, will be moved. And instead, the forward one will be very unlikely. So these are two examples of situations in which you will have that here in the backward evolution is very likely, and indeed the forward evolution becomes unlikely because you have that entropy increasing events are unlikely in the backward evolution, and in the previous one the opposite. So in these two situations, you had that either the forward evolution was very clear to happen or the time reversal. If instead we reduce the number of particles in our chamber, you will have that, well, the other one, say, for instance, if I do the backward, the movie in the opposite direction, so in the forward direction, will become less unlikely. And so this is basically what the fluctuation theorems tell us. You see that this step-up-step function is the one that describes the case of a macroscopic system. So in the case of a macroscopic system, the likelihood of the, say, forward process to occur is a step function. It's either 0, and then it sharply becomes 1 when the entropy becomes positive. Instead, in the case of microscopic system, we have these fluctuation theorems. So it's this curve over here with this formula here. So you have, as you can see from this blurred area, there is a discrepancy between microscopic and macroscopic. And you have that in the microscopic case, there are situations in which both forward and time reversal quenches are just as likely to occur. So as I was saying before, just a remark I have to make before closing this topic of fluctuation theorems is that all these considerations only make sense when I'm not looking at phenomena that are the equivalent of the harmonic oscillator as before. So I cannot have situations, if I have situations where the total entropy variation is just always 0 in every single run, so totally time symmetric events, then all these considerations don't apply. So the situations that I will be looking at are situations where I have a time asymmetry, and thanks to this time asymmetry, I'm able to say, oh, this time I had some positive entropy variations, and this time I had some negative entropy variation. So for the scopes of what will follow, I will be also using some time asymmetric thermodynamic quenches. And in order to create time asymmetric quenches, there are many techniques. The one that we decided to use is to start from equilibrium states. So we will always start from equilibrium states. We will then perform a quench with a certain unitary U. This quench will bring my state from equilibrium to out of equilibrium, where out of equilibrium is simply a system where there are some fluxes inside that I'm transferring among the particles. If I was stopping here and I was just trying to go back, this would be perfectly reversible because I just performed the unitary, so there was no entropy change. But then I will plug my system to the external environment. And so there will be an exchange of heat. Because of this, there will be an entropy change. And so the quench will be all in all time asymmetric. The reason why I am separating these two, so I am performing a unitary in which my system is unconnected to the outside environment, and then I'm plugging it to the outside environment, is that I want to separate the work invested and the heat. If I was just doing both together, if I was doing the unitary in the bath, it would be very difficult to understand what is the work and what is the heat. So I will separate these two. I will perform first the quench to the system isolated from the environment, and then I will connect it to the environment. Then, so these first and last states will be equilibrium states. In the time reversal quench, vice versa, I will start from an equilibrium state that was the end state of the forward quench. And then I will apply another quench, a time reversal quench, and then I will let it thermalize to the environment and reach the initial state of the forward quench. So with this in place, we are able to move to the actual topic of the results I wanted to present you. So just to wrap up on the fluctuation theorems, basically, if I was showing you this movie in the microscopic case, and I ask you to guess whether I'm showing you the movie in the forward or in the time reversal direction, the best strategy from you would be to, whenever you observe a dissipative work times beta, which is about 1, you say, I don't know, I cannot tell you whether it's forward or backward. The time arrow cannot be inferred. And instead, when you observe a very large or a very large but with negative sign entropy variation, then you will be able to say you showed me the move in the forward or in the backward direction. So with this in place, we are able now to move to the actual results I wanted to show you. And so let me quickly define the framework for what comes next. So I will now use always a thermodynamic system S. This thermodynamic system will be embedded in an environment E. This environment could include the thermal reservoir, but also other degrees of freedom that get entangled with the system. And then I will consider an auxiliary system A. So what will I do with this joint system? I will start creating a quantum superposition between the start state of my forward quench and the start state of my backward quench. So let's say, for instance, that whenever my auxiliary system is in the state 0, I will have the start state of my forward quench, and whenever it's in 1, I will have the start state of my backward quench. What are these C0 and C0 tilde? So this is the form of these two states. Here, EK0 and EK tau are the eigenvalues of the Hamiltonian at times 0 and tau. Beta, as I was saying before, is the inverse temperature. EK0 and EK tau with the cats are the eigenvectors of the Hamiltonian of the system. epsilon k0, epsilon k tau will be the eigenstates of the environment, which can always be chosen as a set of orthogonal states. And then zeta0 and zeta tau will be the partition function of the system at times 0 and tau. And finally, this theta is an anti-unitary time reversal operator, which basically flips the sign of observables without parity. So as you can see here, I was telling you, right, that at the beginning and at the end, I always need to have thermal states. So you can see indeed that from these two states, whenever I trace out my environment, my system is left in Gibbs states, which are indeed thermal states. So this respects the requirement I was posing before. So let's go back now to this initial state. So I have this quantum superposition of initial state of forward and initial state of backward controlled by this auxiliary system. Now, I perform my unitaries, as I was saying. So whenever the state of the auxiliary system is 0, I will perform a unitary operation on the system and just nothing to environment and auxiliary system. This is this case that I was telling, this fact that we keep the system isolated from the rest and we perform a unitary only on the system. In the same way, whenever I will have that the auxiliary system is 1, I will perform my time reversal unitary to the system and nothing, just identity to the environment and auxiliary system. Now, so as I was telling you, the important thing here is to keep in mind that for now, this unitary is only applied to the system. Now I want to evaluate the difference in entropy, right? So this dissipative work. To evaluate the dissipative work, I need to evaluate the work and the difference in free energies. So the work is sort of the difficult thing to evaluate in the systems, because there is no, in quantum mechanics, there is no observable that is associated to work as a quantity. So people standardly use the so-called two-point measurement scheme. In this scheme, the work is defined as the energy difference between the initial and the final state before and after the thermodynamic process. So if I use the two-point measurement scheme, I can define the stochastic probability that a certain amount of work W is invested in my forward process with this formula, where P and M is the probability of performing a measurement before the quench and observing the outcome En0, and then applying my unitary U, and then performing a second measurement afterwards and observing the outcome Em tau. So P and M is the joint probability of observing En0 at time 0 and Em tau at time tau. Instead, W and M is the amount of work performed in this single run, and it will be basically the amount of work that I need to bring my system from the state En0 to the state En tau. This is linked also to the stochastic entropy, which is this, which can be proven to be equal to the logarithm of P and M over tilde P and M, where I remind you, this tilde was indicating the time reversal processes. And so basically this stochastic entropy gives us a quantitative description of how distinguishable the P and M is from P tilde and M, so the forward from the backward probability. In the same way, I can apply the two-point measurement scheme to evaluate the probability in the backward process to observe a variation of a work W, which is given by this formula. So this would be what I would be using if I were just to look, if I was just looking at the classical microscopic system and I was just trying to observe fluctuations. But we want to look at this superposition of forward and backward. So we will do an extension of this. This extension will look like that. So at the beginning, I create a superposition between the two auxiliary states. Then in the forward, as I introduced before, I will perform a first measurement, a forward process, and a second measurement. In the backward, I will perform a first measurement, the time reversal process, and the second measurement. And then I will interfere again the forward and the time reversal processes, and I will measure the auxiliary system. So this will be my extended two-point measurement scheme that will enable me to evaluate the the entropy in this quantum superposition of processes. Now, of course, one remark I should make is that these measurements have to preserve the coherence. So how do we do this? There will be this, whenever this auxiliary system is 0, I will implement the identity on E, and I will do a first measurement, the unitary, and a second measurement. And this will be the same thing for the time reversal. And now I will have that, I will choose an auxiliary system that is large enough that I can always encode states of my outcomes in a further state of my auxiliary system. So I will not project this state right away, otherwise I would just destroy my quantum superposition, but I will perform measurement and encode all those measurements in additional states of the auxiliary system, and then I will finally re-interfere them at the end. Okay? So basically, to sum up what I did so far, I had an initial state, I perform a map, MW, and then I will project the auxiliary system in a generic state Xi. And then I will do just identity to the system and environment. So if I want to look at the joint probability of obtaining a certain outcome of work W, having projected on a certain state Xi, I will just have to do this modulo 2 of this quantity. So just to simplify a little bit the formulas that will come afterwards, let me call PXW the conditional probability of obtaining the work W having measured Xi. And then let me group these two quantities in Q0 Xi and Q1 Xi. Now it's not important what exactly is in this, it's just to basically group everything in a single variable. The outcome I will obtain is this. So the probability of having measured Xi obtaining a certain amount of work W is given by this formula, where here, this is the probability of the forward, of having performed an amount of work W in the forward process. This is the probability of having performed an amount of work minus W in the time reversal process. And this is the interference term. The interference term looks like this. Now, I really don't want to enter in the detail of this formula because there is no point in entering in all these complicacies. All what I want you to remember is this dependency on beta alpha W and M minus delta F, which is this dissipative work. So all I want you to remember is this, that the interference term is proportional to the E minus beta W dis alpha. Now, this will be the incoherent part of my quantum superposition, which will be just compatible with running the process in one of the two temporal directions. And this will be instead the coherent part of my process, which is just a generally quantum feature that arises indeed from this quantum superposition. So whenever I will perform this two-point measurement scheme and observe a very large entropy variations, I will effectively project on the forward component, because as you can see here, this one will go to 0, this one will go to 0, this one will be the only one left. And this would be equivalent to having measured the auxiliary system and projecting it into 0, but I didn't do that. I projected it into plus, and I didn't project my system. I only measured the entropy, but this effectively projected it into the forward component. Vice versa, whenever I will observe a very small entropy variation, so very large in modulo, but with a negative sign, I will effectively project in the time reversal one. So this was to answer the first question about how about when I observe entropy variations that are very large. Yes, I will project my state into one of the two components. But now suppose instead that I don't get a very large entropy variation, but I get a smaller entropy variation. In this case, the interference term is the one that actually becomes relevant. So let's just consider a more concrete example of a spin 1/2 system that is subjected to a magnetic field that is rotating within the XZ plane with a certain angular velocity omega. This will be the Hamiltonian of my system. Just to visualize the system, you can basically imagine it as a spin system that at time 0 is in an eigenstate of sigma z, and at time tau is in an eigenstate of sigma x. Okay? So this will be my system. And now I create quantum superposition between performing this quench of rotating from eigenstate of sigma z to eigenstate of sigma x in the forward and in the time reversal quench. And then I will project my auxiliary system in the states plus and minus, as I did before. So if we look now at in the limit of a rapid quench, so for instance, like the example as I was showing you before in this vessel where I was pulling out very fast, in the limit of a rapid quench, we look now at the probability distribution of the work W in the plus and minus states of the auxiliary system, and we will compare it to the mixture of a classical system. So this will be the mixture, this green bar. We will have that, as you can see here, the interference term can either sharpen or flatten the coherent work distribution. And so effectively, it will be increasing or decreasing the degree of reversibility of this quench. Now, because in this specific case, reversibility means adiabaticity, in the post-selected case, if I only consider the state plus, for instance, I will see the probability distribution over slower quench. So what I will have obtained is that I am in the lab and I want to perform, let's say, a very slow quench on my system, but it's very difficult for me to actually slow down my quench. What I can do is I can perform, for instance, a situation like this. So I can create quantum superposition of forward and backward quenches, and I will effectively observe a slowed down process in the forward, in the post selection, in the plus, for instance, state of the auxiliary system. So with this, I reached the conclusions of all what I wanted to tell you today. So I tried with my talk to address two main questions. I hope that this was clear. The first question was how a definite thermodynamic arrow of time can emerge with arbitrary superposition of forward and backward processes. And I showed you that this happens when I measure the entropy and I observe a very large entropy variation in either the forward or the backward temporal quenches. And then I showed you also that instead the interference term becomes relevant when these entropy variations are small. And in particular, I showed you that some processes that can be more irreversible can look less so, and vice versa. Also in our paper, we show that similar technique can also be applied to cases that are not necessarily time invariant of one another. For instance, we applied our scheme also to the case of some thermal engine, so a reservoir and a heat engine. Future directions where we would like to go, well, one option is to apply all those concepts to more complex quantum thermal devices. And another option is more a bit on the foundational side, is to apply all these findings to other sort of entropies, for instance, the coarse grain entropy. And with this, I thank you for your attention and I conclude the presentation.
Thank you, Julia. That was a wonderful talk. So I believe there would be questions from the audience. So if you have questions, please raise your hand, or you can also write on the chat box. Is there a question? Okay, so before we get some questions from the audience, I have a couple of questions, Julia. Mm-hmm. So first of all, when we talk about fluctuation theorems, so normally we have, of course, as you mentioned, I have a state, I let it adiabatically evolve, and then I let it thermalize so that my dissipation may occur, right? But here, except the final measurement and also some selection on your ancillary system, that is like your control system, mm-hmm. You actually don't have dissipation as such because you consider your initial state to be like in an entangled state with the environment, right? So how do you explain in particular here this dissipation term?
So I connect. So at the beginning, my system, I am performing only this this unitary on my system, and the system is not connected to the environment. But then later I connect the system to the environment, and there is this exchange of heat. This exchange of it will create in turn a change in entropy. And this is all what I need for basically estimating this dissipative work. This heat exchange, this thermalization of my system creates a difference in the entropy between the initial and the final state of my quench. And this is what I will be estimating. I will just check the difference, the distance between the initial and the final.
So this part is clear, but because by looking at your expression in particular, where you started with the pure system environment state, right, where it is like this, it is square root of this the thermal population, and then you sum, right? So in this case, if I see you started with even a state which is already in entanglement with the environment, right? So essentially,
it is already in entanglement with the environment, but then I unconnect it during the quench. So at the beginning it was in equilibrium, but then the unitary brings it out of equilibrium.
yes,
and
but
that's
equilibrium does not mean that it has to be an entanglement, right? Equilibrium means there is no correlation between system and environment.
Yes.
But
yes.
there is entanglement.
There is entanglement between the two because I have a forward quench and a time reversal quench. And so it is at the beginning in entanglement because I was having this side zero of the auxiliary system. And then I unconnect it to I isolate my system and I perform the quench. During this quench is not connected to the environment. And then I plug it again to the environment and then it thermalizes after. But during the quench, it is not to be connected to the environment so that I can single out my work.
Okay. So the second question in this line is that, of course, I see that if I measure my control system in plus and minus, I see the interference, right? And there where at some point you see the effect of interference appearing. So that means, of course, if you just trace it out, for example, I just ignored my control system, I'm not supposed to see any effect, ideally. So that means whether you choose it to measure in plus minus basis or 0 and 1 basis or completely ignore it, you see some difference. So I believe that this particular selection in measurement does have something to do with this interference, and that in principle should ask some thermodynamic resource cost. So how do you count that?
So you are saying that the projection of the auxiliary system in plus minus should have a thermodynamic cost.
See, I see the effect already, right? Effect of it. So that means it has something to do with thermodynamic cost.
Well, but in a sense, I'm just rotating the state because I'm going from one basis to another. I will have a state plus and I will have a state minus. So I did not think about this aspect, but I would not say that I'm not neglecting any part of my system. So I'm not. I mean, all the thermodynamic costs are taken into account in this 2-point measurement scheme because I'm not throwing away any part of the system. I will only be throwing it away whenever, for instance, I want to, I don't know, for instance, as I was saying before, speed up my quench. But in all these cases, yeah, indeed, there will be a waste of this invested work, for instance. So I will have to pay the expense of having to throw away part of my system in order to observe some, I don't know, speed up of my quench. But this is only in all those situations in which I perform post-selection, so in which I decide to only look at one of the two. But in all those cases, I'm not throwing away any of the two. So in all the cases where there is no post-selection, then I would consider that there is no.
Okay, thank you, Julia. So we have a couple of questions coming from the audience. So first I will consider Rajendra. So Rajendra Singh Bhatti, can you please unmute yourself and pose the question?
Okay, thank you. So my question is that when we talk about time reversal, we consider the evolution equation is dynamics is fundamentally reversal. Like we put some reversibility in the Schrodinger equation, but here you are considering the Hamiltonian, the unitary time reversal unitary, which is generated by the same Hamiltonian and different Hamiltonian, but the same dynamical equation. So my question is it equivalent to the to the fundamental time reversibility we are talking about?
So, so that, as I was saying, if you just look at a time reversible phenomena, then you cannot single out an arrow of time. As I was showing you this movie at the beginning, for instance, and there was this oscillator, and I was saying if the phenomena are intrinsically time symmetric, then I cannot single out an arrow of time because there is no, in each single run of my thermodynamic quench, there will be just zero change of total entropy. And so all these considerations that I was building upon that cannot be made. And so because of this, I had to introduce, for instance, this thermalization with the environment. So the unitary itself, only the unitary would be indeed time symmetric. And so it would have all these properties of whatever else time symmetric unitary that you observe in quantum mechanics. But I'm not only performing the unitary, because if I was only performing the unitary, this would be totally time symmetric. And so I would just be able to go forward and backward however I like. And I would not be able to tell this is forward, this is backward, because each single repetition of this process would just give zero entropy change. So because of this, I was then connected to the environment. I need to establish a time asymmetry. Otherwise, just every single run will give zero entropy and everything will just be absolutely time symmetric. And so all the consideration I was saying don't apply. You need time asymmetry in order to speak about forward and backward and an arrow of time.
Okay. Then my follow-up question is that since your observation of arrow of time is just because of you are projecting in the basis of arrow of time, let's say. So is it the definiteness coming from the collapse of the dynamics?
No, actually, it's not. This is what I was trying to say before. So you said that I observe a definite arrow of time because I project, let's say, in the basis of the arrow of time. But I'm not projecting in that, because if I was projecting in that, I would be projecting the auxiliary system in 0 and 1. So if I was, as you say, if I was observing this, let me get back this. In this, yeah, here. In if you see here, I'm projecting in plus minus. So if, for instance, I was stopping here and I was just taking this one, this would be only the forward process. If I were to take this one, this would be only the backward process, and this would be projecting on the, say, a well-defined arrow of time, just taking the state 0 or the state 1 of the auxiliary system. But I'm actually taking plus and minus. So what I'm projecting the auxiliary system on is in a superposition of the two, either positive or negative superposition. So by itself, I would not be projecting on the forward or time reversal. And this is why it's interesting, this result, because it's not just projecting on 0 and 1, which of course would then just be standard quantum mechanics, that the fact that I'm obtaining forward or backward. I am measuring the system, I'm projecting on plus minus. I'm measuring the system at a variation in entropy. And even though I'm just projecting on plus and observing a variation of entropy, I am effectively projecting my system in the forward or backward component because I observe a very large entropy variation. So this is the interesting part of the result.
Okay.
So we have one more quick questions coming from Ramandeep. Ramandeep, can you please place the question quickly?
Yeah, thank you, Manav. Julia, thank you for a nice talk. So my question is also a bit related to the previous question. So I understand that you can, if you have created a coherent superposition and you make a projection, then you can project to one of the states, right? But here, when you measure the entropy variation, then it actually decides which of the two states it will be projected to. So now in this entropy variation, there's a beta parameter, which is actually the inverse of temperature. So I was just wondering, how does the temperature is affecting the measurement of that entropy variation, or whether, say, if you are at very small temperature bath, then the entropy variation can be large. right? And so that looks to be counterintuitive, because at small temperature you actually expect that you will get interference terms. But it seems that due to large entropy variations, the interference terms may get cancelled there. Can you comment on that?
Yes. So when I was showing you before this these fluctuation theorems, I showed you. Wait, the next. Where is it? Yeah, here. I was showing you also this graph. I didn't comment on it, but this exactly is an answer to your question concerning the temperature. So as you can see, with the bigger the temperature, so the smaller the inverse temperature, the more you will observe these fluctuations. So for higher temperature, you observe more fluctuation than for small temperatures. And this is basically, this is a concept that applies to fluctuation theorems. So you observe more fluctuation the higher the temperature. This applies just in the same way to our extended two-point measurement scheme. We are building upon those fluctuation theorems. So the higher the temperature, the higher is the probability that some processes will be just as likely to occur in the forward and in the time reversal processes. And so the higher the temperature, the more superpositions I will be able to create of forward and time reversal. Instead, for very small temperature, I will have that the situation is very similar to the classical case, whereby macroscopic case, where I have this theta step function. For very small temperature, you see that it approaches the case of a macroscopic system. And in this case, I cannot build those superpositions because the probability of observing, let's say, the backward quench is perhaps just almost zero. And so it's very difficult to build superposition between forward and backward because it's just very unlikely to observe one of the two. And so it makes everything more difficult to build this whole construction.
But doesn't that go against the motivation to construct a quantum version of it? Because you expect quantum effects to dominate at low temperatures.
No. I didn't. No, we don't expect the. I never said that we expect those effects to dominate at low temperatures. I said that at low entropy variation. So the small entropy variation, I will observe that I have a very predominant effect from the interference term when the entropy variation is small. Whereas when the entropy variation is large, then it is more likely that whenever I perform a measurement on the entropy change, then I will effectively project my system in the forward and time reversal.
Okay.
So thank you, everyone. Actually, we have to stop because we are running out of time. So once again, thank you, Julia, for this wonderful talk and the discussion, and also the people who made these questions. Okay, so thank you very much. With this, we are going for the next talk of the session, and our speaker is
I just
Professor
unshare my screen. Yes.
Ravindra Pratap Singh. So let me say a few words about him to introduce. So Professor R.P. Singh is an experimental physicist from Physical Research Laboratory, Ahmedabad, working in quantum optics. His current research interests include quantum entanglement, quantum space communication, multidimensional entanglement using optical vortices, quantum imaging, and quantum cryptography, among many others. So today he will be talking on Hong-O-Mendel interferometer and orbital angular momentum of photons. So now I will request Professor Singh to present the talk.
Thank you.
Over to you.
Thank you, Manvin. Let me try to share the screen.
Please.
So screen is visible, Manvin?
Yes, we see.
Okay, fine. So hello to all the friends who are online and listening. And thanks to Kavita and Sandeep for the invitation. So this is basically done this is the work which is mainly done by Sarika, who is fourth year PhD student, and Nijil and Anindya. They are postdocs. Now Nijil has joined University of Naples, and Anindya has joined NUS, National University of Singapore, CQT. But when we started this work, they were here. So this is Hango Mandal interferometer and orbital momentum. You can read the abstract, it's written here. So I will reverse the order. First, I will introduce OM, and then we will go to HOM. OM is orbital momentum of light, and then we'll go to discuss about Hango Mandal interferometer. Although Anand has presented, Anand has described what is orbital momentum of light, but somehow he was in quite hurry. I wanted to present so many results. He has got so many results, and he was very excited to present all those results. So I will go slowly, and I will tell you what is OAM, orbital momentum of light, what is spinning momentum of light, what is the problem, how you can isolate in quantum mechanics, whether you can isolate them, orbital momentum and spinning momentum or not, and what are the classical experiment we have done, what are the results of that, and what is this new experiment which we have done. Quite exciting result we have got. I think that you will find it exciting. To me, it looks very exciting. So we'll discuss that. So mainly the main result are only in the last 3-4 slides of at the end. So this orbital momentum of classical in orbital momentum you define for electromagnetic wave by defining this total angular momentum, which is given in terms of Poynting vector. Once you have the Poynting vector E cross B, you can find out the angular momentum density, basically S by C square, just R cross P, moment of momentum. So yes, you can write in terms of momentum. So you define the angular momentum density, then you integrate over volume, and you get the total angular momentum. This total angular momentum you can write as sum of orbital angular momentum and spin angular momentum. This total angular momentum, orbital and spin. So that is classical. It's well known, okay, from electromagnetic theory. And it was Poynting who showed that for a plane wave beam of circularly polarized light, having plane wavefront, circular polarization, this angular momentum in that direction, and if you divide by energy, you get this kind of ratio. And this energy, you know, the energy of photon is, one photon is h cross omega. You just multiply by h cross up and down, so you get this spin angular momentum. Okay, so it is associated with circularly polarized light in light. So in case of light, it is associated with circularly polarized light, and you get the spin angular momentum plus minus h cross per photon. And it was experimentally verified in a beautiful experiment by Beth, who passed this light, okay, circularly polarized light, through a half wave plate, and it just reversed the direction and measured the torque on this half wave plate. Okay. And but before that, our own C.V. Raman, he has written a paper in Indian Journal of Physics in his characteristic style. First, he published this in Indian Journal of Physics. He mentioned that light carries this, photons carry spin angular momentum through his spectroscopic observations. He was he was very good in spectroscopy. So through spectroscopic observation, he could infer that light carries spin angular momentum, and he pointed out that in 1931 itself, and then later on he wrote in Nature as well in 1932. So that was there, but you won't find this Raman name in most of the papers. Generally they talk about Beth only, but Raman was the first who pointed out this light carries spin angular momentum, although it was not direct observation, but through spectroscopic observations he could infer that light carries. But if you don't have plane wave, suppose you have this kind of having azimuthal phase, a helical wavefront. So this, because of this azimuthal phase, IL5, okay, light carries, light becomes helical wavefront instead of plane wavefront. If you take this kind of wave and find out the ratio of angular momentum and energy, it becomes plus minus L plus divided by W. And same way, you know the photon's energy, h cross omega, you multiply. So you get orbital angular momentum and angular momentum part. Okay, that's how it was introduced in 1992 that light carries angular momentum, and very soon a lot of experiments were done and they verified that light do carry angular momentum as well as spin angular momentum, and they could separately show the effect. I will show you one of the experimental results, how you can see it separately, spin angular momentum and angular momentum of light, classical experiment. Now comes to quantum mechanics, angular momentum in quantum mechanics. So you replace these observables you write in terms of operators in quantum mechanics. So angular momentum operator, J cap. But our own Arvind, uh, if he's listening, he's online. So Arvind, Professor Chaturvedi and Professor Mukunda, they have written two very extensive detailed paper on orbital angular momentum and spin angular momentum of light. And this 2018 and again 2020. And what do they write? They write that this L and S, this cap, these operators, orbital momentum and spin momentum operators, go over into bona fide observables, but they don't follow the angular momentum algebra, like commutation relations. So they cannot be interpreted as orbital and spin operators. And they conclude that instead of calling OM orbital momentum, it should be called optical angular momentum. So that's what they conclude. And again, in their 2020 paper, they write the terms spin and orbital momentum of light are thus misnomers. So it's but you will see in experiments, it's not that confusing. And again, 2020, there is another paper. It's in archive still, and this Jubin Jacob from Purdue University, this Ang and Jubin Jacob from Purdue, and this Host Ravi from Alberta, University of Alberta. So they say that they have solved this problem. You can decompose this in orbital and spin angular momentum part, and they show that it follows the right angular momentum commutation relations. So it's really confusing when it comes to quantum mechanics, this quantization of orbital momentum and angular momentum, right? So it's really confusing. So one need to do experiments to solve this kind of problem. So let's see what the experimental results say. So let me show you. You can transfer. You can see here this orbital momentum. This is a classical experiment. You are transferring to microscopic particle your orbital momentum. So it's moving in the orbit. Okay, this is orbital momentum you are transferring. You can see particle is spinning around its axis. So this is spin momentum. So you can see clear like separation, clear if like completely different effects of transferring spin momentum and orbital momentum. So how do you produce these kind of beams having OM spin angular momentum? You know, a circularly polarized light you can produce with a quarter wave plate. So, but this OM orbital momentum carrying beams you can produce in the lab, although it's not like you require elaborate setup for generating these OM beams. So in nature also, if you pass your light through a rough surface, you get speckles. In there also you get this kind of like helical wavefronts in that pattern. So, but if you want to generate them in a controlled way, you have to make certain arrangements in the lab. So these are the some popular techniques we use to generate this kind of beams. So one is like cylindrical lens mode converter used to cylindrical lenses at certain distance through two way of this f is the focal length of this cylindrical lens, and then combination of certain optics. You can use this edgy modes. You have to have the superposition of edgy modes, and that will generate the vertex. Okay. But problem with this method, you get very good quality mode, very pure mode. But problem is that you have to start or experiment with higher order modes, edgy modes, higher order edgy modes. Instead of HG00, LG00, most of the lasers, they have Gaussian beams and lowest order modes. So you have to have this higher order modes to do this experiment or to get this kind of mode. This computer generated holography, that is the most popular technique, and spiral faceplate now getting popular, but there are limitations with spiral faceplate which are not there with computer generated holography. So you generate the hologram, you know your vertex, what vertex you want to generate, and then you interfere in computer itself. You can do interfere with plane wave or Gaussian beam, and that will generate this kind of pattern, okay, interference pattern, interferogram or hologram. Then you transfer this to a holographic seed, you can transfer, or you can transfer to special light modulator, which is liquid crystal based device, which can be refreshed in real time, attached with computer. So, but when you transfer to holographic seed, it's a fixed hologram. Okay, so advantage of SLM comes there. You can refresh in real time. You can make any pattern what you want. So you just pass through this branch point your beam, Gaussian beam, or plane wavefront, having plane wavefront, and in diffraction you get the vertex. This is for first order. You see two arcs dividing into one. You get first order vertex in first diffraction order. And you can use spiral faceplate also. Spiral faceplate, this thickness varies along the azimuthal direction. So this thickness has to vary in lambda. You have to change the phase by 2 pi. Okay. Thickness has to vary in such a way. This, phase depends on the path length and refractive index. Okay. So phase has to vary in such a way that phase changes by 2 pi if you want to generate this for first order. And phase has to change 4 pi if you want to generate second order for a particular wavelength. So particular wavelength, suppose 633 nanometer, you want to generate 2 pi in lambda, phase has to change like 633 nanometer, phase has to change 2 pi, and accordingly second order 4 pi. So it's so you limited by the order. You can't still technology is not so perfect so that you can give very high phase value. You can't go for very high order in such a small thickness order of the lambda. So when you pass your beam TM00 or Gaussian beam, you get the helical beam, and that also can be used to generate this vertex mode, LG modes. It is called Laguerre-Gaussian modes also, because Laguerre-Gaussian modes carry this azimuthal phase I raised power IL5. So that's what it is. These are the methods to generate. And then after generating, you can find out whether you have generated a particular vertex mode or LG mode or OM mode or momentum mode. So you pass through a tilted lens, very simple technique, just pass through a tilted lens. And depending on order, you will get number of this bright or dark spots. Okay. And that you can find out the sign, like topological charge it is called. Because these are topological structures. So you can associate topological charge also. So plus and minus depending on the winding of the helix, whether clockwise or anti-clockwise. So that's what you get, plus and minus charge you can define. And you can use the hologram again, the same hologram which you have used to generate, you can use to analyze also. Just you pass through this, and then m+1, this is first order. So m+1 combined with first order, suppose this is first order, here you will get Gaussian first order now. Okay, if it is first order. So you just get the Gaussian and then you couple with single mode fiber. Whatever order you generate accordingly that same hologram which you want to like check whether that OM is present in the beam or not. You generate that hologram and pass through that in first order. You will get this Gaussian beam and then coupled to single mode fiber that allows only Gaussian mode. So that's how you know that you have got this mode in the light. So this is another technique. This is called phase flattening technique, because you're flattening the phase. You are cancelling the phase with this hologram. So this is classical experiment. Before I go to quantum HM experiment, HM Hango Mandel interferometer, I want to show you the experiment in classical. What happens? You have you can 810 nanometer laser, this diode laser. It was available in the lab. You can use helium neon laser. It's any laser having Gaussian beam. You pass through the spiral faceplate, first order and second order, okay, and then pass through the beam splitter. This tilted lens is being used, You see that for L is equal to 0, this Gaussian beam, this slightly elliptical beam, diode laser, being diode laser. And for L is equal to 1 and -1, one is +1 and is -1. I think there's some mistake here. So this is +1 and minus, and both sides it has come. I don't know, +1, -1. One is 1 and 2. Okay, so depending on you see very clearly both sides. One is +1, other will be -1. One will be +2, other will be -2. Okay, +2 and -2. So charge has to be conserved. Okay, depending on. Okay, so this is order 2. So both sides you get a second order vertex. Basically, that's what I'm saying. Both sides you get the second order vertex when you do this splitting. If we are using a second order vertex or first order vertex, both sides you get first order vertex. Okay. Because of reflection, one will be -1, other will be +1. And then let's go to Hango-Mandel interferometer, the experiment. This experiment was first done in 1987. This PRL paper they published from Rochester. And what they're doing, they are generating this biphoton mode, 2 photons through KDP, type 1 parametric down conversion, PDC process. This is argon ion laser. Okay, they're using their argon ion laser 351. Okay, nanometer, and then do the down conversion. You get these 2 photons, and they are being combined at these beam splitters. And after this combining at this beam splitter, they are being detected. So what they observe, that if they are indistinguishable photons, like in all the respects, they are coming at the same time, they are having same polarization. So here it was same polarization, horizontal. And when they approach at the same time, this term, because of R and T, this term becomes cancels, and you get 2 photons either in this port or this port. So you get the, because only at one port you are measuring coincidences. You are both the photons, here 2 photons, both the photons going to same port, not the other port. So you get 0 coincidence, because only one port coincidence when you have photons at both the ports. You get 0 coincidence and you get the dip. So this is famous HOM dip here. Okay. And they use around 3 nanometer interference filter here. This is 3 nanometer. They write in terms of frequency, but it's around 3 nanometer if you calculate. So this is very important experiment, and it can be used to study indistinguishability of 2 photons. You can measure length of a photon wave packet, or coherence time, coherence length, and you can use it for producing maximally entangled states. And then you can use for quantum metrology, quantum information processing, 2 photon interferometer boson sampling. You use this kind of technique in boson sampling in quantum computation. And you can use in quantum communication. It is used for this entanglement swapping. So quantum network and all those things are long quantum repeaters. This is very important, and it plays a very important role there. So this is our setup. You see here, this is basically here. This is beam splitter here. This is type 1 BBO, 2 photons are being generated. And this is delay stage. Okay, having 1 micrometer least count, 1 micrometer minimum you can move. Okay, and this will become 2 micrometer because you have 2 mirrors here. So this is beam splitter. Here you are combining these 2 down converted photons, and then you place this SPP, spiral phase plate. So, and then you verify that your dip is very good. You are getting around 99% visibility. So both the photons are coming together, they are indistinguishable. Then you put a spiral phase plate. Okay, and then you just collimate that and pass to the beam splitter, and then you measure the OM of both the photons and do the coincidence. Okay, OM of this are the SLM. You project an SLM, as I told, phase splitting technique you can use here. And then single mode fiber you couple, and then these are special single photon counting module, and then you do the correlation. Okay, coincidence detection you do. That's what is the setup. So what you get here, okay, this is just to show that we have got very high visibility. We have checked with 3 nanometer interference filter as well as 10 nanometer. Just width is changing. This FWHM will change. This dip width, and that's all. Visibility remains same, and so that's what will happen. So that's what we get this result, OM distribution. Okay, I showed you in classical, it is second order, both the sides you get second order vertex. Okay, when you split, just because of reflection, it becomes -2. But here you will see this is 0. We have first verified with 0. Suppose there is no spiral faceplate. This is 0, result is there. Yeah. So there is no spiral faceplate. So you get maximum correlation for 0 0. Okay, that's fine. Now you go to second order. So second order spiral faceplate, if you replace put there, so you get the maxima for 1 1. So photons are carrying, like you have 2 photons, you are passing through second order spiral faceplate, and this orbital momentum is getting divided into 2 photons as 1 1. Okay, so and they're indistinguishable. Okay, you have to take, and they have to follow the OM conservation also. So this becomes 1 1. So that's where you get the maximum. And when you have SPP1, so what happens? SPP1, so in principle it should become 0.5 0.5. Okay, fractional thing, but fractional charges are not stable. They are not eigenmodes, okay, of the propagating wave equation, and they are not stable as such. It has been observed experimentally, and so it becomes either 1 or 0. So that's what you get. So if you put SPP, so these 2 photons, you get maximum coincidence either for 1 or 0. That's what you get. Same way, when it is SPP3, a spiral faceplate third order, you will get maximum coincidence because 1.5, 1.5, you will get maximum coincidence either at 2 or 1. The same you see, either at 2 you are getting or at 1, because 1.5 is not stable. So that's what you are getting. This is really interesting, and this is because of indistinguishability of photon. Photons have to conserve the indistinguishability, and they have to conserve the OM. And because 2 photons, so they just take 1 1 or 1.5, 1.5, 0.5, 0.5. That's what is happening, and which is not the case in classical. You can't explain these results using classical knowledge. So it's not only like beam splitter. Beam splitter, what it does, just it's 2 photons. It is 2 photons coming. One photon goes one way, other photon other way. So it's not like beam splitter is playing any role there. Second beam splitter. Okay. If you can measure this, it's just after spiral faceplate, you can measure this OM. So you will get, suppose this is 0, you will get at maximum at 0, just no coincidence, just after spiral faceplate, you are measuring with single SLM. And then if you have 2, you will get maximum. You see here, maximum you are getting for 1. Okay. Why I'm showing this? This is not very like even at 0, you will see this kind of OM modes are there. This can be reduced by changing the beam size. It can come down, and that's what we have to do. We have to clean up the experiment, but it's very clearly you can see that even with SPP2, you are doing single measurement SLM for 1. It is maximum, means both the photons carry OM 1 H plus. And if it is 0, and this is, I think, this is for 0 1, this is for 1. Okay, if this the LG mode is yeah, SPP1. If you SPP1, this is 1 0 or 1, you will have maximum. So it's not beam splitter just. So photons, because being indistinguishable, they distribute, OM is distributed, and they conserve the OM. So this is the conclusion. OM of photons manifests itself quite differently in a quantum system compared to classical. We have shown that. And indistinguishability can be considered as unique feature, very unique feature of quantum mechanics, just like entanglement. And this indistinguishable photons are a robust quantum system. That's what we're saying, because even after this diffraction through this spiral phase plate, indistinguishability remains there. Okay, so this linear diffraction through spiral phase plate, it remains there. Can be realized as a quantum resource in other information processing. So with that, I will end. Thanks, and I will invite questions, discussion, comments, whatever.
Thank
I
you,
think there is
Professor
time.
Singh.
Yeah.
Thank you, Professor Singh, for this wonderful talk. So now we invite questions coming from the audience. Yes, I see one hand raised. So Sandeep Goel. So Sandeep, can you please unmute and place your question? Sandeep? Sandeep, can you please unmute yourself and place your question? Meanwhile, others, if you have questions.
My system just crashed, so I was like, couldn't. So yeah, my question is, can you hear me?
Yes.
I can hear you, Sandeep.
So I'm confused when you send the photons from through this spiral phase plate of order 2, let us say. Why will not all the photons get +2 OAM? Why will they get 1, 1?
Why they will get 1, 1 in HM, you are saying?
So can you go back to your setup? I maybe missed something there.
Yeah, here.
Yes. So after the beam splitter,
This beam splitter, HM beam splitter.
yes. So either you have both photon in that arm, which is being processed later, or there's no photon, right?
Yes, right. So one is dumped a beam block. One is blocked. So either they have, whenever you measure, there will be 2 photons. Yeah.
There will be 2 photons. And now you are sending them through a spiral phase plate of order 2, let us say.
Order 2, right? Yeah.
So
RR1.
both the photons should get 2 units of orbital angular momentum.
2 units up. That's the thing. If you go by classical, so both the photons go 2 H cross. Yeah.
Yes. So you are saying there is a fundamentally different here in classical or quantum world?
Yeah. So because photons are having now 1 H cross instead of 2 H cross.
Yeah, but is there any theory to support that? Like I see that you have
I don't know. Right? There is no theory till now. Okay. There is no theory till now. It's just quantum mechanical effect of indistinguishability and you can say conservation. There is no theory. You can ask Arvind if he can give, because they have done extensive work on this topic, if they can come up with some theory, but till now there is no theory. This is first experimental observation.
This is really unexpected thing, because
it is very much unexpected. That's what. So, but that's why it is exciting. Yeah.
Okay. Thank you.
Any other question coming from the audience?
Arvind is there. I was expecting from Arvind something. No.
Okay. If there is no question from the audience, let us thank Professor Singh. Thank you, sir, for this wonderful talk and the discussion. And with this, we move to our last talk of the session. And
there is a question from Steph. I think I saw his hand. Yes, Steph has a question.
I have to move now.
Okay, Steph. Okay, Professor Singh, we have one last question before we move.
Okay, so, okay.
Yes.
Sorry,
so, Steph,
can I just?
yes.
I don't know whether I understood the experiment completely, but it looked to me that if you have an entanglement, if you come in with a pump that has 0 OM, and you down convert, you get 2 photons, and let's say the one is +1 and the other one is -1.
It can be anything, +2, -2. If it is L is equal to 0, then biphoton can be +1, -1, +2, -2, 0, 0.
Yes. Yeah. I want to consider specifically the case where it's +1 and -1.
Okay.
Okay.
So that's what you get. We have studied this OM spectrum. You see here, if you have L is equal to 0.
Can I finish, please? Can I finish that?
Yeah, sure. Sorry.
So if you then go through a spiral faceplate of +2, then one of them will go to +1 and the other one will go to +3, I guess. So then you would see two different OMs. That's what I expect from the result. Am I right?
No, I'm.
Can I interject a little bit here? Steph,
Yeah, sure.
If the two photons have different OAM, 1 + 1 and 1 - 1, then they will not show you the OAM dip.
Yeah, distinguishability will not be there. They have to be indistinguishable in HUM dip.
Okay, but in
You're
your
doing HUM
experiment,
experiment, so they have to be indistinguishable. They have to be same photon, same properties.
yeah, but so that is what bothers me. In the experiment, to see the Hong-Mandel effect, you need to go through a beam splitter using both inputs and both outputs. But I don't see where in your experiment you go through a beam splitter with both inputs and both outputs.
So this is basically we are using one output here, one is being blocked. So basically, whenever you measure, you will have two photons only.
Hong-Mandel effect. That will not give you the Hong-Mandel effect.
We have measured earlier. First, we have measured HUM dip. That's what I'm saying. This is the dip you are getting. Now, this is the method you use to generate two photon state. So here you are generating 0, 2 and 2, 0. So this is basically you have 2, 0 state. And then you pass through spiral phase plate and then you measure the OAM. That's what we are doing. So that's what we have confirmed this thing.
That's classical interference effect. That's not Hong-Mandel.
But Steph, let me say here something. The setup before SPP, spiral phase plate, is one set. That is the only purpose of that set is to get two photon state. Okay, two indistinguishable photon in one beam. So first you can calibrate the setup on the left up to the beam splitter and you tune it such that you get the Hong-Mandel dip. When you have Hong-Mandel dip, it means there is no coincidence. It means either both photons are coming in the vertical arm or in the horizontal arm. So once that is tuned, now you know that in the beam which will pass through SPP will have either vacuum or two photon state, nothing else.
Right, Sandeep.
No, you can't have it. Oh, you mean, okay, sorry. The vacuum or the two photon state. All right, okay.
Right. So the vacuum, if vacuum is there, then it's not going to change anything, but they need two photon at the same time. And this is what they use.
Okay, but so in other words, at that point, there's no OAM in the photons. It's only the 0, 0.
Most
because it's 0, 2. Either you get 0 or 2. So 0, no measurement, nothing. At 2, you measure when they are 2, when they are together.
Number of photons, but what is the OAM of those photons?
OAM, it will decided by the SPP. So the order you decide by the SPP. So you
Before
give
SPP
2, you expect that it will be 2H cross each photon, but you get 1H cross, 1H cross. That's what.
Okay, I'll have to think about this. Thank you very much.
Okay, so
thank you, Sandeep. Huh? You could follow the experiment. Hello? Very nice. At least one could follow.
Can I say something?
Yeah, sure.
Sarika, please go ahead.
Hello.
Yes,
Sarika,
yeah. So before the SPP, both the indistinguishable photon have Gaussian mode, not the other mode. So we are using only Gaussian mode, then we are putting SPP. So the order will be divided into two Gaussian mode photons, because other photons which having higher order mode, they will not contribute for the HUM dip.
I think that's right.
Yeah.
Good, Sarika.
So it means both the photons have 0 OAM value before they go to SPP.
Before SPP, yeah.
Yes. Because of SPDC, you will get either 0, 0, 1 - 1 or 2 - 2. But 1 and -1 are not indistinguishable. They are distinguishable. So they will not contribute for the dip. Only the Gaussian part will be contributed to the dip. And then we are using SPP. And the Gaussian part will convert, participate in the SPP, and they will give.
Very nice, Sarika.
Thank you, sir.
Thank you for clearing the doubt. Yeah.
Okay, so now that the question is more or less answered, so we once again thank Professor C
Okay.
and all of you who
Thank you, man.
contributed to this discussion.
I
And
will stop sharing.
with this, we will move to our next talk, and which will be the last talk of this session. And it will be given by Dr. C.M. Chandrasekhar. So let me take this privilege to introduce him quickly. So Dr. Chandrasekhar completed his BSc from National College, Jayanagar, Bangalore, India. In 2002, he moved to University of Oxford, UK, on Rhodes Fellowship. At Oxford, he worked on experimental Bose-Einstein condensates in the ultra-cold quantum matter group led by Professor C.J. Foote in Clarendon Laboratory. Then he moved to Waterloo, Canada, which houses the Institute for Quantum Computing and Perimeter Institute for Theoretical Physics. At Waterloo, he worked with Professor R. Laflamme and completed his PhD in the year 2009. He is currently a faculty member in the Institute of Mathematical Sciences, Chennai, India. So today he will be talking on quantum simulation for energy transport in an open quantum system. With this, I now request Professor Dr. Chandrasekhar to start the talk. Over to you, Dr. Chandrasekhar. Thank you.
Thank you, Manav. Is my screen visible?
Yes, we can see that.
Okay, so I think even the pointer is visible, I guess.
Yes, but it has to be made full screen, maybe the presentation mode or?
Yeah, it is in the full screen now.
Okay,
so,
okay.
I just checked because for me it's a full screen, so whether it's shared as a full screen.
I can see the entire screen of your slide, but seems like it's not yet full screen, but I think it's not full screen yet.
Yeah, just give me a minute. I'm trying to.
Yeah.
Now, Manav?
Yes,
sorry,
but we are on the second page, probably on the outline slide. Maybe you have to click on the screen itself and then press the left button.
Okay, good. So now it's full screen visible.
It's full screen, but not the
so,
first. Yes, now it's clear. Yes, please go ahead.
Okay. So thank you very much, and sorry for the time it took to set it up. I'd like to thank the organizer for bringing us together online to discuss some of our works. Hello. Yeah. Okay. So so this is a work which is done by one of my thesis student. She was an undergraduate final year student, and she worked on I think simulating energy transport mainly, and what are the ways we can try to look at mainly quantum circuit approach, so that you can digitally simulate energy transport in open systems particularly. So this work is an archive, and then it's also been accepted for publication in New Journal of Physics. So before I go to our work per se, I would like to give a general introduction to a quantum simulation. This outline of the talk, where what is the motivation for quantum simulations and how do we go about simulating quantum systems. And one simple example is the Dirac equations, where we don't have interaction terms, and how do we look at the discrete simulation of them. So I'm going to give a simple or a very quick run over to the simulation of Dirac equation, so that you get an idea of how you can simulate a simple closed systems. And after that, if you want to simulate an open quantum systems, and what are the approaches? And we have developed a simple new framework to simulate environmental assisted quantum transport. That framework we're going to outline, probably like, what are the approaches and how we can do it. That for a FMO complex. So that's something, one of the very well-studied model, and we have chosen the well-studied model so that we can repeat or reproduce some of the experimental results from by applying our framework. Also a quantum circuit so that you can actually have a circuit formalism so that it can be simulated on any quantum computers which are available. Might be the circuit depths are all still long, but still it's coming based. So to give a very quick introduction to quantum simulations, the idea of quantum information computing originated from this thought from Feynman, where he suggested that you want to simulate a real physical system, then it has to be from a quantum system. So it means a quantum simulation uses principles of quantum to develop tools to solve some challenging problems in basic sciences where quantum effects are prominent. So it can be, it need not be specific to some areas. It can be anything like physics to chemistry, biology, materials, where quantum effects are prominent. So the simple schematic picture is here where systems and there is some evolution. I put it at a more simple terms where you have a unitary, you have a final state. But a simulator is something which you prepare an initial state and then of set of evolution operate, and then you have a final state. From the final state you measure, and there is a mapping. One has to look at the mapping of the initial state and a final state. So this is a simple, quick idea of what a quantum simulation or what a quantum simulator really does. Okay. So next, the main objective of quantum in current days research scenario is to try to organize a controllable quantum evolution in order to simulate other inaccessible complex systems. So mainly, there are many high energy physical systems or biological systems or chemical complexes, which we really can't go through those minute systems and directly study them. So one has to simulate them in other accessible systems, and you can manipulate and have a control. A quantum systems. To simulate quantum systems in a classical system, you need an exponential resources. So to turn those exponential scalable resources to a favorable quantum machine. So these are the two main objectives for simulators. So quantum simulation all field has been quite robust. A lot of research is happening, and it's been divided into two main sub categories. One called a digital quantum simulation approach, and the other is an analog quantum simulation approach. Whereas both has some advantages and approaches are different. In a digital decomposition is done on a complex systems into a smaller local terms, and then you start approximating or stepwise unitary operations from that, and you try to minimize errors so that you arrive at an operational scheme. Break a given component into a set of smaller unitary operators, or you can have an local operators, and some approximations are required in this process, but you're bringing it down to smaller. The next is an analog simulation, where analog version represents an alternative approach that is not restricted to register of qubit, and the dynamics are not necessarily built upon gates. So this is main, like you have one system, and then it has certain kind of Hamiltonian, but then you have another system which has a closer or a related Hamiltonian, and little manipulation of those Hamiltonians will be able to reproduce the system which you are looking at. So these are analog quantum simulations, but the analog simulations are be flexible, and then it's not an universal character. And there is a very detailed review long back, and the area, many things I've added up for that, but one can look at these two things. So our interest is mainly towards a digital quantum simulation kind of research you try to do. So we want to have an or algorithmic approach using qubits. So it should not be a specific, like when you look at analog simulation, We are trying to look at the system in which it is simulated, and then you try to work it out for that. In this kind of approaches, you want to have a generic operational approach or algorithmic approach, so that irrespective of the system you are looking at, either it might be an NMR system, or it might be a superconducting system, or it can be an ion trap system. So you want to have a protocol, an algorithmic approach for the simulation. Okay. So one simple example I'm going to present, which is also one of the things which we did. So we did some theoretical, so that how a simple, a closed Dirac simulation can be done in a digital quantum simulator. So a very well known textbook equation of Dirac equation is presented here. So you can see you have an Hamiltonian, and then you have a mass term, you have a velocity term, everything there. And if you take this differential equation and try to the difference operators take into consideration, you can arrive at some cellular automata model where you would have an equivalent form in a discrete formalism, where you have t minus s or the hopping terms to the right term, beta are something which corresponds to mass and hopping strength of it. So you can actually bring this Dirac equation to a Dirac cellular automata formalism. Now you have some discrete formalism from which you can again in mass terms and a quantum circuit formality to simulate this expression, which is a matrix with the hopping term and everything. Then effectively you have simulated a Dirac equation. Okay, so to do this, there has been a standard algorithmic approaches just known over years. People we have worked and developed explicit protocols to do that. So one of them was a quantum walk model, where you toss a coin because it's a quantum state. It can be like the classical one where simultaneously move to the left or right. It means left and right. So, and be in superposition. When you have a continuous superposition of to the left and right, you end up having this red curve, a standard, which gives you a quadratic spread. So it also has very wide algorithmic applications. But to recover this kind of equation, where we have a Dirac cellular automata model, some fine changes are to be done to Dirac equation, where you split the single step of walk into two steps. We not have to go into detail of it, but you can say some modifications to the walk will give you some fine oscillations and recover a cellular automata model. So you have a quantum walk of this particular form. Again, you have a shift operator, the cos theta sin theta terms are the coin operations, and you can see, you can go back here, you have a same structure, mathematical structures are the same, identity and the coefficient element of diagonal elements and the diagonal element. So in principle, you can use quantum walk to simulate Dirac cellular automata, which does straight away map to a Dirac equation. So this experimentally was done very recently. The whole approach of taking this kind of formalism, writing down a quantum circuit for it, and then implementing it in an ion trap 5-qubit, 8-qubit machine is used. And only 5-qubit was used for the processor. So you have a coin shift operator, and then you choose your theta parameters. So the interesting thing here is that your two parameters, what you choose, thetas, are the one which kind of suit to recover the effects of mass in your dynamics. So it means that you can actually say what masses are used, and then how your outcome are measured. So this is the experimental results which was obtained in an ion trap mission, and then matching of with the classical results. And these are for different masses. So you choose different mass, and then you get a different kind of distribution. So this was only done for the quantum circuit was worked out optimally for less number of qubits, so that you do the process 130 or gates. So this is a clean closed system, because Dirac particles don't interact much with at least the kind of the equations which we took in high energy. The Dirac equations are not interacting with the environment. So you can take a clean system, and once you have a unit operator, you can work out a gate and then implement it on a system. So now, to go for an open system, the things are not the same. So it means that you are not have a clean system and you have many. So it means that most quantum systems interact with the environment. So the thing is, if I have to simulate a system which interacts with the environment and still has some quantum behavior in it, well, that's where crucial things come in, right? So there are many studies which says that you an efficient energy transmission in quantum transport, which is called an environment tested quantum transport system, where you can have an enhanced transport. So one simple or a very famous example, which has been very well studied with a lot of literature, is a Feni-Matthew-Osler protein complex. It's one of those widely studied photosynthetic systems. It transfers energy with very high efficiency in certain photosynthetic bacteria. The whole idea for people to look at this is try to see a way or a methodology so that you can use to develop an efficient light harvesting system. So if you can mimic and understand them, you can look at it. And it's one of the reasons why it's been very widely studied. In fact, it took many years to people to say the existence of quantum behavior in it was the one which was contributing for the enhancement. So there are two complications here. One, to simulate an open quantum systems, it means that you have to take a quantum system and also introduce a noise to it. In addition to the noise which is present, you are taking. So in most of our simulators or the processors have some noises, inbuilt noises, occurrence times are less. In addition to that, you have to engineer environmental noises into those systems. Okay, so this are the challenges. So in fact, why it's very important and still, one of the active areas is that it's a very promising applications of near-term quantum simulators are to understand the dynamics of the system, because these are like smaller complex systems where you have quantum coherences and also some noise effects. So it's something which there are some references. Probably I'm not been very explicit in putting in all the references, but few important references are there. So keeping this in mind, we want to see how best we can look. For example, to simply begin with FMA complex and try to take FMA, which is I'm going to give a pictorial representation of it later on, but it's a very simple complex of about 7 sites where there is a dynamics of exciton happening there. Still, a complete digital simulation of FMA complex not being done. It means that some effect of noise has been modeled and some effect of unitary evolution has been modeled, but not a complete simulation exists. The reason is very simple. The master equations are one of the most widely studied tools for describing open quantum systems. And to develop, one needs to solve an evolution operator. One needs to solve a master equation. So it means that you have some dynamics which is almost all of or the maximum component of those evolution equations into an operation formalism. So, but solutions of master equations are generally not known, and that's one of the major hindrances for it. Okay, so what the theoretical framework which we wanted to look, in fact, was something motivated from many of our earlier studies. Just the most standard approach for an open quantum systems is you have a Lindblad master equations, which would you have the terms which are described here. So you have an hopping terms which are and a standard Hamiltonian which leads. You have an energy of the state, and then you have a coupling terms leading for different coherent operands. So you have a system with different sites. It can be represented by M, and you have a quantum gems which is a phonon bath Hamiltonian. So you have system Hamiltonian, bath Hamiltonian, which contributes for a Lindblad master equations. Okay, so there is this term which a coupling of phonon bath which comes into L operators form here. Okay, so this is standard textbook description of Lindblad master equations. Now, from that you can always say from these expressions you can kind of conclude that the coherence causes some, look at the hopping things, some speed up and there are quantum jumps, sudden hoppings, which is giving a directionality to the transport or the transport problem. And then the interplay of unity and evolution jumps is causing the, what you call environmental state quantum. Pictures which we can, quickly, roughly get from looking at the expression. But how do we break it down? Okay, so till now, there has been many ways people have looked into, and all of my follow-up talks is simply broken down into this simple picture. After that, it's only a mathematics, right? So standard state, like, we take, instead of taking large complex systems, let me take a state or two simple sites, and call them a state 1 and state 2, and you take just one possible, a single evolution, simple evolution, like state 1 to state 2. So there is a possibility of, self-looping, which is happening there, and there is a quantum jump, and then there is an unitary evolution between these two. So now, till date, there has been an Hamiltonian, which could have been brought down to unitary evolutions, and some effect of self-looping was considered in it, where a quantum jumps was kind of introduced in the noisy form, where the kind of closed model for FMO complex or an environmental quantum. So what we have done, what we tried to do was try to break it up into two sets of it. One, you only look at an open system problem, like you arrive at a cross operator formalism to recover an operation which does an exact or at the closest possible quantum jumps, and add an unitary evolution to that system, so that this unitary evolution would take into account the unitary and the self-looping components, or the probability of the state being in the same state. So this explicit way of putting in operation formalism of quantum jumps is something which is quite a bit new in our approach, which tries to account for finer details in the whole transport and recover the experimental results to the closest approximation. Okay, so how do we do this, break up the whole system? So for the whole evolution into two steps. So that's something now it's sort of a mathematical writing down the terms. So here we took only one state, going from state 1 to state 2, and then you have a quantum jump. But if I'm taking a multiple jump, it means that there can also be a self-looping here, and then a quantum jump from this point to this also. So then you have to break down the state. It means that it's a state to the left. This probability it goes from 0 to 1, some probability is from 1 to 0. And this transition, now we can treat it as a bigger space and then take it as a closed system, which means that I take two qubits as baths, where the first qubit B1 captures the first quantum jump, the qubit B2 captures the second quantum jump. So I can write down the system and the bath evolution equation in this form. Now, this is a system, the first term, and the second and third terms are the bath terms, and introduce the probabilities of going from one to the other. So now, by tracing out the bath term, and I can end up getting cross operators equivalent of the form of these two of these transitions. So now I have this M00, M01, and all these four terms. Okay, so now these terms are followed up with a unitary operator. So you can see here, these two have a unitary operators and don't have. So now a discrete time dynamical equations, just plugging them into a rho t plus delta t1, we end up having an expression of this form. Okay, so now we see here the first term and the last three terms here. So these terms are something which represents the quantum jump. The second and the third term captures the decoherence and contribution of normalization terms. So there are some differences here which will come to it, and captures the unitary evolution. So now the same thing when you just write down in terms of M operators, the M0 and so they are not the same, the symmetric. There is some asymmetry term in the second and the third terms. This makes a difference in our approach to the earlier known formalisms, where these terms of asymmetric elements won't come, and this asymmetry element come. The asymmetric elements which are coming in the dynamical expressions is something which is capturing more details in the evolution which is happening in our model. So just with these terms, hello, okay.
Yes.
So
yes, go ahead.
yeah, okay. Sorry, I think there's at some point. Hello.
Yes, Chandru, please go ahead.
Sorry. I think there's some point I had got a disconnection notice. Okay, so now from this dynamic expression, so you can actually, the details are there, old mathematical details in the paper, which is available in archive. We can work back from this dynamical expression and arrive at the Lindblad master equations without much endurance, but it's only a little detailed mathematics. So one can look at the correctness of it by going back to this. So, I mean, the whole difference is with these two terms where we have an asymmetric terms which is coming in into the open when we try to get an operational formalism for the framework. Okay, so now to the same thing, one can introduce a tunable Bath coupling. So where you have sky, where we can introduce different strength of system Bath coupling. This can digitally be simulated by following some dynamical equations here. So where your temperatures or any other component can be introduced in the form of chi. Okay, so using this formalism, we wanted to test the known experimental results or something a complex system which has been very well studied. And this is the FMO complex which I had mentioned initially. So there is a pictorial representation which is available in a computational biology page of University of Illinois, where you have a light falling in on chromosome, and then you have an FMO complex here. This is, in fact, from here it's a direct transfer, and there is a 7th site here where the whole transport happens, and then there is a reaction center to which it goes. So one can look at the different paths for excitation to go from one to the other, and the whole setup can take multiple paths. So the way hello, yes.
I think your screen is frozen. It is not. Slides are not changing.
Okay. To which slide?
We are theoretical framework of ENQT. We are still on 29th slide.
Yeah.
Okay. So is it changing?
Not yet.
Okay. Apologize. Internet connection is good, but
I mean, just unshare and share it again, because I think your connection is not very good. So just switch off your video and we can listen to your.
okay. Is the screen?
Yes.
Okay.
Yes, it's
Is it
working.
changing?
Yeah.
Yes, now you can change it. Yeah.
So, yeah. So now, it was frozen at this screen. So I'd say, so one can do a Bath coupling by just adding chi terms, and then the standard methods of how we do various state evolutions is shown here. So you can introduce the temperature term and all of those things. So from our formalism, we just want to try to test the FMO complex and apply the dynamical expression for that in operation formalism and see the result. So this is a schematic representation complex where you have an energy which falls on the complex, and then there is a transport of energy. It goes to the reaction center. It can take various paths, and there's one representation here, and there is an excitation input, and it can take a path. So there is a representation of output and path C. So what we have tried to reduce or do was to try to reduce it to the graph formalism and put it into this particular form. Anything can be an input state, and any state can be an output state, and that's how usually it is in FMO complex. So now for this complex, so the Hamiltonian of multichrome chromophoric system is given by this form, which has 7 centers. So it means that you have going from 1 to 7. Then you have a creation and annihilation operator. Then there is also a Coulomb coupling of transition of density from one to the other. And then there is a phonon bath, which is a scaffolding, which was there in the figure here. The surroundings would kind of treat it as a phonon bath, which induces quantum jumps, decoherence, and dephasing. Everything comes into the picture. And Hamiltonian to have the phonon bath is here. And then there is also a radiation field, and Hamiltonian for the radiation field also is given for the system. So the standard known Hamiltonian for FMO complex with the phonon path and radiation field coming into picture. So now the third master equation for this system be given this formalism, and one can give a representative Lindblad superoperators for this. So now there are quantum rate jumps and the whole terms. These are all the terms which are there in the standard literature on FMO complexes. So what are the rate of quantum jumps, which has been looked into, where the temperature, frequency term all come in there. The rate of jump increases with temperature. This is something which we have from this one. So now, following our approach of how we work out, treat them as a separate quantum jump initially, get the operator formalism for the quantum jumps, and then introduce a unitary operator. So just applying that technique, not just for one site or two site here. So we did it for the whole 7 site. So when you do it for the whole 7 sites, so one can reduce it to, one can write down a mathematical expression for it in this form, and a solution for a Lindblad equation will be of this particular form. So it's mathematically, it's consumed some time, but it's one can work out the term, and then the numeric simulations was also done for it. So we could see that it matched with the experimental results to almost 98 point some percentage of it, where you could see if the initial excitation state was 1, so we get some slow efficiency, and then if the initial excitation was, so there is a faster increase in efficiency. These are the results which was noted experimentally and which matched completely into this. So now, because of our digital simulation approach, where you can actually turn on and turn off and selectively use operations, one could turn off the jumps and then study only the coherence behavior of it, which means just the quantum behavior in it from initial state site and how it changes with some particular time t, and what are the populations on different sites things could be studied unexplicitly. So by introducing temperature, one could also see or vary when we tried out for various things, but to match up with the experimental result. So there are the nice matching with the oscillation. One could see how the increase in temperature for particular excitation for a site as site 3, you would always see an increase in population compared to various other sites, or the 3 and even sometimes 4. So these are the observations which kind of help to weigh the connections between one side to the other, and our formalism of taking the discrete operations for the jumps and then unitary separately and bringing them together could reproduce these results with the final precision. Okay. So now, once we have it, the next step is try to see it's just an operators. We wrote down operators, and then we wanted to work out some circuit for it so that it can be simulated and see the number of gates required. Because once we want, if you want to simulate an open quantum system, you need a lot more cubes as a space, or like what we call an environment. So where we choose the 7 sites given by a 3-qubit system, and then the 2 bath systems.
Chandru, we lost your voice.
I think his internet crashed.
Okay, he came back, it seems. Chandru, can you hear us?
Hello?
Yes, yes.
Yeah, sorry. Was I lost in between?
Yes.
Or,
Also, you have to share your slide once again. We don't yet see your slides. Yeah, we are yet to see your slides. I think you are making an effort to share. Yeah, Chandru. Yeah, now we can see your slides.
okay, so you can hear me? Sorry.
Yes, we can hear you, though your voice is breaking a bit.
So I don't know what slide I was in. I lost.
So some observational facts you were mentioning, I think you can just start also from here.
So I was what, right? So at least this slide you can see.
Yes, we can. It's not full screen though.
Okay. In fact, actually, the whole the results are in the slide. As I mentioned, the framework is something which is very important in the beginning, that you could break the.
I think we again, so he probably went out of, yeah, went out of Zoom.
I think I again was lost probably my. So I was almost at the end of my slides. Hello, ma'am. You can hear me?
Yes, yes. Some time to time we are losing your voice.
Okay. Yeah, I apologize to all. I think. Sorry. The connections were good.
So you are on the last slide, yeah. Yeah. So here you were.
So, okay. So this is something which with our formalism of breaking down the evolutions in quantum jumps and then unitary them. So we could reproduce all the experimental results to almost 98% efficiency. So we think the way forward for us is to try to look at various other chemical complexes and probably other open system dynamics, and then see how best we can arrive at the quantum circuit models for that, to simulate them. And that's how something which we would like to take it further. With the result for FMO complex is very promising for us to take it forward. And that's all I actually had to say. But I would like probably stop at this point and take questions.
Okay, Chandru, thank you very much. I hope there will be some question coming from the audience. Please raise your hand in case you have some questions. Please raise your hand. Yes, Vikas. So Vikas has questions. So Vikas, can you please unmute yourself and place the question?
Hello, Chandrasekhar. Yeah, so thank you so much for the talk. So I have this question regarding the application. Like, can you point out other possible systems or other possible applications where you can use your method and see this and this phenomena of environment-assisted quantum transport?
No, so I think the environment-assisted quantum transport is one simple model we chose. But the formalism which we have developed or which I presented in the first half of the talk is applicable to, should be applicable to almost all open systems. The way we try to work out, it's just a rigorous formalism. So might be, we are looking at few other chemical complexes to take it up as an example, not just FMO complex, but and then see how you can work out the operations formula and then look at it. So, but mathematical framework to simulate almost all open quantum systems. In fact, we are trying to, the student who did most of the work, she's again working on making it more generic, not just for transport, but for the whole quantum systems, open quantum systems.
Okay.
Or might
Okay.
be
Okay. Thank you.
Any other question coming from the audience? Okay, meanwhile, maybe I ask a couple of questions to Chandru. So Chandru, so kind of model you have chosen here is like the ones you can write down in the form of Lindblad form, right? So yeah. So, but I know that there are plethora of operations or channels that are not Markovian, and even much of the cases you cannot write in terms of this Lindbladian form. So how you, so two questions actually coupled. So if they are non-Markovian and you cannot express them in general with Lindbladian form, how you think you can implement them using this random walk kind of model?
This is a very, very important question, which in fact, we started it some time back, but we are not reached to an exact formalism for it, but there are some promising results. Hopefully we'll be able to. So as a subset of it, one of the things which we tried to look at was,
Yeah, we lost your voice once again. Chandru, can you hear me? Your voice is breaking. Chandru, your voice is breaking, so I could not make out what you are saying. Okay, so apparently he's out of Zoom.
so
Yeah,
you
Chandru,
can hear me
please.
now?
Yes, please go ahead.
I think this is a very important question. In fact, that was one of our initial motivation. We could not reach too far with that, how to do a non-Markovian system simulations. But as a precursor, one of the other postdoc was working with us, with myself and Subhash Banerjee. So we are trying to simulate, have an operational or like a quantum walk model to simulate non-Markovian channels. So that result looked bit promising. It's still a very small step in that direction. And how we can bring them into a bigger picture and operation formalism is something which we would like to look at. And it's a very interesting question to look forward for us.
Okay, thank you. My second question was like, of course, I'm not really an expert in this. That's why I just like to know, because of course this efficiency, transport efficiency for FMO complexes are very high. So is there any reason for us to think that the dynamics there are Markovian?
Okay,
Because
okay, so
see,
there
the
is
moment you talk
no,
about, yeah, please.
yeah, so from what we have seen, we are not seeing any quantum bounce back into the system. Like for example, when we try to simulate the effect, to look at the numerical result, we don't see kind of oscillations as a signature for non-Markovian behavior in this FMO complex. So that's one of the strong reasons we could see to look at it. So I'll also tell you the other reason which is not there, which is not presented, but we tried to work out was, since I said quantum walk, if you take a quantum walk system and you trace out the position space, you can recover some non-Markovian effect because there's always a feedback. And that model could not be applied to FMO system. We could not do that, and we had to give up that approach and then take the approach which we have presented. So this indicates to us that we don't have a signature of non-Markovian behavior in this energy transport of FMO system particularly. I'm not saying about in other systems because, in fact, this also new started very recently looking at these kinds of systems. Might be we'll have more knowledge and understanding coming time.
Okay, thank you, Chandru. So with this, we are very close to conclude this session. And so in this session, we had 3 talks, and I would like to thank all the speakers of this session for these interesting talks and wonderful discussions. So with this, I conclude this session. Thank you very much. Thank you very much.
Thank you, Manav, for chairing the session. And I think this is the only session so far which was finished exactly at the time assigned at 5:10. So impeccable timing. So our next session will be chaired by Professor Aditi Sen. Aditi, are you here?
Yeah, I'm here.
Hi, Aditi. How are you?
Yeah, I'm fine. How are you?
I'm also fine. Thanks. So let me introduce our esteemed chair a little bit. So she did her PhD from the University of Gdansk under Professor Marek Zhukovsky, sorry. And subsequently, she was the Alexander von Humboldt postdoctoral fellow with Professor Levenstein, who started this conference with an amazing talk. And after that, she was a Ramon Y. Cazal Fellow in ICFO, the Institute of Photonic Sciences, Barcelona, and an assistant professor in Jawaharlal Nehru University, Delhi. She is currently a professor level H at Harishchandra Research Institute, Allahabad, along with 2 of her colleagues, Professor Ujjwal Sen and Professor Arun K. Pati. She started Quantum Information and Computation Group at HRI, which currently consists 3 faculty, 15 PhD student, and 5 postdoctoral fellow. Professor Aditi Sen was also awarded Bhatnagar Award in 2018. And I now hand over the mic to Professor Aditi to start the session.
Yeah, thank you, Sandeep, that you were so kind that you introduced even the chairperson. So, okay, so we start. So our good afternoon, everyone, and we start these sessions. This session also has 3 talks, and the first talk is by, because there is some change of I think schedule. So the first talk is by Isaac Knapp. So are you there? Hello?
He doesn't seem to be in the audience.
Okay, we can check. I guess he was the first speaker.
Yes,
of the
he is the
session.
first speaker. Dr. Isaac Nape, can you hear us? Our team is trying to contact him.
Okay.
We still have a couple of minutes before his talk.
Yeah, bit ahead of time. So.
Hi, Aditi. Good to see you.
Kavita?
Yeah.
Okay. Yeah. Actually, it's now kind of voice recognition is more important.
Yes, indeed. Everybody's videos keeps freezing, so.
Yeah. Yeah, I should also off the video because it may happen that.
No, but you should, you're the chair, so you should keep your video on while.
Yeah, that is what I was, at least after starting the talk.
Yeah.
So can you contact Isaac Nape? Or?
I think the team is still trying. Actually, we started the session a few minutes before, so usually we ask the person to log in and then he checks his slides and all that. So I guess, let's see.
While we are, this Praveen here, while we are waiting for him, can I check my slides?
Yeah, I think sure, you can check.
So can I share my screen quickly?
Yeah, so I think host has to give the permission. So can any of you?
Permissions are there, but once in a while it switches off automatically. So see if the permission is there or not.
I think it's there. It'll be very quick. I'll just flash it and Can you see my screen?
Yeah.
Oh.
Can you make it full screen?
Sure.
So that it's clear. Yeah, fantastic.
Okay.
Yeah.
Okay. I'll stop sharing.
Yeah.
Okay, thank you.
Hi, Aditi. I think instead of waiting for too long for Dr. Isaac Nape, we can start with the next talk because the speaker is ready, I think.
Okay. So yeah, that will be probably good. If he joins, then we can have a
next session, next
talk, or maybe at the end. Okay.
Yes.
So actually, Vidya Praveen is the next speaker. So Vidya Praveen Valamudi is the next speaker. So you can share the screen, Vidya. Hello? I cannot hear you. Yeah.
I'm here.
Yeah.
I'm just turning off my fan. Go ahead.
Yeah. Okay, so maybe I introduce Vidya. So Vidya Praveen Valamudi joined as assistant professor at IIT Madras in July 2018. His broad interests are in the areas of quantum technologies using defect centers, solid state materials, and nanoscale magnetic spectroscopy and imaging. His expertise is in optical and scanned probe microscopy and magnetic resonance studies. Along with his collaborators, he pioneered a technique for gigahertz range spectroscopy of ferromagnets using NV center quantum defects in diamond. And today he will be talking about detection and spectroscopy of ferromagnetic dynamics using NV centers. So Vidya, you can start your talk.
Hi. Yes, thank you, Aditi, for that introduction. And yes, I hope everybody can hear me. Sometimes my office room acts as a nice acoustic chamber and there's echo. I hope the audio quality is good.
Yeah, it is good. It is good.
Okay, so let me get started. in the interest of time. So I'll be talking about, as the title says, detection and spectroscopy of ferromagnetic dynamics using NV centers. And so we'll come and discuss what the context for the NV centers is, and I'll introduce them. But let me go ahead and first thank my collaborators and funding agencies, because usually at the end we are always rushed. And so most of the work, in fact, all of the work that you'll see is the work that I did while I was working with Professor Chris Hamill at the Ohio State University. So as a postdoctoral associate and a research associate, and various people from the group have contributed to this. So there's effort that I'd started working on NV centers. And so various graduate students, Michael, you'll see his work. Now he's at AFRL and he still sort of continues, and my collaboration also continues with Chris on the topic. So there are other groups at OSU and other places, all of whom I should thank, along with various funding agencies. Okay, let me give an outline for my talk. I will first, as we said, the NV center, which is actually a nitrogen vacancy center spins in diamond. These are what are important to us. And I will introduce what these are. These are of quite important, or rather of quite interest in the context of quantum sensors or even quantum computation, which have some great properties that we'll discuss. I should highlight, though, that while this is a quantum related conference, most of what I'll talk, I won't really get into truly quantum behavior, as in there won't be an entanglement or using phase relationship or superposition. But the point still is that most of the properties that enable these quantum sensing are sort of acutely important to the work I'm also doing, and sort of on the way towards a more quantum regime that we can use. And so I'll first introduce what are nitrogen vacancy centers. Then I'll discuss about how we are doing spectroscopy of ferromagnetic dynamics in diamond. There are different modalities. I will discuss one particular one that we have sort of pioneered. And so we'll discuss that. And so first I'll show the observation in different materials of how we could do spectroscopy. And then I'll get into the physics of it. I'll discuss the relaxation-based mechanism that enables our spectroscopic tool, and how a change of NV spin lifetime arising from magnetic noise due to the ferromagnets is at the heart of what we are doing. And then I'll present some newer results where we are looking at the regime of where if you drive the ferromagnet into nonlinear regime, then what happens? And in this case, you can enhance the applicable range of the spectroscopic tool. So I'll discuss that. And so introduction to the NV centers. The NV center, so I will point out, I hope you can see the laser pointer that I have on my screen. So the NV center is a defect in diamond. So diamond is made out of carbon tetrahedra. So that means one carbon bonded with 4 other carbons through sp3 bond. An NV center is a nitrogen, a substitution nitrogen, plus a vacancy. So a combination of these two defects is the NV center that we are interested in. And what I'm not showing is, of course, the nitrogen is a group 5 element, so it will contribute, it's a dopant, so it contributes an electron. What we are actually interested in is the negatively charged state of this center. So I won't keep saying negatively charged in the interest of brevity, but what we are interested in is the NV minus. And so that basically the center captures another electron from the lattice, maybe from another NV center or some other place, some other defect, but it captures another electron. And so that's the NV minus that we are interested in. And so what I'm going to show you is some of the interesting properties of this center that will play a part here. And so to understand this, I think the energy level diagram is the important one. I hope you'll excuse me for a minute. I was going to close my window later, but because we started quickly, there's a lot of noise coming from that side. Just give me literally 20 seconds. I'll be right back. Okay, I'm back. I hope you can hear me. And the advantages to living in the middle of a forest, but sometimes, you have to deal with wildlife. Okay, so the NV Center, we are looking at the, once again, you can hear, I hope. I've unmuted myself. So I'll continue. And the idea of interest to us is this NV center is sitting in the carbon lattice. And so the carbon itself, diamond itself has a band gap of 5.5. This NV center forms, essentially acts as a pseudo atom sitting deep. So the energy levels associated with the center, NV minus center, are deep inside the band gap. It acts as I said, an effectively a pseudo atom with its own energy levels. And what we are interested is going to be the ground state of this NV center. This is where what we'll call the qubit, or for us, the magnetic center, is going to be sitting. And it's going to be a spin triplet because there are two spins, one contributed by the nitrogen, one captured, both of them together, two spin halves make a spin one. And so this is what the spin triplet will look like. But the excited state level is also quite important to us, as it enables the sensitive spin detection that we are interested in. And so what we are looking at is the ground state, the excited state, and the separation here. There's a zero field splitting. That means even at zero magnetic field, there's a splitting between the 0 and plus and minus 1 states of 2.87 gigahertz. The excited state is about 637 nanometers away. That's where what's called the zero phonon line sits. So you can excite it using green laser. And for the students here, I hope you understand that the energy levels difference between 2.87, which is in gigahertz, and this optical transition is huge. It's few orders of magnitude. And I will let you work out how many orders of magnitude, but sort of be aware of that. So anyway, so you have a spin triplet, and we can excite the electrons from the ground state to the excited state. And where the nice, interesting things start happening is that we also have these singlet state, which are available to us. So these singlet states actually play an important part. And while the spin orbit coupling in diamond is weak, but it's enough to cause some of the plus and minus 1 electrons to sort of decay via the singlet states. And this is a non-radiative transition, non-radiative in the sense that under normal circumstances, you shine green laser, you're measuring a red photoluminescence or a red fluorescence, which is around in the range of 600 to about 700 nanometers. This transition is going to be not in that range. It is in a different range, so we don't care. So we won't measure it, which means that the fluorescence in red that we are measuring is going to be weaker for the plus and minus 1 states, okay, as opposed to the 0 state. And this is one of the key factors that is sort of interesting to us. And so this gives us, first is that the spin state can be read by monitoring the fluorescence. So plus and minus states are weak, and 0 state is bright, the fluorescence. This is the first thing you should remember for this talk. The second is also that if you do this optical cycling a few times, what you will notice is that all the electrons will come and settle down at the 0 state, okay? So even the plus and minus 1 will come and the 0 state will come, and they'll settle down. And so you can initialize the state with very high fidelity. I've said greater than 80%, but these days people routinely achieve, even at room temperature, fairly higher than this. At low temperature, almost 100%. So you can polarize the spins to a very high degree, which is not possible, let's say, in a conventional EPR or a conventional NMR experiment where you rely on thermal polarization. And this is, many orders of magnitude more than that, and enables great signal to noise ratio. So the consequence of both of these together is that you can detect the spin of a single electron even at room temperature. So for people who are used to doing EPR or something at room temperature, typically you need about 10 to the power of 12 to 10 to the 15, electrons and nuclei, depending on what you're measuring. But here we can measure at room temperature single spin. But again, I should highlight that while that is what we can do, definitely our experiments that I'll be talking will be mostly using ensembles. Even there, these properties are going to be of value to us. What is also important is that we can now manipulate and cause spin resonance. So we can apply microwaves between these ground state levels. And as we manipulate them, we will cause transition from 0 to plus or minus 1. So obviously, let's say you initialized everything to the 0 state. And then as you manipulate, and if you hit resonance, you're going to put spins in the plus or minus 1. That means the luminescence will come down. And so you have an optical readout for the magnetic resonance. And this is what is called optically detected magnetic resonance. And this is at the heart of what we are doing, okay? This optically detected magnetic resonance. And so to understand, in this particular case, I'm talking about the sensing applications. As I said, NV centers have other applications as well that people are contemplating for quantum technologies. And I'll give you a gist of where these different applications are coming from. So we can look at the Hamiltonian of the NV center. So we have the Zeeman term. This is what we're looking. So if you go back, the splitting between the plus and minus 1, that's the Zeeman term. There is the zero field splitting. In fact, both of these, all of this is coming because the interaction of the two spins. So you can write basically, SDS. So you have two spins that compose the NV spin. So you can write that and you can split that into the SZ squared part and SX squared and SY minus squared. And there's a bit simplified version of it. But this gives you zero fields and splitting. And this is because of strain. So I'll start with this gives you magnetometry. There's also, if you go back, there's the nitrogen nuclei that is sitting there that can have a hyperfine coupling. So that can give you hyperfine interactions, which are useful to generate nuclear memory. And so there's one of the reasons people are interested in making, let's say, registers for quantum computation. And then this E term here is sort of sensitive to the strain or electric fields that exist in the sample. So you could use it as a strain or electric field sensor. And you can also use it as a temperature sensor because the D term here is sensitive to the temperature. And this is just a gist of, well, I'm not going to cover all of this in my talk, but for students, sort of they can understand there are various other properties of the NV center which are important. So I have already discussed the optical readout, high fidelity initialization, all of these and some of these other things that are, but besides this, one of the central things that makes NV center so important for quantum applications is its long spin lifetime, which is also the long coherence time, which is very crucial, especially compared to what will be the effective gate time, which is the microwave manipulation on resonance of these spins. So that's one of the central features of this that enables a lot of the quantum technologies that people are interested in. And even for bio applications, diamond is biocompatible. So that's one of the nice things. But again, all of these things that you're doing, the sensing applications, the key part is it gives you very high sensitivity at the small length scale. So we are talking submicron to nanometer scale, or in biological terms, it will be single cellular to single molecular level. And so that's the power. We are not quite pushing spatial resolution in our experiments. As I said, we are doing ensemble measurements. So we are going to be limited by, in our case, the optical spot size, but in principle, they can be extended to a single spin as well. So let me get to the heart of the talk, which is the spectroscopy of the ferromagnetic dynamics that we are doing using the NV center. And so I'm going to first introduce the topic, I'm going to show you the observation of the result, and then I'm going to discuss the physics of how it's happening. And so I'll give you a gist of what the experiment is, and the experiment setup is actually not too complicated. all we are doing is we have ferromagnets that are, we have a ferromagnet here. So in this case, YIG, which is yttrium iron garnet. And what we'll do is we'll put a bunch of diamond. These are nano diamonds. So it's like basically little pieces of diamonds, but we get them in solution. You can just drop them onto the YIG. And so these have NV centers. And one thing I didn't point out is these are represented in this color because there's also how you give color to the diamond. The NV centers are what are responsible for making pink diamonds. So when you see a pink diamond, it means it has a lot of NV centers. So you'll have this nano diamond film here with NV centers in it. And to do magnetic resonance, we have to apply a magnetic field and we have to apply microwaves. And all we are going to do is now look at the light, and we are going to use light as a detector for this magnetic resonance. And for technical reasons of improving sensitivity, we are going to do lock-in technique, but we don't need to discuss in great detail that part. Okay, so we can do this, and it's not always that. We have done other materials. So sometimes you could have the diamond, you could have a diamond substrate itself, and you could put ferromagnet on top of it. YIG is hard to grow, single crystal YIG is hard to grow, so we have to put diamond on top of it. Sometimes you may have ferromagnet that you put on top of the diamond, and you can study that way also. Both geometries are possible. So let's understand what happens to the NV centers when we are looking at just the, if we are going to look at if the NV diamonds were sitting alone, let's say not on a ferromagnet, but on some non-magnetic substrate, let's say in this particular case, maybe glass, or could be just the substrate there without the ferromagnet. And what you're going to find is you're going to see this 2 spectrum from the energy level diagram that I'd shown you, but you see a blurred effect here. So this is the ground state of the NV center. What you're seeing, this 2 triangular, these lines emerging out of it. And this actually is the excited state. And these are the 3 at the bottom are artifacts of measurements. Don't worry about it. We have verified they don't play a part in our experiment. For now, we'll focus on this part mainly. Okay, this is what is important to us. First thing, of course, is that we are seeing many lines. And this is because we have a powder in our first experiment as opposed to a single crystal. And so the NV center resonance is dependent on the relative orientation of the magnetic field to the NV axis. And because in this powder, we have all orientations, you get a range of frequencies. So you get what's called a powder pattern or a powder spectrum. And that's what you're seeing. And that's why it's sort of smeared out. But this is the main thing. This is the ground state that we are seeing. So this is the ground state resonance. And this is the Siemens splitting at any given field. So if you apply a field, the external, the extrema are going to give you the maximum. So when the field is oriented along the NV axis, some of the NV axis will be oriented along the field. And so those will give you those extrema. And that's what we are. But what is of important to us, or what is sort of very nice that we saw, is that this is what happens when the diamond is alone. But now if you put NV on a ferromagnetic material, you're going to see this very bright change of fluorescence. Remember, all we are measuring is this change of fluorescence, which is basically a stand-in for the spin state. So we are changing the spin state of the NV as we are applying, as we are changing the field. And so this is kind of very surprising for anybody doing resonance on the first, at least at the first glance, is that the NV resonance is nowhere near, or this is the YIG resonance. So we see a change of fluorescence, which we have confirmed is not because of some change of temperature or some other reason, but simply because of the YIG going on resonance. And so the YIG resonance itself is very far away from the NV resonance. And yet we are seeing a change of the NV spin state itself. And so there seems to be a coupling, even though the 2 resonances are far away. And so this was a puzzle to us when we started. And so we started to understand at least the magnitude, especially. I mean, we did go looking for it, but the magnitude was a surprise. So we have been trying to understand it a bit. And so the first thing is, of course, there's the first detection of FMR using the NV center that was done. And it's also done in a sort of a continuous wave manner, which is sometimes easier to set up and do rather than a pulsed experiment that people have been using for any other NV spectroscopy. So where you do coherent manipulation of the what will be target spin along with the NV spin. And so then you can look at it here, just a CW experiment that we are doing. And so, of course, as an application, this is very nice that you can do this experiment, you can measure the spectrum. And as I said, we are measuring quite locally. We are measuring, in our particular case, given by the optical spot size. But of course, in principle, we could go even finer down to, and people have done it. Other people have now other people have done it. You can go down to a single NV center. We can do this. That was in YIG that I presented, yttrium iron garnet, of course, which is a sort of a canonical ferromagnet with a very nice narrow line width. We have now tried it on an organic-based ferromagnet as well, which is called VTCNE. And this again has a very narrow line width, comparable, and I think actually better than the YIG also. Well, comparable to YIG at least. Maybe the best YIG will be similar. And we see the similar thing. What you're seeing on top here is what we measure is an inductively measured signal, which is the more conventional way of measuring magnetic resonance. And so we can do that. But again, remember that this is being measured over a much larger area. So this is averaged over a large spot size, basically the entire sample or a significant portion of the sample, while we are measuring on something that is limited by the spot size. And so we can measure the signal. As you can see, there's nice correlation, and we can do the microwave. So this is the classical or conventional inductively measured signal doing microwave transmission. And this is the NV-based measurement. And you can see that there is good correlation again, that we are able to measure the resonance of this ferromagnet. In this particular case, it was nice, and we'll come and discuss this a bit. How this happens is that we are able to actually, we are showing that we are sensitive to the wave vectors, spin wave branches in the ferromagnet, which are in the exchange branch of spin waves. And these are something that are typically hard to measure, even with, let's say, BLS and other techniques. And so for us, it's nice that maybe we can contribute to studying some branches of the spin wave spectrum that are challenging otherwise. And so we have done this in other materials. So there's some magnetic metallic ferromagnets. We have done this in permalloy. We have done this using both nanodiamonds. We have done this using single crystal. We have done it in CMFG, cobalt. And as you can see, the signal varies, but we can still see the signal. And I'll highlight this low field, low frequency regime, which is much further away from the NV's own resonances. So the NV's own resonances are around 2.87 gigahertz. But the one of interest to us is in the lower corner, where we are seeing a signal that is coming from the ferromagnetic resonance. And so signal is different. We need to understand, and we are still working on understanding all the details, but I'll tell you where our current understanding is. What I won't have time to discuss is that we can apply this. And so what I'd shown you earlier was thin film YIG. If you go to thicker film YIG, which has much more richer magnetic spin wave spectrum, we can sort of identify, and you can look at, and the central portion is actually the unsaturated magnetic domain dominated regime, which is also can be seen quite nicely. And we have not focused exclusively on that, but in principle we can see. And so the idea is that you can do spectroscopy, you can study all of this locally, and we could measure it at different positions. If people have questions, I can look at it later, but in the interest of time, I'll focus more on the physics of why this is coming about. Similarly, we have been looking at magnetoacoustic coupling, where we had saw wave device. So this is a saw wave. So there's a piezo substrate, and you can drive saw waves in the substrate. And if you have a ferromagnet on it, you can actually modulate the magnetization, the anisotropy, and you can drive into FMR. But again, we can look at it using our spectroscopy technique, and we can try to do some local measurements of this phenomena. So these are again things I won't have time today, but these are things we have been doing. What I would want to focus, and let me try to keep track of time also, is we are looking at relaxometry, which is the spin relaxation based mechanism. So I'll try to tell you what is the basic mechanism. And so the basic idea is that we saw that there's no direct coupling. The resonances don't match, so you really can't do a coherent coupling. So the next logical thing for us to look was, is there incoherent coupling, which means that are we producing some magnetic noise at the NV resonance? Okay, so for that, to study that, we would have to look at what's called the T1, or the spin lifetime of this of these sensors, of these quantum sensors. And so that's what we are looking at here. And so the protocol for that is you apply this laser, as I said, you initialize the spins, and then after some time you apply and you read it out. Please understand that the same laser can both initialize and enable readout. So if you read out for a long time, then you basically initialize. So you have to do a good job, so it's a perturbative technique when you do the readout. So the readout pulses are short and the initializations are long. And so you can do the readout here, and that's what we did. And so you can vary this delay, and that's the delay that is being varied. And so you can initialize and you can watch what happens to the spin. And in our case, we can also apply the microwaves, but remember these microwaves are at FMR. We are not manipulating the NV themselves by the resonance. It's only the the ferromagnet that is being manipulated, FMR. So the NV resonance itself, we are not touching. And so when we do that as a function of delay, so this will give you the T1, or the effective lifetime. And so what you'll see that is the effective lifetime is changing when the microwaves are at FMR are being applied or not. And I should say that this happens only when we applied microwave at FMR. Even if we had microwave away from FMR, we didn't see this change. So we have confirmed that. So this is coming due to the microwaves which are at FMR, and you can see the change of spin lifetime. And this is basically what is changing this steady state, population of NV spins and giving us the signal. And so this is at the heart of it. And so this, now we need to understand that, but FMR itself is not an NV resonance. And to change spin lifetime, you need some fluctuating fields at the NV's resonance. So now we need to understand where are we getting these, fluctuating fields at NV's resonance. And so one thing we can also do is that we can use this to actually do a better spectroscopy and get rid of some of the excited state peaks and get a better signal. So what you can do is you can measure this difference signal here, and you can sort of map that out. And so when you do that, you can actually see the signals much nicer. You can see the FMR signal. And so you can get rid of some of the other artifacts coming from the excited state. And so you can prove that the excited state is not playing a part. It's only the ground state dynamics that are important for us, of the NV spin. To understand the physics more, we went to trying to understand the separation, and we first tried to understand what happens in the case when there is no microwave drive. That means the FMR. In fact, that goes back here, that when I showed you this decay here with microwaves off, this is very rapid. Typically, the NV spin lifetime, which is one of the main reasons people use, is in the order of millisecond. But here we're getting much shorter. So to understand that, we said first, let's understand that. And so we put this, basically we again have this diamond, which has a layer of NVs implanted inside it. And this is what was used previously also in the previous measurement I should have highlighted. So this is the NV that is, or diamond that is sitting with, we can control the depth of implantation. And so it has at certain region, it has NV centers. But we put a spacer layer in between. So we varied the spacing between the ferromagnet and the NV. Of course, it's quite exaggerated. The scale here is about 400 microns and it goes only to about 400 nanometers. So the angle is quite small here. And while I'm showing you a strip line for some of the measurements that we are doing, for these data, the strip line does not play a part. We are not applying any, we are not applying any microwaves. We are looking at the thermally excited magnons. Okay, we are looking at the noise from the thermally excited magnons. And so what we could do here, and you can see the nice fringing because the height is changing. And so you can see the optical micrograph of that. So we can look at the signal. And when we look at the signal, what we'll see, this is the inverse of the lifetime. This is the relaxation rate, the inverse of the lifetime, and there's in kilohertz. And this is what I was saying, that when you are far away from it, so if you're looking at the signal when you're far away from it, or when there's no permalloy rather, you will see that it is at a basically few kilohertz or in the millisecond range. And as you put permalloy and as you bring it closer and closer, you will see that the lifetime keeps changing and it becomes, the spins start to relax faster and faster the closer you get. And that's what we are seeing. Once again, the protocol is the same, that you have a reference signal, and so you initialize and then you can measure in between. Okay. So this delay here is what is important, how we are measuring that. And what we are seeing here is how this relaxation rate changed as a function of applied magnetic field. So as we applied a magnetic field, there's no microwaves, but just we are applying a magnetic field and we see a change of the spin lifetime. And we can sort of understand these lines here are coming from a fitting that we'll discuss. And I'm not going to get into too much math. I'm trying to keep it to a physical picture of what's happening in the interest of time again. And so what you're going to see here is there are two contributions. There is, of course, the intrinsic lifetime, but then there is the magnetic noise. And this magnetic noise is basically coming because of a dipole coupling between the thermally excited spin waves and what is the strength of them at the NV center. So this will be a function of both the wave vector of the spin waves and the separation between them, and some sort of spectral overlap between the NV resonance and the spin wave resonance. And so those are the two things that go into this. And based on that, and we can sort of compute this again, I'm not going into the math. We have the paper, we have written that, and we can discuss it later. But for now, what's more important to know is that the wave vector is what is playing a crucial part. So you can do this and we can fit it to within a scaling factor. We are still working on the scaling factor. It's a not so insignificant scaling factor, but we don't fully understand it. Maybe it's because of understanding the details of our material, pinning centers and stuff like that, or whether the spin waves give one Bohr magnetron per every spin wave, for every magnon, stuff like that. But we are able to nonetheless model it reasonably well. What is important to also notice is that this noise sort of starts going away when the FMR here, so this is the dispersion relationship, field versus frequency. This dispersion relationship, if you focus, this is the NV resonances. And when the FMR crosses all the NV branches, that is where this starts to die out. Okay. And that's sort of crucial to our understanding. And what is then happening is the fact that is happening is basically that we have these spin waves, and this is showing the dispersion relationship for the spin waves that can exist in the ferromagnet. So this is the dispersion of the thermally excited spin waves, and those depend on whether the K is parallel to the magnetization or perpendicular. I won't go into the details, that level of detail for now. What is more crucial is to understand that the high K spin waves gives you a larger magnetic field. And because you can imagine that if you have a uniformly magnetized plane, it does not give you a magnetic field at the center of the plane. Okay, you need to have inhomogeneity to get a stray field outside the plane. So this, so obviously uniformly magnetized is K equal to 0. So you need a non-K equal to 0, and higher the K, the more the variation and the more the stray field you get, and the bigger the effect. And that's why the spin wave, so you see a bigger effect, the noise is higher at low field. And this is again because the K, so this is typically a quadratic dependence that you get at K for parallel. And so that's how you plot. This is the uniform mode that you're driving, or there's the uniform mode. Later on, we'll be driving this. But what is resonant with the NV is the high K mode. And obviously, as you go higher and higher, that K is going to become smaller or smaller and smaller, which means that the magnetic field noise is going to become smaller. And eventually, of course, what happens is that the NV resonance becomes smaller than the, goes into the gap in the spin wave spectrum. And at that point, you don't see any effect, okay? So the NV goes into the gap of the spin wave spectrum, and that to first order should be the limit to which we can apply this technique. Once the NV goes into this, then that's pretty much it. And this should be the limit. And that's basically what I've told, that the higher spin K gives you this, and at low spin wave match the NV resonance, resulting in greater noise. And once the NV resonance move into the spin wave gap, yes, so I've already discussed these things. So we'll move on then. What we now, I'll say that was for the non-driven case. We'll also look at the driven case. In the driven case, what is happening is that we don't have directly the thermal magnons interacting. What we do is we have the uniform mode that we will excite. So this is going to be precessing, the uniform mode of magnetization of the ferromagnet precesses. But these are going to scatter off of spin wave magnons because that's their relaxation mechanisms. And when they sort of scatter off of them, some of them, or they are going to produce some spin waves, which are going to be resonant with the NV centers. And these are what are causing the magnetic noise and giving us the change of spin lifetime and ultimately enabling the spectroscopy that we saw. But a very nice thing here is that this gives us a sort of a tool to look at the relaxation of the NV, of the ferromagnets. And this has been experimentally a challenging thing to look at, the relaxation of the ferromagnets. And so this provides us a way to sort of interrogate that. And while we are sort of still working toward that, but it gives us a very nice promising tool to look at that. And so that's, so in the last part, I hope I have some time left. Yes, so let me try to quickly wrap this up. Is we have the regime of the large drive field. And this is what we call multi-magnon process. I would put this in quotations, the multi-magnon, because even here, there were multi-magnons. You were driving this spin wave while it's uniform mode, we say, but it's never uniform mode. You never have an infinite sample. It's some low K mode, spin wave mode, and you have thermal magnons and the other. So it's a multi-magnon process already. But I'll explain to you what I mean by multi-magnon in the next part. But here what we said is that once the resonance goes into the spin wave gap, we can't apply the technique. But what we saw here is this is another material, which is the zinc aluminum ferrite. I should have written down the material somewhere. Maybe it's in the next slide. But this is another ferrite, which is a nice narrow line width. And we were studying this. It's an insulating sample again. We see that what you see is that we can see the signal of the FMR well past the NV resonances. So there's the NV resonances, and we are seeing that. The other thing we also notice, and this we had been seeing from the first observation in YIG, we had tried to ignore it, but finally we said we'll look at it, is that the detected peak at higher powers, the NV detected peak, and the inductively detected peak, or what will be the uniform mode, are slightly separated, or are separated basically. And as you increase the power, the separation also increases. This, of course, gives us the idea that because it's dependent on the microwave power, that it's coming from some kind of nonlinear process. So we try to look at the nonlinear processes. And there's a famous one called as Soule second order spin wave instability, which comes, let me try to explain that quickly, is basically if you're driving as you're changing the frequency, you can imagine that if the frequency is far away from ferromagnetic resonance, nothing happens. But as it approaches resonance, close to the resonance, what will happen is the driven microwave can actually split into two high K magnons. And this is actually a more effective way of relaxing the spin wave mode. So these processes are quite effective. And so these happen regularly, but they have a threshold. And as you increase the power, they happen much more frequently or much more effectively. And so this leads to instability, which is what we are going to be looking at. And so these high K, so this is what we are looking, these parametrically excited non-zero spin wave modes. And as you increase the power, you can start to see them. And the rest of it, I've explained that you can go into the uniform mode, and eventually you can drive the NV, or the NV can go into where it is sitting in the gap in the spin wave regime. But let's quickly look at what happens while it is still not in the gap, but it is above that. And what we are seeing here is that the NV here is sitting not in the gap, but it is still in the spin wave spectrum. But you're seeing that we are driving and we are seeing this NV signal peak is separated from the ferromagnetic FMR peak that is inductively detected, and this is the uniform mode. And this 2B is actually, if you go, this is the Magnon mode, or this is where the 2K, 2 Magnon processes start to happen, and this gives rise to the instability. And we are much more sensitive to that. And so we are looking at that because these give you much more magnetic noise. And so this is the NV resonant, that, as I explained, thermal magnon and the driven magnon scattered, and you get this NV. And so when we say a single magnon, what I mean is that only one of this magnon is responsible for the noise at the NV resonance, and that is what is giving us that spectroscopy that I discussed earlier. What we can now look, in the interest of time, I'm going to skip the slide, but you can look at what happens as a function of power, and you'll see that the stability keeps moving, and we have verified this is what is expected, and this can be modeled by ferromagnetic resonance models and instability models. So we understand this well. What is interesting for us is this last slide here, is that we can extend the range, as I said, beyond the NV zone resonances by looking at higher when it is in the gap. So now this is the regime where the NV resonance is sitting in the spin wave gap. So nominally, I don't expect to see the spectroscopy signal. But what can happen is that you can still have this process by which a thermal magnon, the driven magnon, is scattering and producing two product magnons. And these two magnons can have a difference that is sort of matching. So if they have a difference that matches the NV resonance, so that can also give you a noise at the NV zone resonance. And that is how we are sort of able to see beyond the, when the NV is sitting in the spin wave gap, and we are able to extend the regime in which we can do this spectroscopy. And that's what we're looking. That's pretty much where we are. I should say that we are still trying to understand the line shape. It's still sort of something we are working on a bit, but at least we understand the key physics that is there. With that, I should come to the conclusions. And the basic idea is that these quantum relevant defect spins in diamond possess excellent properties to act as very good sensors at the nanoscale applications. I have shown you one particular application of detecting ferromagnetic dynamics. People have used it for many other things, for looking at paramagnetic spins. We have also done that. I have not discussed in this particular talk, but a lot of other people. I mean, that is the bread and butter so far. And people have looked at structures, static structures of not just the dynamics of ferromagnets, even for imaging the static structure and all of those, for doing temperature sensing in, let's say, single cells, for looking at electric fields, many things that people are using it for. In this particular talk, I have shown that we have demonstrated the relaxation-based modality for performing ferromagnetic spins. And actually, Kavita can tell me, maybe, I've been trying to find this. I know that people, of course, use relaxometry in conventional NMR, but I'm not sure if they actually do spectroscopy using that. And I've been trying to see if there is other places where people have used relaxometry for doing spectroscopy. And if somebody in the audience can tell me, that would be great. Then NVs we have developed, we can look at high K exchange magnon regime, which is sort of very interesting. Other tools may not be able to look at that. And so for us to be able to look at relaxation of ferromagnet, and especially in the high K, this exchange magnon regime is important. And I should point out, we could see this because the magnetization of that VTCNE was very small, which means the uniform mode sits very low compared to the NV. So the only branch that can touch the NV is going to be the high K branch, okay? So it comes because the VTCNE was a very low magnetization, where the uniform mode is much lower compared, or very small compared to the NV resonance. And so that's pretty much it. And we can also look at nonlinear processes, which allow us to both enhance the regime in which we're looking and also understanding these processes. Thank you.
Okay, thank you very much. Now this is the time for questions. So
yeah, I hope I didn't go too fast.
Yeah.
I know that the ferromagnet was, I'll wait for
questions. So there is a hand raised by Kavita. So Kavita.
Can I, let me see where I can find the chat.
Yeah, thanks, Aditi. Thank you, Praveen, for a very nice talk. Just a comment, really, because you asked about relaxometry in standard NMR spectroscopy. And there are really very interesting experiments done these days on using NMR relaxometry for different kinds of, studying diffusion of different kinds of materials. So we, generally, we can talk offline more about this, but definitely relaxometry has very important applications, and it's an upcoming technique in NMR.
And definitely. Okay, let's talk more offline, I would say. Okay, great. Thank you.
Yeah, so then the next question is by Harpreet. Can you unmute and he can ask directly to.
Hi, so thank you for a very nice talk. I have one question regarding the slide you have shown that when you are applying a no microwave, at that time that its signal is decaying very fast, and when you are applying the microwave, it's basically it's decaying slow. So I want to know the order, means so this red curve, and what is the order of red and blue? Means how fast red is decaying as compared to blue one. And another thing is that okay, so field is 50 Gauss here.
Yes. The field is 50 Gauss. This is for permalloy. And how fast it's decaying depends on the microwave power. So that's hard. And you can sort of see this is in microseconds here, right? So let's say you could have something like, and again, as I said, it could depend on the separation between the NV centers and the thing. So there could be many different things that can change this. So the intrinsic one or the effective lifetime without the microwaves, as we saw, could go from milliseconds to microseconds. Okay. So in this particular example, I'm showing, let's say it could be about a few microseconds to maybe 1 microsecond. But that again depends on how much microwave power I'm applying and what is the separation of the NV and the ferromagnet.
Okay, so but how you are applying RF to this NVs? You are using some wire or a coil or some resonance stripped?
Yes, we are applying a microwave strip, microstrip. That's what we are doing, and I think I can show you. Do we have? Yes. So basically, it's some configuration like this. So we have a microstrip here that we are applying. And once again, we are applying the resonance not to the NV itself, but to the ferromagnet. Okay. So we are driving only the FMR. We are not driving actually the NV. We are looking at the effect of the FMR on the NV. And so we are not resonantly manipulating the NV, but incoherently relaxing them.
Okay. Okay.
So,
thank you.
Okay. Yes.
Any other questions? Comments? I have a very naive question, actually. You talk about this NV center, these spins. So can you address or control this single spin in your system? Because that's probably from the perspective of quantum technology, it's important, right?
Definitely. I mean, that's something, of course, people do routinely. I mean, in these particular experiments, we were doing ensemble measurements. So yes, we can control them. That's how, let's say we are doing resonance, but eventually, yes, you do want to go to the single spin limit. And people have looked at even in these experiments, let's say Jacobi group with a former lab mate of mine who moved from our lab to there. And they have done excellent work using single spin, reproducing what we had and also sort of elucidating some of the mechanisms also. So there they were looking at single spins and they were doing coherent, they showed both coherent and incoherent mechanisms. And so you can manipulate, of course, and as you know that many people in the country now, I mean, Kasturi, and others, all of us are trying to set these experiments up. And so we are going, so hopefully sometime soon we'll start to do that.
Okay, thank you.
Mm-hmm.
So any other question? I do not see any raised hand. You can also ask probably. If you cannot raise hand, unmute yourself and can ask. Okay, if not, then let's thank Vidya once more. Thank you very much for your nice talk. So we go to the next talk, and the next talk is by Durga Dasari. So Durga, are you around?
Yeah, I'm around. Can you hear me?
Yeah, we can hear you. So can you share your screen?
Yeah.
I can introduce the meanwhile. Okay, so Durga is a theory group leader at Physics Institute, University of Stuttgart, Germany. He did his PhD in at IIT Kanpur with Professor V. Subramaniam. His postdocs are at Weizmann Institute of Science, Israel, Aarhus University, Denmark, Max Planck Institute for Solid State Research, Germany. And today he will be talking about exploring new capabilities for quantum technologies through solid state spin defects. So yes, we can see your screen.
Yes.
So
thank you for the kind introduction, and I would also like to thank the organizers for the opportunity to give the talk here. So what I would do now is I'll catch up on what Vijay was talking before, but I will try to give a much more broader view, and also in connection to what Professor Sen was asking, like how the manipulation of a single NV could be done. So I'll be talking about that, because now with NV centers, this is almost like I'll say in competition with any of the current technologies for quantum computing. For example, in our lab, we have something like a 5-qubit IBM like a machine, where only mostly students and within the group, we share this thing. So the field is much more matured now in lots of respects, and I will share some quick view, and also what further one can think in connection to lots of topics that were discussed in the last previous days in this conference. So as the picture here, what it shows is a small nanodiamond that is attached to an optical fiber, just like as Vijay was pointing. So you shine it with green, and you see fluorescence in red. So I'll talk about like on 4 topics, which are more related to quantum state engineering, how we do with measurements, and some advancements in spin polarization techniques, and also connection to quantum thermodynamics. And I'll show you our recent works on trying to create artificial spin networks, which could be used for quantum simulations. And later on, I'll finally also discuss like how one could also deal with this computationally hard problems using a single quantum sensors. So I'm a theory group leader here in an experimental group, which has pioneered the research of NV centers and other solid state defects in diamond. So being a part of the experimental group, it would be, it's always easy, and also to be close to reality with your theory, and always get a chance to get some of your ideas worked out in the experiments. And I'll also show instances in this talk where I myself became an experimentalist. So solid state spin defects, like how do we simply understand that? Maybe for the students in the what you see is like, normally these are the point defects that we all study in solid state physics. right? But these point defects, if you think of them in some semiconducting materials, then these would give rise to energy states within the band gap. And for the right combination of energetics, when you could form some structure like this, like the excited ground and a metastable state, then these start becoming useful, right? And now we want to associate further a spin degree of freedom to the excited and ground state, and then that makes almost exactly like a single atom kind of a thing. So these materials, like you have this single energy states in the band gap, and these would give rise to single photons. And now we have lots of single photon sources. You just get them for free, like lots of these 2D material things, like you can just order for free and you have single photons for free. But the crucial thing is how Fourier transform limited are these photons that are emerging from these photon sources, and that determines how well they can be used, for example, in photonic based quantum computing protocols and so on. Right? So, and just to I'll quickly remind you that we are not new of defects, because this is what we have been doing since the age of classical computers, that we have been doping silicon crystals with N-type or P-type. And so in that sense, these two are like now we are exploring now the quantum properties of one such defects, which are formed in different materials and in the right energy conditions. And so the defects, like I'll be talking about NV centers and also some of the defects in silicon carbide. So NV centers, as Vijay was already pointing out, like, so these are the defects which give rise to color. And it's not only NV nowadays, it's the silicon vacancy and germanium vacancy centers are also being quite actively explored. But the best part of NV center is like it has a very good ground state spin properties, making it open to a large number of quantum magnetometry applications. Whereas this other silicon vacancy and so on, they're having quite good optical properties with lots of emission in the zero phonon line. So that may brings them more attractive to exploring quantum optics with these defects. And there are also other defects, for example, like defects in 2D materials, hexagonal boride. There are this transitional metal dichalcogenides. There's a silicon carbide, and there is rare earth ions. So there is a whole slew of solid-state defects which could have good optical properties, and at the same time, when mixed with a good spin properties, they make a very good candidate for lots of quantum systems in study. So if one wants to look into a nice review article about how one could interface spins to optics, then I would refer for this. So this is a kind of a broader picture of what one is interested with these kinds of defects, right? So sensing has been one of the, I'll say, the workhorse topics for these solid state defects because of their extremely good spin properties. And at the same time, because of the ability to manipulate and control the single NV centers to a very high degree, you can realize a large set of possible quantum algorithms with them. So right now, the gate fidelities that we have in the lab are like for single and C0 gates, we almost have like 99% fidelity, right? And then you can implement so we implemented almost all the known algorithms and also this randomized benchmarking circuits and so on. So in that sense, one could do a lot more with these centers because of their long spin coherence times. And in terms of communications, I'll say this is far ahead than what other solid state systems are promising, because right now with these NV centers, one has already realized a quantum repeater network with 2 nodes. And there's a lot of effort going on here in Europe to really to go to a much more multi-node quantum repeater networks. And there's this other aspects of many body physics that one could also explore with this, because what you have is anomaly in the other than the single NV centers, what you also have is this ensemble NV centers, where these are like kind of a million dipolar coupled spins, and which you can address them coherently, you can initialize them, so on, and then you can study many body localization and other thermalization phenomena within this. And also one could realize room temperature quantum simulators and also the other dissipative simulators, which I'll not talk today. So this is like the next three boxes are more like the newer directions of what the field is going to. So recently there's a lot of been research in exploring the measurements, the quantum measurement, strong and weak measurements with these systems to understand more how they bring in new control into this whole game of coherent control, and how they can also further address computationally hard problems, and how machine learning algorithms can be, I'll say, actively invoked into some of these. So on the technology side, I will show this thing where in our lab, so this is almost like a laser table brought down to the size of a 5 rupee coin, right? So we have advanced to such a degree. So this is the one technology which is going to go to the industry much faster than any other quantum technology, because now already we have lots of collaboration with industry partners who are already using these to make extremely sensitive sensors. Right? For example, this sensor here has a sub nanotesla per square hertz sensitivity already. And as I was pointing, that now you could do NMR with chemical shift resolution. So you really are probing like few hundred spins instead of like 10 to the 6 or 10 to the 7 spins to get a signal. And you're doing this with very high resolution so that you could get the chemical information of the molecules that you deposit on top of the diamond surface. And just an extension and the current advancements of the imaging of ferromagnetic domains that which I was showing. So 2D ferromagnetic materials, these have recently got huge attention in the community, because you could make racetrack memories with these. And so recently we have imaged these 2D ferromagnetic materials where, for example, like chromium bromide. And what we see is that upon reversing this is like the domain wall structure of a small piece, 3 layers, right? Because it's a 2D material. So you can really get magnetization layer by layer. And what we see is like as you switch on, reverse the magnetization, you could read that with NV. So at the end, the technology would be that, that there will be like a scanning probe with a NV, with a diamond tip in which there is an NV center. And that is, for example, reading out the magnetization from the sample. That's like 1 and 0s. And that is going back like a normal readout device, right? So the normal hard disks, the way it is, like there are the magnetic domains, which a small magnetic tip is catching up, indicating a small change in current. So now that would be the same, but now with this 2D material. So in that sense, this is truly going into quite some technological applications. And further, these are to get this high sensitive readouts, like for brain imaging and so on. So the structures were going on. And for quantum computing, you're asking like now you could make So normally in the labs, we have like most of the setups we have a nuclear spin register, which is like 6 to 7 spins. But recently it was shown that by a special doping technique, while growing the diamond, that increases the carbon-13 atoms within the crystal, you could make registers of the size of 10 to 30 qubits. So this means that normally we have in the labs a quantum volume. This is like the new parameter that is set by the IBM guys to say like how many useful qubits do you have in your system. So normally in the lab we have like 16 quantum volume, and the whole push from the community is like who can go fast to 1 million. You know? So with these new growth techniques, we are hopeful that in the next few years we could really scale up these to get like a very high qubit number in the registers. Further, in terms of communication, which there were already quite some talks in the last 2 days, so one could realize repeater networks, and these activities mainly pursued by the Delft group. It's already you can use these NV centers as the quantum nodes, which are required, for example, for this long distance quantum communication, right, where the quantum information is also processed at a given node, where active quantum error correction protocols are implemented, right? You can distill entanglement, and so there's lots of room also towards this quantum communications that one could achieve with these NV centers. But today, what I'll do is I will concentrate on like a different, the new topics that we have been looking into over the past year. So this is like a quick review of NV centers in Diamond. So these are like, you can have single defects, right? And these are, so in a sense that they are single emitters of photons. You can well initialize them, as Vijay is showing, like without any special control. For free, you get something like 70 to 80% of polarization. But then with further improvements in charge state control and so on, you can get initialization even at room temperature up to like 99%, and at low temperatures, it's definitely 100%. And these can have extremely long lifetimes, right, of the order of milliseconds. And at low temperatures, it can extend quite a bit even. So we have a well-resolved optical spectrum. So normally at room temperature, like the energy level picture that Vijay is showing in his previous talk, that you don't have resolved spectrum in room temperature. So you only see overall fluorescence difference if it is either in the 0 state or in the ±1 state, the bright and dark state he was referring to. But here you have this resolved spectrum, which means that you can go from one spin state exactly to the other spin state in the excited state and so on. So it just becomes like an atom, where you can address a given hyperfine level with high fidelity. And further, because of its high sensitive to the environment, it is very easy to couple to other spins, phonons, photons, magnons, like the spin waves that was shown in the previous talk. So in terms of dynamics, so what is it that is determining the dynamics is the like the central spin model, right? So where you have this electron spin, and then there are this surrounding nuclear spins. So most of the techniques, like you just take from NMR and EPR, and the pulse control and so on. So that's what we have. So that's the central spin in V, and then you have carbon-13 nuclear spins spread around. And this is typically like we see like 6 to 7 spins within a decent coupling up to like something like 10 kilohertz. And beyond that, it's a bath. So you normally don't see any more resolved nuclear spins. So till 2 or 3 layers, you can see resolved nuclear spins that are going to be our register spins. And as I was saying, like at low temperatures, you can have this resolved spectrum, which means that you can address optically only a single spin state. So you have a single shorted out. So what you see is like if you are in 0 and you shine light, then you get a photon out. If you are in the other states, you don't get a photon out because E and A are separated by more than a gigahertz. So in that sense, you can projectively collapse the quantum state into one of the spin states at low temperatures. And we are going to use this feature to do some kind of a quantum state engineering of a spin bath, which I'm going to talk in the next few slides. So for a good review on NV-based physics, you could refer to this. So the kind of control that I'm going to talk will be normally like there are 2 ways, right? So this is the direct access where this is a normal circuit-based approach. And then there is this indirect access, which is the ancillary based. So where the ancillary holds the coupling to its register spins. So these qubits of the register themselves not directly interacting, they're only interacting via the ancillary spin. And now by manipulating the ancillary spin and by measuring it in the right measurement basis, you can do a variety of quantum gates among these non-interacting register spins. So first here I'll talk about this measurement-based control. So when we talk about measurements and how do they control the field, so we need to quickly remind you of the noble work of Weinlein and Harosh. Right? So in their experiments, what do they have? They have the Rydberg atoms, which are prepared in a superposition, passing through the cavity. They come out and then you measure. Right? So it's like you create a superposition and the tau, they interact with the microwave cavity, and then they project back to the energy basis, you measure. And what one typically observes are these quantum jumps. Like you are in excited or the ground state, and that you see explicitly. And what happens because of these collapses of these atoms is that with sequential collapses, slowly the cavity field also goes into some interesting states. So one can generate fog states, cat states, and so on, depending upon the collapse of the atom that has interacted already with the cavity. So for example, here you see that these measurements are kind of a quantum state engineering the cavity field. And if you want to implement the same for our system, what do we do? So what we can do is we can already initialize that like you have like a single atom in, which you create a superposition. Now it will interact with a nuclear spin bath for a time tau, get back and measure it. Okay. And now instead of having this multiple atoms, what we do is we just repeat this. That is, we again reinitialize the NV center and repeat this protocol. So reinitialize. So here n is equal to 100 atoms is equal to doing n is equal to 100 measurements. So that's what we have. Now to start with, it's like we consider these ground state structure, spin structure of the NV. And now if we do the same trick, so what we do is now when we create the superposition, means we create a superposition between plus and minus 1, right? If it is in the plus combination, then the next pi half pulse will bring it back to 0, else it doesn't bring it back to 0. So which means that when you now shine the light after this interaction, depending upon if you came back or not, you get a photon or no photon. And now if you do the same experiment here, you just see a similar jump like behavior. Quantum jumps. Right? So this is what is happening. First we polarize, then you prepare this superposition by this microwave. Then you evolve, and during the evolution, it attains a phase which is coming due to the interaction with the nuclear spin bath. And then the final state, again, you do this by half pulse, and then you go back to your zero. And so in terms of quantum circuit, this is how it's going to look like. This is what the system that I start with. I have a single NV center, which I am selectively projecting onto a given spin state. And because of this, I am modifying the quantum state of all the surrounding spins. And that's what is exactly depicted in this picture here, right? So the interaction is only between the NV and these spins. These spins don't have direct interactions because these are like nuclear spins, are weakly interaction, and also these are a bit spatially spread out, which further decreases their dipolar couplings. So effectively, there's no coupling between these bath spins. So what is the non-triviality that we get? Right, so before that, I'll quickly, briefly tell you the theoretical prescription of what we understand by repetitive measurements. So repetitive measurements is not something that's being done for the first time, right? So it has been done like for more than 50 or 60 years. And also there are many protocols, which we also heard within this conference itself on repetitive selective measurements in each of the protocols. So what do we have is a simple scenario. Here is the ancillary system. Here is the system of interest B, and there's interaction between A and B. Now we start with the initial state. More or less, the ancillary is the one which is always pure state. It's well initialized, whereas the B is in the thermal state, like fully mixed state. And now what we do is we do a measurement on A in a kind of a chosen basis. And how do we, so A, we are collapsing it with this measurement. So it's a strong measurement on A, but because of this interaction, that could translate into some kind of a weak measurement on B. And now if you ask what is happening to the state of B after these measurements, so because each measurement is going to project also the total state in a way that only the measurement of A in a particular state psi A is seen. So in that sense, the state of B is also slightly projected out. Okay, and then that is determined by this. And now what we see is now the effective action on the bath or the B spin set of spins, the B system, is a non-unitary. Right? So sorry, this is a V of tau. It's non-unitary because of the projection of A. The effective operation e to the power of this IHT with the projection of A gives rise to a effect operator which is no more unitary. And because of this non-unitary nature, what you see is like measurements actually start to polarize also the system B. And the probability with which a certain measurement is successful is given by just the overlap, this P. And what are the systems that we are going to look into, and what gets affected because of these protocols are, for example, determined by the cooperativity, right? So you want the system B to have a much more longer lifetime so that it can take into account all the effects that A is imposing on it by its measurements. And you want also the coherence time of A to be larger so that within this time tau, its coherence is maintained. And now it has become now an optimization problem where you have to optimize the time tau between measurements and the kind of control that you would do on the ancillary spin and the measurement basis that you would like to choose for A, so as to obtain the right state that you want for the B system at the end of the sequential measurements. So one could do this. So we started with the case where a general scenario we always have in the labs, that is a central spin coupled to let's say some external spins on the surface of the diamonds. Okay, so if one does a normal DNP like a protocol where you transfer your electron polarization to the nuclear spins, for example. So that is a normal polarization that you get. But now, if you do the same, but not by doing like a Hartmann-Hahn nuclear transfer, but let's say you're doing the selective measurements on this spin. So then something interesting happens, that these spins polarize, but they polarize into some special states where they all get paired into singlets. So this is the state. Effectively, what you ask is, in the n-qubit Hilbert space, what is that state which is least decoupled to my central spin for a given Hamiltonian? And that turns out to be a singlet paired state. And further, we also applied for this for a spin mechanical system. Like if you want to cool down a mechanical oscillator using the spin, using this method, okay, it still works. And we could find out an exact closed form analytical solution for this problem, where we bring an initial thermal state either to the ground state or to the squeeze state, depending upon the choice of the measurement time tau or the measurement basis. And just like recently, the small bachelor thesis, just to show that there is a learning feature, and when you apply machine learning algorithm, it will try to show many solutions, of which the human found solution, for example, in this works, is a part of it. So now I switch gears and I go to the next topic, where I'll tell about, still I'll continue my discussion on polarizing the path, but now I do the polarization in a more conventional way. Oh, sorry. No, I'll talk about now experiments about what I was showing you theoretically. So in the experiments, this is what I have. There is a qubit which is dephasing because of interaction with the path, right? And if you see that there is a certain time tau where it is completely dephased. So here the qubit is just like a classical coin. So now at this time scale, if I do like 4 measurements, right? 4 measurements means I can have 16 possible measurement output, where all of them are 0, 0, 0, 1, and so on. So because if you think this as a time where it has completely dephased, then what you expect is a flat distribution classically. That is, all the strings are equally probable. But what we see in experiments is a completely different scenario. You see that certain measurement results are more probable compared to the others, and you see a different kind of distribution as opposed to a flat line. So if you do for even larger number of measurements, what you see is that suddenly you see something like a quantum random walk like behavior in the measurement statistics, and compared to the normal classical expectation that it has to be a Gaussian. So this was a surprise. So what we thought is, like, maybe we try to understand it in a reverse way. That is, if you start, so in the previous case, we are trying to infer what is happening in the system depending upon the measurement statistics. Now what we say is, okay, now let us say we have a classical random walk, and let's say we are doing measurements on it. So now classical random walk will give rise to this flat distribution as expected. And if you start with a quantum random walk and you ask now that at every instant, the guy is doing a measurement either into the plus or minus possibilities in the superposition. And there you see that this walk gives rise to a measurement statistics, which exactly mimics what we see in the experiments. So in fact, there is some kind of a quantum random walk happening in the Hilbert space of the bath. And to also further see that, what we did is we just simulated the whole problem, taking like a large number of spins, 20 spins in the bath, and we simulated it. And this is what's happening. Every measurement, depending upon the measurement result, is making the bath evolve into 2 possible states. Right? And that is how the random walk is coming in. And then what we see is also the polarization of the end states that you get, for example, in these multiple measurements, also seem to have different polarization. So in that sense, what's happening is every measurement is polarizing the bath or giving rise to entropy, which is different for different measurement results. So, and further, what we saw is like, why is that one, is there a experimental signature where the bath is really polarizing to this? Because we can't do quantum state tomography on this large unknown bath. So is there a indirect way to learn if there is some polarization happening? So polarization happening means that as the bath is going to asymptotic state, so then the a certain measurement result no more changes, because now the bath has completely become an eigenstate of the interaction Hamiltonian. So as if there is no interaction happening. So if you start with a superposition state, you end with a superposition state. And we see that exactly here, that with increasing number of measurements, we ask, what is the probability given that n measurements are 0? What is the probability that the n+1 measurement is also 0? And that we see that it's actually saturating, indicating that the bath is actually collapsing to a certain state. So all is good in terms of what we see, understand the phenomena, but does it have any implication? So for example, if you do a measurement like this, correlated measurement, that is, if you do 4 measurements, wait for a time t, and again redo the 4 measurements. Now you ask, how correlated are these 2 measurements? And what we saw is surprisingly that the spin lifetime here in this time t has improved by 6 orders. So the 6 orders is like, this is like huge number, because no matter how good an optimal control you do, you can never bring the spin lifetime of the V2 from like a T2 star from microsecond to second. Means you have to do like few thousands and 10,000s of pi pulses in CPMG or something like that to really make a very sharp filter function. But here you get this, and you get this in a way that you have actually modified the bath itself. Means you have modified the whole spectrum of the bath itself, that we see before and after. If one does this ODMR, this magnetic resonance scan, what you see is that it's completely different before and after. So you squeeze the ODMR, and this change is permanent, because as long as the T1 lifetime of the bath, this change is permanent, which means that you do these measurements, and then you suddenly get a new set of qubits with a renewed spin lifetimes, and from there on you do the quantum circuit. Right? So normally in any optimal control, you need to keep the control on, but here you're permanently changing the state of the bath to something which does not couple to your central spin. So in that sense, this is completely new. Also, and also for us, this was like a bit of a surprise the way it came. And now I'll talk about other polarization techniques, and try to make connections with the quantum thermodynamics. So normal way of doing spin polarization technique, which has been like the equilibrium technique, the Hartmann-Hahn transfer, is like there are 2 systems, A and B. A, B are coupled. Now A is in contact with some kind of a heat bath. In time, A equilibrates with this heat bath, and slowly, because B is coupled to this A, it also equilibrates. But then later on in NMR, people came with this novel concept of algorithmic cooling, where they said that is it possible that one could extract more polarization? Means, can you cool the B to a temperature much lower than the temperature of the bath itself? What they asked is there a way that one could manipulate A, which is in coupling to this heat bath, so that B can get more polarization, or B can be made go to a much more lower temperature by manipulating. So this is this heat bath algorithmic cooling technique that was introduced in NMR. And though it was like introduced and showed in principle demonstrations, so its asymptotic limits were never proved. So we tried to do that because now we have a much controlled system. So now exactly we have this A and B, and now we manipulate this coupling in a way that we get this. So how we manipulate the coupling between A and B? So there was a circuit proposed that, for example, for 3 qubits, you see these are the 2 reset qubits which are in coupling to the bath. And this is the computational qubit which is trying to extract more polarization than what these spins had. So a simple circuit like this, a more like a Toffoli kind of a thing, would increase the polarization of the computational qubit to twice the amount than what this initial reset qubits had. So in that sense, this the asymptotic limits which were derived, for example, in this early papers, tries to tell, like, connects how much cooling can this get depending on this. So what we try to do is like we try to reach this asymptotic limit, and experimentally we could verify this that indeed this is true, and one could get the expected increase in polarization. And for example, the theory calculation, and for 1 point I'm just showing you these values. And you can also now think this as an efficient refrigerator. And for this, if we calculate the efficiency, the Carnot efficiency, it's around between 80 and 90%. There's one other aspect which was also like but slightly touched in the conference, is like, how does entanglement, for example, do something different than what we know in equilibrium thermodynamics? So normally what we have is a scenario where heat flows from hot to cold. But in the case where if the initial state between the system and bath have quantum correlations, this heat flow could be reversed. So that was recently shown. Also in an NMR experiment. So we wanted to, and there it was because of this ensemble system. So there one couldn't really talk about entanglement. So people were trying to characterize only in terms of correlation. And because we now have a very good control system, we thought maybe let's go ahead and do the experiment with few spins, calculate the concurrence, and see if it holds. So indeed it holds. So if you start with the initial system, which is in a certain, so the initial states A and B are at 2 different temperatures. So one is cold and one is hot. And then there is some correlation. Then what you see is at the end of the experiment, the cold becomes more colder, hot becomes more hotter at the expense of by consuming the correlation. So the concurrence here, for example, in this state is 0. So if one finds, like, with increasing concurrence, how does this temperature change? How much cold does the cold bath get, and how much hot does the hot bath get? So they seem to increase with each other. So in this sense, that quantum correlations help to reverse the heat flow. Maybe I have to rush. So maybe I'll skip this talk. So there's one other activity that's going on with us where we try to do spin mechanics, and based on that to try to make heat engines where we try to, for example, transfer heat between 2 spins which are coupled via oscillators and so on and so forth. So I'll skip this part here. And the other directions where we were going is to create this artificial spin networks, so that one could do one could realize some kind of a spin Hamiltonian, and in that sense we simulate a spin system. So we've been successful, for example, to make structures using molecular spins. So these are like spin labels attached to polyproline polymers. So and we could, like, make the NV coupled to those spins and also read their local environment and so on. And these are the further directions you're taking, like how to, for example, realize a 1D chain and also look at this phase transition in it and so on. And also recently, this other possibility is this endofullerenes, also to make such artificial networks. Quickly then to the spin problem. So so what we started to look at is like, okay, you have now a good sensor who could resolve the changes that are happening in the environment with such a high precision and high sensitivity. Can we use this feature to do something more? So we said like, okay, let's look at this graph pairing problem. So as you know, like if one wants to find out the perfect matchings of a graph, so this is a hash-tree problem in graph theory. So perfect matchings in the sense that if you take a 2D lattice, so you only find one partner per point, per edge. So those are the perfect matchings, and generally finding those is a hard problem. So because we can have surface spins, and then we can start with different initial states. As I was showing before with the measurement based, you can start with nice singlet pairing of all of these. So in case if you start with a scenario like this, what one finds is that indeed one can resolve, for example, the pairing statistics. For example, in the case of 4 edges like of a graph. So you have, let's say, these 3 independent possibilities of perfect matchings, and your sensor can actually resolve all of these 3. So in fact, when we run the simulation for a large number of large size graphs, we could recover exactly the statistics that one would get from this thing. So in that sense, using having good sensor could also help us to do some other computational problems which are hard, other than this normal the boson sampling problems and so on. Right? So I'll leave this on. And this is one other problem. Maybe I'll skip this thing. Maybe I think I don't have time. And there is this other system which, because for audience, I want to say, because already Harpreet was talking about the 6H silicon carbide. So there are these other 4H silicon carbide systems where the silicon vacancies in these have extremely good properties, in the sense that we did this low temperature experiments and so on to see 2 well resolved lines corresponding to 2 different spin transitions. And with this, one can do a lots of nice things. So we did homomodel on these indistinguishable photons, and we can think about generating photon assisted spin entanglement or spin assisted photon cluster state generation and so on. There are lots of quite nice properties, and we reported this recently in this. So with that, I'll end my talk here. And this is the group, and Professor Akrup, he's the director of the institute, and all of us here. So I would like to really highlight upon the future quantum technologies that are going to be empowered by the solid state defects in all areas of the information. Thank you.
Yeah, thank you very much for your nice talk. So now it's time for quick questions, because we are probably running out of time.
Yeah, sure.
So, yeah, so there is a question from Shashwat. Could you please ask?
Yeah. Hi, Durga. Thank you very much for this such nice talk. I was wondering. So my question is from the initial part of your talk. How did you simulate the dynamic nuclear polarization? Was it with the master equation or numerically? I mean,
so because this dynamic nuclear polarization for DNP is like for Hartmann-Hahn, for most of the systems, it's analytically solvable. So you could also do numerically if you take into account all these finite lifetimes of these things. But for our case, because the lifetimes are so long, you can just do it like the ideal case calculation, and it still fits the experimental.
And what is T2 star for your system normally?
Normally, it's like T2 star will be like in microseconds, and T2 will be in milliseconds. Yeah.
Yeah, I see. Thank you very much.
Thanks, yeah.
Okay, so next is by Harpreet. Harpreet, could you please ask?
Yeah, thank you, Durga, for very nice talk. I have one quick question on your slide number 15. That you said that you apply some CPMG pulses and then you don't need to apply. So could you comment something more about the environment? How this CPMG on the system will affect the environment?
Sure. Yeah.
Because
So this
generally we consider the bath have a very means very quickly reset. So here the bath is not resetting.
Yeah. So sorry, this is not CPMG. This is actually these pipe pulses are the pipe pulses for this measurement based protocol that I was talking. So these are CPMG pulses. So these are these pipe pulses.
Okay. So it also form the similar some filter function. So
exactly. Yeah. But this filter function now is not in the frequency space, but it is actually in the population basis.
Okay.
So normal CPMG, the filter function will just like filter out this unwanted couplings. But here the filter function is directly on the density matrix. So it only chooses certain states to appear in the density matrix and suppresses all of them. So in that sense, the function is completely different. Yeah.
Okay, so maybe in a chat, if you send me the link, I'm really interested in that to read more.
Okay, sure. Yeah, so this is actually different.
Thank you.
Yeah, so thank you, Durga, for your nice talk. So we are running out of time. I see that there will be another talk in this session. So Sandeep, is Isaac?
Yes, I think he has joined. I saw him some time back. Yeah.
Okay. So I thought that, okay. So, okay. So are you online, Isaac?
Hello, can you hear me?
Yeah, I can hear you.
Hello? Yes, I'm online, thanks. Yeah.
Okay. So is it Isaac? Can you share your screen?
Okay, yeah, perfect. Yeah. I'll do that now.
Okay, so Isaac Nape is currently a final year PhD student at with Structured Light Laboratory in the School of Physics based at the University of Witwatersrand, South Africa. And his research interests include tailoring light's transfer spatial structure for applications in high dimensional quantum information and communication. He has contributed to several works that include high-dimensional quantum secret sharing, multi-dimensional state transfer through optical fibers, high-dimensional quantum key distribution, and spatial mode transfer through turbulence. And his main focus is in exploiting multiple degrees of freedom of photons to realize high-dimensional state encoding through various media. And today he will be talking about tailoring structured light fields for single photon quantum secret sharing. So Isaac, please go ahead. And since we are running out of time, please be on time. We should finish by 7:40, I think.
Okay, great. All right. I'd just like to confirm, can everyone see my screen?
Yeah, I can see the screen. I think everyone is.
Okay, perfect. Yeah, thank you so much for giving me the opportunity to present. And I do sincerely apologize to everyone for missing my time. So I hope I keep you guys excited and that you enjoy my talk. So as the speaker said, my name is Isaac Nape. I'm from the Structured Light Lab here in South Africa. And today I'll be presenting on tailoring structured photons for quantum secret sharing. Okay, so for most of you who don't know, South Africa is like right at the bottom of the African continent, and I'm currently sitting here in Johannesburg, which is situated in Gauteng, which is one of the well-known provinces. And in fact, most of you guys might know Johannesburg from the Soccer World Cup. We had one of the nicest stadiums built here. So this is a picture of my university, and the School of Physics is actually situated on the left of this building. This is called the Great Hall. So to get straight into the talk, we currently know that like a lot of companies, for example, Google, D-Wave, IBM, have invested a lot of resources into realizing quantum computers, and most of them have actually built them and they are currently running. Some of these companies have been increasing the number of qubits that they have in their systems, and this means that actually the future of quantum computing is very close. And this might be bad for systems where encryption, for example, relies on hard to solve computational problems. And as quantum computers are well known for their computational speed up, our current encryption systems are actually at risk. So how do we defend ourselves against it? Well, one proposition has been to use quantum itself against quantum. So use quantum secure encryption or quantum cryptography against quantum computing, as this provides provably secure security based on fundamental principles of quantum mechanics, like the fact that you can't clone quantum information, and neither can you, you can't clone quantum information, and you also have the uncertainty principle, which means that if you measure some particle state using a measurement analyzer that is incompatible, you don't really get information out, okay? Now, the most well-known quantum encryption protocols are with 2 photons, and the 2 photon case usually uses correlations in the form of entanglement, where you have Alice and Bob who want to share some secret information. And so what they do is they both have entangled photons, they perform sequential measurements on them, and based on the correlations that they get, they can then share classical information which they can use to build a key. Now, you can also have an equivalent system where instead of using entangled correlations, you now use a prepare and measure system. So now if you look at this system here, imagine that the photon that's detected here travels back in time, right? And Bob encodes information on it, sends it to the crystal, which we would maybe replace with a mirror, and then send to Alice, okay? Or vice versa. Alice prepares, it gets sent to Bob. The detection probabilities in this case and in this case, where you have Alice sending the photon to Bob, are actually equivalent. And so it has been shown that these 2 ways of transferring secret keys are actually equivalent. So they are very much identical. Now, in this prepare and measure case, which was actually the first to be developed by Burnett and Brazard, then only this came later. In this case, what happens is, like I said, you have Alice preparing a photon, which she sends to the channel, Bob measures. But the key here is that they first agree on an encoding basis, okay? 2 bases to be precise. The first basis forms the standard basis, and then the second basis is mutually unbiased to this first one. That just means that if I have a photon encoded maybe in a state that comes from this basis, and I try to perform a measurement with an analyzer that projects onto this basis, I cannot get any information out. So what happens is, what Alice and Bob, using states from these 2 bases, they would randomly select different states which they would encode on their photons. Alice would transmit, Bob would measure, and then at the end, they would announce their basis measurement. Alice would announce the basis she used to encode her information. Bob would announce the basis he used to detect the photons. And where the bases agree, they can then keep that information, and where the bases do not agree, they then discard. The remaining bits where the measurements were correlated in terms of their basis selections would then build up the desired key. So the point I'm trying to make here is that you can actually move from a case where you're using prepare and measure schemes to a case where you're using entanglement-based measurement schemes. And it's probably far easier to use single photons than to use entangled photons due to, for example, in the entanglement case, most of the entanglement sources are very inefficient. For example, SPDC probably has an efficiency of about 10 to the minus 6. So for every million photons that you produce, you only get one photon out of it. And it's much better to use single photons, okay? Now, the case I've explained is when you have two parties trying to share information. But what happens if we have more than two parties, say 3 people, Alice, Bob, and Charlie, okay? In this case, if they were to use entangled correlations, they would need to have access to a multi-particle entangled state, okay? And such a state is known as a GHZ state, okay? And these states are also quite difficult to generate. However, people are still working on encryption protocols that enable you to distribute information to multiple participants by exploiting the correlations between them. So how does that work? Well, you would start with this state, okay, which is produced from some GHZ source. You have the photons distributed to the parties, Alice, Bob, and Charlie. What happens is Alice, Bob, and Charlie each have access to an apparatus that allows them to control a parameter which we shall call alpha, beta, gamma, and these are just unitaries that can be enacted on the photons, okay? What happens is each of them would, for a single run, for example, choose alpha, beta, and gamma, okay? And then in the end, each one would perform a measurement and they would get either a click on the minus detector or the plus detector, okay? This can be mapped onto like binary states of zeros and ones. And depending on their selections of alpha and beta, okay, the detection probability is given by this here, where ijk is -1 or +1, and alpha, beta, gamma are just these phases that they each selected, okay? For a single run, they have to announce which alpha they selected, and then calculate the correlation value. And in the case where their P is 1, then that's considered a valid session, okay? Now, they would do this sequentially and then in the end build a key in the same way that you would have done if you were using QKD. Okay, except this time they choose whether to keep or discard information based on this parameter P. Now, the problem with that protocol, or the problem with using multiple photon entangled states, is that there's an issue with scalability, okay? The more photons you have in your system, the more noise you have. And also, it's very difficult to generate multi-photon entangled states. So I guess maybe the best solution is to again consider perhaps maybe using single photons. And that is the direction that we looked into, okay? Now, how would we achieve this? Now, imagine that I first begin with a single photon, which I could herald from an entangled pair, okay? I would only use one of these. I would prepare one of those photons into this initial state X, okay, with 0 and 1 at my information basis states, and I would prepare the superposition and then transmit it through to my different participants. Okay, C1, C2, C3 would, for example, be Alice, Bob, and Charlie. And here, each of these participants have access to your unitary, okay, which is very similar to the unitaries that Alice and Bob and Charlie had here. They would then apply these unitaries to their photons, right? And at the end of the transmission, the last person would then have the final state, which is given by this here, okay? Which is just, again, this state, but you have this relative phase between your eigenstates here, which result from each participant applying this unitary. And the values for their unitary, or the orientations that are allowed to select, to choose from, are given by 0, pi, pi over 2, and 3 pi over 2. Okay, we will discuss precisely what the significance of these base values are. Okay, so let's say now they have transmitted their photons, then it arrives at the detector, okay, of the last participant. What the last participant does is they perform their final measurement, okay, well, their final unitary operation also into one of these angles, and then observe a click. Okay, they either get a plus or a minus, and the detection probability also is given by this equation here, which looks very similar to what we had before. Okay, now also again, to check if the session is valid, the participants again have to mention which, in this case, have to mention which bases they selected from. Now, why do I say bases, right? Remember I said that each one of them select psi, which is the angle that dictates the unitary that they apply. Okay, it's just a relative phase. You can divide these unitaries into two classes, okay? One where psi is between 0 and pi, okay? We shall call that x. Here, x switches between the states in the bases, okay? And then we have y, which switches between the bases, okay? Now, once they are able to select these, okay, let's just go back here again. To check whether this session is valid or not, they all announce this y. And then the final participant has to check if this results in a deterministic value. In other words, whether where the detector clicks plus or minus, okay, corresponds with the right-hand side of this equation, which depends on the unitaries that were selected. So this sort of checks for correlations, checks whether the session was valid or not. Okay, so now if we want to perform this secret sharing in the lab, okay, where we have these multiple participants enacting some unitary on their photon one at a time, how would we achieve it? Well, we considered we considered using vortex beams, okay? Now, vortex beams are spatial modes of light that carry orbital angular momentum, and you can identify them by a phase vortex. So they have a zero null intensity in the middle, okay? What we did is, well, we coupled them to different polarizations. So I would have a vortex beam with a topological charge of L-1 and 1, each coupled to different circular polarization states, okay? Then to apply the unitary U, which imparts a relative phase between them, you can simply just use a half-wave plane, okay, which is a simple linear optical element that you can find in almost any lab Now, in our case, when you select X, which is the phase 0 and pi, again, you move between states within the basis. Okay, here we have a basis constructed of an azimuthally polarized beam and a radially polarized beam. Okay, and then using Y, you can move between the bases. And the corresponding MUB to this here is composed of these polarization states with spiral-like fields. Okay, so we did this in the lab. Okay, we generated these vector modes using a Q-plate, which is a birefringent optical element with a spatially varying birefringence, which allows you to couple the orbital angular momentum and polarization of light. So you would start with a Gaussian beam transmitted, and then you would be able to get radially polarized, an azimuthally polarized beam. In this case, our azimuthally polarized beam corresponds to the initial state that's prepared in the system. So we would then send it to the participants, where each participant has access to a halfway plate, and they would impart their phases on the photons. And then in the end, we would then have a deterministic detector that either looks for clicks here or clicks there. Okay, we did this with the vector modes, and we were able to transmit successfully the photons through the system with a fidelity of around 97%, and this corresponds to a bit error rate of about 0.021. Okay, so again, we showed that you could generate a key using such a system. Remember, what happens is each participant selects X and Y, which they impart on their photon. They only announce Y and keep X. They don't tell anyone what X is. And then in the end, they would have a correlated key that's constructed from the X's that they select. So X would be like 0 and 1 here. And then from that, they can construct the key. Okay, now we would like to perform this in high dimensions. Of course, to achieve this, you need to control, you need access to a degree of freedom of photons, which is high dimensional to begin with, right? In what I showed you now, we only used two-dimensional states. So, but what's interesting is that we were using the OAM states of light, which are known to be high dimensional, okay? And that is because the topological charge, which characterizes the amount of OAM in them, is actually unbounded. In fact, these OAM modes span an infinite dimensional Hilbert space. Okay, so how would we get these high dimensional states with, polarization and the spatial degree of freedom? What we did is we took three distinct topological charges, okay, and then coupled each one to polarization. So this here would be coupled to the right circular polarized. This also can be coupled to the right circular polarization state. However, this one is coupled to the left circular polarization state. Okay. Now that we have such high dimensional states, how do we perform the unitaries that we had before? Well, we need to first select a set of mutually unbiased basis states, okay, in the dimensions that you're working in, okay? And what you do is you don't use the computational basis, you only use the other superposition bases. So from the mutually unbiased basis, you only discard the standard basis, and you only consider the superposition state. Okay, so now what you need to be able to do to perform this secret sharing protocol, you need again access to an operator X, which can cycle between the basis states and then an operator y again, which can cycle between the bases. Okay? And to construct them, you can use these diagonal operators, okay, where omega is just e to the I 2 pi over d. Now, what we need again, just to show you graphically, okay, these are the standard basis states that I spoke about. You have your first mode, your second mode, your third mode, and then you need to construct the mutually unbiased basis states from the from this basis, okay, just from the superpositions using this relation here. And you then need to construct these operators that will cycle between the states individually and then the bases. Okay. In our case, we found that you can actually perform this the y operation by simply using the halfway plate, and the x operation by using a Dove prism. Now, a Dove prism just allows you to obtain this operation here, which is the x, because it imparts this phase, which is which is just e to the I 2 pi over d times L, okay, on each individual mode, while the half-wave plate can shift you between the bases here, and that only changes the relative phase between the right and left polarization state. Okay, so experimentally, what you would have is you would generate the vector mode. Okay, to generate this state here, the superposition of these modes, which is this basis set, you simply need to interfere, well, separate. You need to separate the beam that is diagonally polarized, okay, with a PBS into two parts. On one part, you would encode information. You would encode the OAM with a Q plate that transfers this state here. And on the other part, you only need to transfer, you need to convert the mode into a circularly polarized state, which gives you this here, okay? And then the output would be, the output would be a superposition of them, my bad. So then the state that you would have at the output here would correspond to this basis set. Would correspond to this state here, state 1 in the MUB1. That would be a superposition of all of these three states. Okay, now the parties, whom would be Alice, Bob, and Charlie, would now need to have a halfway plate and a Dove prism, which would correspond to the X and Y operation. So they could do this sequentially, and then in the end perform their measurement in the basis, in this basis here, the first basis, okay? Now, the issue with being in high dimensions is that you obviously need a detection system that can discriminate states within these bases, okay? However, that is quite difficult, and in our case, we only considered sifting through each basis one by one. Of course, this is inefficient, but at the moment, it's probably the best way to do it. There are some works, I must mention, where people are working on ways to measure deterministically such high dimensional states. Okay, so now what I've shown you only restricts you to 3 dimensions, okay? Because remember that our spatial modes are 3-dimensional while the polarization states are 2-dimensional, okay? And the reason why this was easy to perform is because you could use both the polarization and the spatial degree of freedom to control the phases between these states so that you can shift between the bases and the basis modes. However, if you want to go to higher dimensions, you probably need to couple the spatial degree of freedom to another high dimensional degree of freedom. And in our case, we considered using perfect vortices. Now, perfect vortices are the Fourier transform of Bessel modes, and they actually just look like rings, azimuthal rings. Okay, and each of these rings can have an independent OAM. Okay, so this here would correspond to the Fourier transform of one Bessel mode with a specific OAM charge, while this one here also has its own independent charge, and so on. So if I have many, I can then have many such rings, okay, where the charges of each one are independent. So I can write them as an independent superposition of modes that constitute to these rings, okay, where the azimuthal index characterizes the topological charge of each ring, and this radial index characterizes its position in the radial direction, okay? Now, to apply our unitaries on these modes, you can simply use an optical element that can apply a phase to each individual ring. And you can easily do this with a spatial light modulator, where each location on the ring can be encoded with a phase that corresponds to either X or Y. Okay, and we showed that you can actually actively do this. For example, shift between the states, okay, in one basis, and shift between the bases of various and shift between the bases using Y, shift between the states using X. Okay. Now, to do this in the lab, again, you would start with your mode, send it to an SLM, prepare your initial superposition state, and then each participant has access to a spatial light modulator. And then they transfer their desired X or Y operator, and in the end, they can perform a final measurement and then check whether there are correlations according to the protocol. Okay, and we showed that you can actually do this using these ring aperture states or these perfect vortices, and you can actually, in principle, get about 3.5 times the information, the mutual information as compared to your traditional two-dimensional states. Okay, if you're interested in reading more about this work, you can go take a look at the two papers that we wrote. The first one is on the spin-orbit coupling states, where we used polarization to realize our secret sharing. And then the second case is where we used high-dimensional states of these ring aperture modes to realize the secret sharing. With that, I'd like to close off, and I hope everyone enjoyed the talk. This is a picture of our group here in South Africa, and below are our sponsors. Thank you again to the organizers for inviting us to speak, and I'd like to thank you for your attention.
Thank you, Isaac, and thank you very much for finishing the talk before your time. So now there's time for question. So yeah, you can raise hand or you can unmute. Any question, comments? Okay, I have a quick question. You show that, I mean, so how have you, I mean, is it possible to check the the rate of keys when you increase the dimension, how the scaling behaves.
So the mutual information and also the key generation rate scales with log D base 2.
Yeah, that I know, but I am
With
saying
D
that
as you increase.
experimentally how
Yeah.
difficult it will
Oh,
be.
how do you check it?
Yeah, yeah.
No,
I mean,
like experimentally, well, I mean, there's two ways, right? If you know the fidelity of your system, there are equations that guide you to calculating what the best secure key rate is, or what the upper bound on the key rate is, based on the fidelity of your system. So how well you can sift through the modes. The second option is to check the number of key bits that were successfully transmitted, okay, and comparing it to what you expected, okay. So that would maybe be calculated from the error rate. If you know what the error rate, there are equations that guide you to knowing what the mutual information should be. Yeah.
Okay.
Yeah.
Thank you. So any other question, comments? Okay, if not, let's thank Isaac once more. Now I stop here and I pass the mic to Sandeep.
Thank you, Aditi. And I thank all the speakers of the session and our chair, Professor Aditi Sende. And we move on to the fourth session of the day. And our first speaker in this session is Professor Andreas Winters. Professor Winters,
Hello, yes.
Yeah. Hi.
Yeah, hi.
So here you can start sharing the slides. Meanwhile,
Sure, yes,
I would like to introduce our speaker. Professor Winter received the diploma degree in mathematics from Free University of Berlin in 1997 and PhD from the faculty, I can't pronounce the German word, so it's Faculty for Mathematics, University of Bielefeld, Germany in 1999. He was a research associate with the University of Bielefeld until 2001 and then with the Department of Computer Science at the University of Bristol, UK. Since 2003, he has been with the University of Bristol, where he was appointed as a lecturer of mathematics and as a professor of physics of information in 2006. Since 2012, he has been ICREA research professor with the Universitat Autonoma de Barcelona.
Oh, yeah, sorry, it's Autonomous University, yes.
Yeah, Autonomous University of Barcelona, Spain. His research interests include quantum and classical Shannon theory and discrete mathematics. He is recipient, along with Bennett, Devitak, Harrow, and Shore, of the 2017 IEEE Information Theory Society Paper Award. So today he will be presenting his work on resource theory of heat and work with non-commuting charges, yet another new foundation of thermodynamics. Professor Winters, the mic is yours.
Thank you very much. Thanks for the invitation. And I'm sure, like many other speakers, I have to say that it would have been so nice to actually be at IICR Mohali, but okay, one cannot have everything. Okay, good. Today I want to speak about this paper that we finished recently and posted very recently with Sarah Khanian, who is now a former PhD student in our group. She's already in a postdoc in Munich now. Manavendra Bera, who is, of course, who was formerly ICFO Barcelona, and Ana Riera, also formerly ICFO Barcelona. Manavendra, of course, is now in IICR Mohali. And finally, Maciek Levenstein. So down here you see the archive number. So obviously the full title didn't fit on the slide, and the second part is a little bit cheeky anyway. So I want to talk about something which, we took a long time to finish, but it's been years that we've been thinking about this stuff. And so let's see, I will just try to give a bit of a flavor of the work, because the fact is the paper itself is rather mathematical and maybe a little bit long. So I would like people to read it, but at the same time, I know that it's probably not possible to actually give it full justice in a talk like this. Okay, sorry. So I start here with a picture just to show that I'm really from Barcelona. Yeah, so this is the harbor side with the beach. Okay, so let's just jump directly into the setting. So we want to do thermodynamics. So we're looking at a system with a Hamiltonian HS. And for most of the discussion, S will be actually a finite dimensional Hilbert space. I mean, I guess one can also generalize it, but the interesting features appear finite dimensional. And we're looking in particular at this, at some kind of thermodynamical limit where we have many replicas of that system, many copies, each of which has the Hamiltonian H. So I have here, for example, HSI, which is the ith system, and I just sum them. Yeah, so by which I mean that I have the Hamiltonian of the SI system tensor with the identity operator on all the others. So there's no interaction. It's just a sum type Hamiltonian. And in addition, to this Hamiltonian, we will also want to consider further conserved quantities. And we also assume that they are of this, that they are kind of this non-interacting type, for example, like spins on different subsystems, or I mean angular momentum on different subsystems, they just add up in the same way. And so the number of these conserved quantities can be arbitrary, in particular because when quantum mechanics, they might be non-commuting. For example, the angular momentum, the sigma x, sigma y, and sigma z operators do not commute in any representation. Okay, so this is our setting. We have these many non-interacting systems, which you might consider as some kind of a limit, and one could try to overcome this by allowing certain interactions between them to make for more realistic materials, but this is our setting for the moment. It's kind of inspired by classical thermodynamics. And yeah, so somehow the basic way of thinking about this is starts with a single axiom that the state transformations have to conserve the entropy. Whatever we do, it has to conserve the entropy. So I don't want to, I mean, on this slide, I'm not even talking about physical transformation. I'm just saying, okay, effectively what happens between, time 0 and time 1, I find myself initially in state rho and finally state sigma, the entropy should be conserved. If I don't do that, it means I'll have to include some other auxiliary systems to take care of the entropy balance. And so the question, the first question you ask is, how does that restrict, well, I call it, say, the energetics, because that's the most important quantity, but of course also the other values of the other conserved quantities, which of course are not conserved necessarily under this kind of transformation. So yeah, so to make sense of this, I mean, I have to probably develop this a little bit. So first of all, I want to get an objection out of the way, and also why, maybe justifying why we are looking at many independent copies. And so this thing with the transformation of the conservation of the entropy, when you think about it, it looks like it's kind of trivializing the problem, because, well, on the one hand, of course, unitary transformations in quantum mechanics preserve the entropy. On the other hand, if I want to model my transformations by completely positive and trace preserving maps, which is somehow the largest non-controversial class of transformations that we are considering in quantum mechanics, in open system quantum mechanics, preserving the entropy implies that it has to be unitary. If it preserves the entropy of every state, it must be a unitary. And so that leads to a bit of a kind of an apparent paradox, because unitaries preserve much more than the entropy. They preserve the entire spectrum of the state. So assuming that S of rho is equal to S of sigma is not equivalent to saying that there must be a unitary, because the states simply do not have to have the same spectrum. And so, yeah, so going to the many copies, that's one way of getting rid of this issue. And so here's a little theorem. It's a kind of an information theoretical theorem It's nothing to do with thermodynamics. So on this slide, there are no conserved quantities. We're only looking at the entropy. It goes like this. So the entropy of rho is equal to the entropy of sigma if and only if rho and sigma are kind of unitary equivalent in the many copy limit. And kind of means, first of all, when you apply the unitary to rho tensor n, you don't get necessarily sigma tensor n. First of all, you have to attach some kind of an auxiliary system, an auxiliary state lambda to rho, and you will also get an auxiliary state mu from sigma. Both of them are kind of small. They live on roughly square root n qubits. And also you don't get exactly the correct state. You only get it in trace, approximately in the limit when n goes to infinity. So this is very typical information theory setting. So in information theory, you can learn that this is related to data compression. For example, you can learn what the characteristic of these lambda and mu's are. They take care of the fact that the spectrum of rho is not uniform. And so the rho tensor n spectrum is also not uniform, even though it's kind of almost uniform on a large part of the Hilbert space. And so yeah, being able to take this stuff out and allowing this small deviation in trace norm, which is the norm of statistical distinguishability of the states, that allows you to give a kind of a unitary picture, a unitary equivalence picture for the equality of entropy. It's not the only way, but it's kind of, I think it's natural when you come from thermodynamics, where going to this thermodynamic of many non-interacting parts is a sort of a classic assumption. Okay, so for the rest of the talk, I will have to reinsert the charges. I prefer to call them charges rather than conserved quantities, because in the stuff that we are doing, oftentimes it looks like they're not conserved, which is kind of natural in thermodynamics, because you always operate with batteries or with other external systems which provide energy and other quantities. Of course, on a fundamental level, they might be physically conserved quantities in the ultimate Hamiltonian of the universe. But for the thermodynamical engine, oftentimes that's a misleading expression. So charges just means, okay, it's a quantity of interest, and somehow it has to follow, we have to somehow obey certain rules. Okay, so once we accept our setting with our system charges, they're called A sub j, j from 1 to c, I guess because for charges. An important thing to do is apply the Jane's principle and look for the state with maximum entropy that has certain prescribed values, expectation values of those charges. And so we call this the generalized Gibbs state for these charges. So the simplest case is I just have the energy, the only charge is the Hamiltonian. Then this is the ordinary Gibbs state, and you should probably know that it has this form e to the minus beta h. And this comes from Lagrange multipliers. So it's no surprise that you can do the same thing when you have several conserved quantities, and then you get a similar form. You get this gamma of A is equal to 1 over z, which is, I didn't even write it, z is the partition function. It's the trace of this exponential minus sum beta j aj. And okay, so I'm using slightly different convention here, but I mean, to not break the symmetry between the charges, I just call all of these beta j's generalized inverse temperatures. It's maybe it's not completely standard, but it helps us very much to see kind of more transparently what's going on. And so yeah, these beta, they're just the Lagrange multipliers, and they uniquely specify this state here. And there's a one-to-one correspondence between the A's and the B's and the betas. Okay, so far so good. This is kind of mathematical analysis. It's actually not so difficult to work out. So the rest of the talk, I wanna go back to this information theoretical equivalence theorem and prove something that includes the charges, that also takes care of the conservation of the charges. And we call this as asymptotic equivalence theorem. That's somehow the basic technical result in the paper. that I put on the title. And with that, we can make a kind of a resource theory of thermodynamics based on this equivalence that kind of, and we can recover certain elements like the first and the second law. And in particular, we can recover some analysis of finite Barth effects. So when we come to that, I will probably have to explain this a little better. Oh yeah, so in the middle, I want to talk briefly about some old topic from the 70s called passivity theory in the setting of these many conserved quantities, or these many charges, because it gives you another sort of intrinsic justification why these generalized skip states are so special. Why they are considered to be, for example, why it's kind of safe to assume that if you want to model a Barth in the thermodynamics or in thermodynamics with conserved quantities, the Barth should come in such a state, and that if you want to distinguish Barths of different temperature, you're distinguishing different betas, for example. Anyway, so we'll get to that. Yeah, so like I said, we want to extend this purely entropic equivalence that I put up before to include the conserved quantities. And so it looks like this here. That's kind of the basic version with only the entropy. With only the energy. I will, for a large part of the talk, I will stick to that simply because it's easier to deal with only one conserved quantity, and also drawing pictures and so on is much easier. But I mean, I will try to give an impression of what the general setting with many additional charges is. So this version is due to Carlos Parachari, Jonathan Oppenheim, and Tobias Fritz from a few years ago already. So the reference is down here. And it goes like this: so that you have two states that have the same entropy and the same expected energy, if and only if you have the same kind of condition that rho tensor n plus the auxiliary lambda is unitary equivalent to sigma tensor n and the auxiliary mu up to small asymptotically disappearing errors for a unitary that conserves the energy. It has to commute with the energy exactly. So to say that, of course, we have to postulate an Hamiltonian on the auxiliary system. So this lambda and mu live on a kind of k qubit system, where k is between root n and n. And so not to cheat with the energy, so we'll write that the total Hamiltonian is just the sum of our previous in non-interacting Hamiltonian plus a term h prime on the auxiliary system. And the h prime has a norm, so which means the largest and the smallest eigenvalues are between minus k and k. So this is just to make sure that the auxiliary system are not able to inject arbitrarily large amounts of energy into the system. And so, yeah, you can do, it turns out a few years ago, we did this with the same group of collaborators, with Sarah and et al. We did the same thing as Sparachari, Jonathan Oppenheim, and Tobias Fritz for further conserved quantities. But we could do it only for the commuting case. So down here, the caveat is in our old theorem, if the charges Aj all mutually commute, then you can do the same thing. So two states have the same entropy and coincide with all their charges, expectation values, if and only if rho tensor n tensor lambda is asymptotically unitarily equivalent to sigma tensor n tensor mu, with a unitary that commutes with all the charges. So that means it conserves all of the quantities. So it's kind of nice. And yes, we have to do the same thing. We have to just add, we have on the auxiliary system, we have to add, we have to kind of create a suitable charge operator to add it to to have a joint charge operator on the whole system. And yeah, it took us a few years to realize how to generalize this even more when the charges do not commute. like I said, in the case of angular momentum, if you want to deal with that, you need it. Well, it took us a few years because we were never able to figure out how to actually do it in such a way that the unitary conserves the charges in question exactly. So after a while, we just gave up and we decided, okay, let's simply relax this to almost commuting unitaries. So simply saying that the unitary commutes with the AJ in this sense. The commutator is bound by the same K. So again, this K is some quantity which is a little bit larger than square root of n, basically. Yeah, so this is, I mean, from the point of view of fundamental physics, maybe this is disappointing, but from the point of view of building a machine, that's kind of okay. So it's basically saying, okay, this unitary, that's somehow the machine that's supposed to transform the states, and it's not, since it almost commutes with the charges, it's not able to cheat you kind of massively in terms of these quantities. Notice that rho tensor n. So why is that important with this square root of n? I mean, maybe I should have, the scale here, that k is between square root n and n. So the lower bound has to do with the fluctuations, both of the observed charge value, since we're only talking about the expectation value, and of the entropy. And the upper bound, it comes from this, that when we look at rho tensor n, I mean n copies of rho, since our charge on the n copy system is always the sum of the single copy terms, the charges will always scale like order n. So anything that scales weaker than order n is kind of okay in this asymptotic limit, and that's why we think we can do that. Okay, so yeah, it doesn't trivialize the matter because it's an if and only if, right? So these rules here, they don't allow to transform any state into any state, only when they coincide with their entropy and with their charges. And okay, so this is the mathematical statement, and maybe I spent a little bit too much time on it, but so now let's look at a few pictures. So what this equivalence theorem says, that two states are kind of asymptotically equivalent, indeed, as the name suggests, under these almost commuting unitaries and modulo small ancillary systems, if they have the same entropy and charge expectation values. And so that means we can just identify a state with this list of numbers. They kind of from certain sense, from our point of view, as long as we're not interested in other charges, they're really equivalent. They are just transformable into another by nothing more than a unitary. And so we're looking at this phase diagram or charge entropy diagram, which is simply the convex hull of these vectors of all the A's, so the A1 to AC, and S, the entropy, the von Neumann entropy. And yeah, we take the convex hull here because if you just take the set of these numbers, this may not be automatically convex. That comes from the fact that the entropy is not a linear function. So, I mean, the states, I mean, rho is an arbitrary quantum state. So this is somehow the image of the set of all quantum states, but under a map which is linear for the A's, but concave for the entropy. So yeah, in general, we have to take a convex hull, but sometimes it's actually already convex. And so the convex hull is called the phase diagram. And so yeah, if you again with a caveat that now I ditch mostly the charges because I want to draw pictures, so I have only one axis for the charge, which is the energy, and one for the entropy. This is what the typical entropy charge diagram, so energy entropy diagram, will look like from this paper of Sparacciari et al. And so up here, the red line, these are the points corresponding to the maximum entropy. So they correspond to a unique state, each of them, the Gibbs state. And only here, this vertical line, these are all the states of minimum energy. If you have a degenerate ground space, then there might not be a unique state. But there is a unique entropy maximizer, which is this point up here. So this corresponds to the temperature 0, temperature infinity. And because I plot this for a finite dimensional system, there's also something going here where I make the temperature negative. So I have here also negative zero temperature up here for the maximum energy. So if you want, you can ignore this right-hand half from beta towards the right, if you think that's unphysical, but in a finite dimensional system, that's sort of natural that this would appear. Yes, okay, so this is just, yeah, this is just, actually, this is going to be important. The upper boundary is, of course, smooth, and we know that the derivative, the slope on for a point beta is, sorry, at a specific point, here is precisely beta. So when you look at the derivative of S by the energy at that point, so which is exactly this axis, this gives you beta. So this is somehow a way of encoding the relationship between E and beta. Yeah, it's convex by definition, but for example, in the case of energy and entropy, or in the case of commuting quantities in the entropy, it turns out that already the set of these points A and S is convex. You don't need the convex hull. This isn't, however, we know that it's necessary when you have non-commuting charges. Okay, so the points in this diagram, so it's this interior, right? So this is in color, I drew the boundary up. The lower boundary is zero here, zero entropy, but energy. So these are pure states. And then you have states populating all the interior here. And so, yeah, so for a typical rho, you have here the pair of the expected energy, trace rho h, and the entropy S of rho. And then I drew a couple of quantities here. So this A of rho we will not discuss, F of rho and B of rho. So like in this next slide, I will just define them. So, yeah, then maybe it's a little bit notation overload, but so B of rho is simply the minimum energy of any state with the same entropy. And so that state, when you think about it, this minimum energy state for a given entropy, this is a different way of identifying the Gibbs state. It's kind of a dual thing. The Jane's principle says, oh, maximize the entropy for a given energy. You will get the same family of states if you fix the entropy and minimize the energy. And so for each state rho, it has some kind of an associated generalized Gibbs state that I write gamma of rho, and it has its particular energy, E of that. So E of rho is simply the expected energy that's written up here. And so, yeah, so this is the lowest energy for the isentropic class. And then we call this the absolute bound energy, and the absolute free energy we call simply the difference between the internal energy of rho and this one. And so this turns out to be actually, you can write this in a familiar form of a free energy difference for example, using this relative entropy here in the particular intrinsic temperature of the state. So I mean, this may not look like it, but this is really a free energy difference when you choose the temperature to be this particular intrinsic temperature of the Gibbs state of associated with rho. And we write the usual, you know, this, I think this is called Helmholtz free energy. So the internal energy minus KT S of rho. And yeah, so then we have here somehow two particular states on the boundary, the one where we go on the same entropy, but to minimum energy, and the one on the vertically when we go on the same energy to the maximum entropy. So this is somehow the Jane state, and this is this minimum energy state. So I wasn't really paying attention to how much time I have, but it may not be that much. So let's talk very briefly about passivity, which is to say, what are the states from which you cannot extract any work? And so looking at this diagram, you can see, well, it has to be on the boundary because if I can move here on the left, I reduce the internal energy. I can siphon this off into a battery, and preserving the entropy, and okay, so I can extract work. And so Push and Voronovich in the 70s came up with this concept and to identify the form of the equilibrium states. And so indeed, in a more recent paper by Litsky and Farnes, they show that the work rate, the work per copy of the system you can extract from many copies of rho equals f of rho. And so the model is a bit like this here. So you have to couple your system to a battery. You have to invent another system because you're not conserving the energy here. So you have a bipartite system, and on the joint system, you're preserving the energy. And your thermal machine is somehow mediating between these two systems. And so, I mean, what comes out in this Push, Voronovich, and Lennard model from 78 is that it's actually completely consistent to assume that you can affect any unitary on the system with a suitable interaction with a weight or with a battery. And this changes the internal energy of the system, and it changes the internal energy of the weight by exactly the opposite. And also it doesn't change the entropy of the weight. A weight is kind of a big deterministic object. So of course you will have internal degrees of freedom, but these are not relevant for the battery. The battery is just in a pure state. And this is kind of what we do here. So mathematically, and this kind of goes to our equivalence theorem. In our setting, what we are looking at is not the system S alone, but at S tensor W, and W is the weight or the battery. And we want to transform really rho tensor a weight state 0, W0 to another state, it turns out gamma of rho, the corresponding Gibbs state of rho tensor W1, with pure states W0 and W1 of this battery. So they don't contribute to the entropy, so it's only sufficient that rho and gamma of rho have the same entropy, and they can balance off any difference of energy, of internal energy that rho and gamma might have. And so yeah, our AET says precisely, well, okay, if W1 minus W0 is exactly the energy of rho minus the energy of gamma of rho, then you can do it. Then there is an asymptotic equivalence between these states. So there's a machine that transforms this rho into this corresponding Gibbs state. So that means it makes this move here. It takes this state that has this point and moves it over here. And the difference in energy turns out to be transferred to the battery. And so, yeah, just to say that you can do the same thing for many charges, but you have to be a little bit more careful, because when you have many charges, then you can somehow sometimes extract one charge or another, or you can, there are many different changes you might want to effect. So here's one version of passivity theory. It goes like this. If you, let's say you want to consider transformations that preserve the entropy and all but the first charge. The first charge, remember, we introduced it as the energy, so it's kind of nice, it's kind of meaningful that we call it the work. We want to extract that number, that comes in units of joule, but we want to conserve all the other charges on the system. So we want to, that means we are interested in, ultimately, kind of in the spirit of Push and Voronovich, we're interested in maximizing this delta E here, trace rho h minus trace gamma tilde of rho h, and where this gamma tilde of rho is some kind of an associated generalized Gibbs state. We're minimizing the energy subject to the conservation, to the fact that the states we're looking at have the same entropy of rho, and they also have all the charge values A2, A3 up to AC in common with rho, except for A1, of course, that one we minimize. And so it turns out this is exactly the maximum work you can extract in this setting, and you do it exactly in the same way. You attach a weight, you attach a battery for each of the charges. Well, actually, you only attach a battery for one of the charges because you want the others not to change. So it's enough. So you attach a battery that has only charge value A1, but cannot absorb or give any of the other charge values. And then the asymptotic equivalence theorem tells us exactly that we can go to another state, gamma tilde, and realize this work extraction. And so that kind of justifies that these generalized Gibbs states, they extend the complete passivity of Push and Voronovich to conserved quantities. So these are indeed the states which by themselves do not allow you to do work. So these are the only candidates you can allow if you want a bath. And so, yeah, that brings me finally to the laws of thermodynamics. So I probably should look a little bit hard with time.
You have still, I think, 8 minutes. So.
Okay. So yeah, let's see. Yeah, so let's just go quickly through some of these laws. So the zeros law, this is just about equilibrium. So so for the single charge, there's a single inverse temperature, and so what this means is for complete passivity, it means that they all have to have the same inverse temperature or the same temperature. And so you have a similar thing for multiple conserved charges. So kind of if you wanna discuss a bath or different bath systems, there is a kind of a distinguished setting that they all share all this beta 1 all the way to beta c. The first law in our setting is actually a bit disappointing because, I mean, I'm referring to the preprint I'm discussing. The first law is basically just an expression of the conservation of energy. So we are kind of, we're looking at a system in contact with a bath B, and if we just look at the entropy preserving transformation rho to sigma, well, the point is we can always do that if the rho and sigma have the same entropy, if we augment the system by batteries for the charges A1 through AC. And so the way I would like to think about this is that each battery only has an operator for that charge. And the charge, so on the first battery, it has energy, but it doesn't have any, the conserved quantity for all the others is essentially 0. I mean, in some approximation, we put it 0. So I didn't put a reference here, but there's the beautiful paper by Gurianova et al. That discusses this in the case of angular momentum. And so the second law, yeah, this is also a bit boring in this setting, as long as we don't have a bath. So if you just want to look at a process that extracts work or some other charge, okay, you can do this, and the quality is attained when your final state is precisely the corresponding Gibbs state. This is already good enough to discuss a little bit of traditional thermodynamics, like a Carnot cycle, where you have a hot and a cold bath, and you're looking at the work extraction. But I don't want to do that. Sorry, there's another picture here. I want to go to the setting, to the general setting, where we have a bath, initially a bath in a specific temperature, inverse temperature of the energy and of all the charges. And so our system becomes more and more complex. So now I will discuss this only for a single charge. So we have just the energy. So if the system, the bath, and W. So this is somehow the weight. Remember, in the case of multiple conserved quantities, there should be W1 all the way to W sub C. And so the rules are the batteries are always in a pure state, so that they don't contribute to the entropy balance, and they don't build up correlations with the other systems. The bath, however, starts off in a Gibbs state. That's kind of how we think of it, and it's justified by the passivity theory. And so then you can ask your question, so which transformations are possible from an initial state rho S tensor, such a Gibbs state, to a final state? And in the final state, we are sort of interested mostly in sort of prescribing what is done on the system. So kind of in all these discussions where you say, oh, work is done on a system, you mean something like this. You want to end up in a state rho SB, sigma SB, with a prescribed sigma S. That's your target. And you wouldn't want to know, so, well, of course, that's possible if I can make the entropy on the left and on the right-hand side equal. And what are the corresponding energy differences? So this should be, I guess, a delta E. But I guess delta W is better because it's somehow what is the corresponding change on the battery. And so, yeah, then the second law actually looks something much, much more familiar, because we have now a bath of a Gibbs state temperature, and we see that so to this kind of transformation from rho S to sigma S is possible only when the delta W is less than the free energy difference between the initial and the final state at that particular temperature. And that's only a necessary condition as long as I don't say more about the bath. So this condition is true for any bath. And it's asymptotically saturated, so sufficient, if the bath is large enough. So it goes like this. If this delta W is strictly less than the free energy difference, then there exists a bath system such that, for example, the following is possible, that we go from rho S to the tensor, the temperature T Gibbs state initially, to sigma S tensor the Gibbs state at a slightly different temperature. Excuse me. And so, yeah, so the interesting thing is for finite bath size, there will be some corrections. And so you can kind of see how that goes. For finite bath, we cannot actually assume that we have this final form, that the bath doesn't necessarily end up in a Gibbs state itself. I mean, locally, yes, but not but not in relation to sigma S. So what we need is that the entropy is preserved, right? So entropy of rho SB is equal to the entropy of the finals. This is a sum because the tensor product is rho S plus the entropy of the Gibbs state, and this should be equal to the final state, which is equal to the entropy of sigma S plus a conditional entropy term. So I just introduce a difference here. So it's just a formal trick. Why? Because I'm given what rho S and sigma S are. So both have their entropies and also their charge values. And so that means we need to find a state, sigma SB, first of all, that satisfies this here. So it has a prescribed marginal sigma S. And its conditional entropy is equal to, well, just solving for it, is equal to S of rho minus S of sigma plus the entropy of the Gibbs state of the bath. And so, and we're looking for the one with the minimal energy. And so if this S star is positive, then we can solve this in the phase diagram, because we're just, I mean, we're looking for a state with this S star entropy, and so we can always find a Gibbs state of that entropy of minimal energy. We're just going most on the left to the left of this line here, and that's it. And so this is kind of how the bath changes, right? So it's very important to see. We know already what kind of work transformation of the system on the S system we want to do. So now it's just a question of what kind of state change do we have to see on the bath to make this possible. And so when you look at it, the energy you can extract is this line, is this interval up to the blue point, to the bright blue point. But the second law would allow you to go down to the intersection of the diagonal and the horizontal line. And so the difference is this delta, which comes from the finiteness of the bath. So on the other hand, an interesting thing occurs when the entropy, when this S star, this sum and difference is negative. That couldn't happen classically. I mean, this is a conditional entropy here. This always has to be positive in classical. So this would be say, okay, this can simply not be done with that particular bath in a classical setting. But in quantum, that's not true. In quantum mechanics, the conditional entropy can be negative. And in fact, we can give a meaning to this. So we go to an extended phase diagram where we plot basically a conditional entropy versus the energy. And it turns out to have this shape here. So it's kind of has for positive entropies, it has the same shape as the phase diagram before. And for negative ones, we just flip that, just a mirror image, except that at minus S of sigma, we cut it off. It's simply not allowed to go below that. So again, it has this horizontal cutoff. And now if we have if we want to do a transformation, we want to go from this from one state to another. So on the bath, it means we go from this Gibbs state that we are on the top up here, so this corresponding to inverse temperature beta, all the way down here where the conditional entropy is negative. It's as long as it's in the diagram, we can find points on this horizontal line. There are states corresponding to this, and there's in particular a state here on the left that minimizes the energy, and it's some kind of an anti-Gibbs state, right? It's sort of it has tremendous correlation between the system and the bath, and in fact, the negativity of the conditional entropy is a witness that the state is entangled. So this is very, very peculiar. And it enables certain work transformations that wouldn't be possible using the same path in a classical setting. And so, yeah, here's a kind of an afterthought for the conclusion about this assumption of entropy conservation. So it turns out, ultimately, we don't need even that. I mean, once we have this idea of this asymptotic equivalence with unitaries, and we see that, okay, for the charges, we can simply deal with batteries. Well, we can also have a battery for the entropy. I would call it a purity battery that has no Hamiltonian, so it doesn't contribute to the charges, but you can have entropy. It can be in a maximally mixed state of 0, 1, 2, 3 qubits, and there's different amounts of entropy. So then we kind of can trade all the different conserved quantities, including the entropy, amongst each other. So I've shown that we can include other conserved quantities. Of course, I didn't draw the diagrams because they're a little bit less clear and it's harder to draw also. So the big subtlety is that in this asymptotic equivalence theorem, asymptotic equivalence theorem, we need to allow unitaries that only approximately commute with the charges. So we don't really know if it's necessary. I would call this an open question. Is it possible to do the same thing with exact commutation with the reference frames? And I want to refer to a paper that I had with Sandro Popescu and other people from Bristol a few years ago, where we show that it seems to be possible, at least in some cases, to construct batteries that also allow you to physically separate the different charges in different subsystems, which is some feature that we have here. Like we can easily have separate batteries for all of the conserved charges. And so, yeah, the final thing is, I would say, since we did this kind of many copy limit here, and with non-interacting systems, these are, of course, the next obvious things to develop. One of them is to do one-shot theory. So one would need an equivalence theorem for the entropy in a one-shot setting. And I think such things exist when you allow catalysts. So you would need some kind of background catalyst system to deal with it. And another one would be to allow correlations, which also should be easy as long as the correlations are kind of weak enough, because then they just introduce some kind of perturbation to this independent many copy thing. And I think that's the end of my talk. Thank you very much.
Thank you, Professor Winter. Due to running short of time, we can take one very short question.
Sure.
Dr. Usha Devi.
Hello, thank you for a very interesting talk. So I wanted to just ask you, when we talk about passivity, complete passivity, we have some multi-copy kind of a situation. That is, we take multiple copies and then analyze what is the complete positivity there. But in the resource theory framework, where one only talks about state-to-state transformation and only talk about work extraction in that kind of a thing, both these things, are there any connections between pure resource theories where one only bothers about state-to-state transformations and work extraction, and on the other hand, we have only passive states and we talk about multi-copy, which gives me a complete passivity, that is no more work extraction possible? Are there any connections between the two approaches? I hope I'm making myself clear.
Yes, yeah, okay. I mean, I think that's a very open-ended question. I mean, I think, yeah, it suggests a lot of different work that one can do, for sure. Obviously, in the work I reported on, we're looking at exactly this many copy setting, and so we can stick with complete passivity, which makes for a very nice structure. So there are these very nice Gibbs state families of or generalized Gibbs states that result. I mean, if you don't do that, then you already have much larger sets of passive states.
Yes.
So that will make the whole theory much more complicated, for sure.
Yeah, but in the complete passivity, the understanding that restricts ourselves to state-to-state transformation, which preserves entropy.
Yes.
That is to get out of it and talk about more general systems of what is entropy non-preserving kind of things, where we can talk about thermodynamics still in terms of multi-copy. Same spirit as how we do passive states. That is
Yes.
also not yet there.
So I will suggest the further discussion can be done either in the chat or
Thank you.
so
Sure.
if there are more questions from anyone in the audience, please type that in the chat, and I'm sure
Thanks.
Professor Winter will
Sorry
be more than
for
happy
running a
to.
bit over time.
Sandeep,
Yes.
I don't have a question, but I just want to say hi to Winter and tell him that thanks for accepting our invitation and giving such a detailed talk.
It's a pleasure. It's a pleasure.
So let's finish this talk, and I would like to thank the speaker again. Our next talk is by one of IISER Mohali's alumni, Vikesh Sidhu. Vikesh, are you here?
Yes, I'm around.
Hi, Vikesh.
Hi,
So
am I audible?
You are audible. Can you share the screen?
Yes, there you go.
So
I think
Vikesh, as I said,
Winter has to unshare.
No, I think it's working. So as I said, Vikesh Sidhu is IISER Mohali alumni. He did his dual degree, BSMS degree from physics major. He received a PhD in physics from Carnegie Mellon University, CMU. At present, he is a postdoc in the quantum computing group at the Day4 School of Business in CMU. So today, Vikesh will talk about non-additivity in quantum communication theory. Vikesh?
Well, it's always a pleasure to come back to. It's always a pleasure to come back to IISER Mohali. This is where my journey in science began, and also later my journey in physics, and then in quantum information, where I started my master's thesis.
I'm so happy that in this conference there are a large number of IISER Mohali alumni speakers, and we are very happy to have all of you speak at this conference. It's a very nice thing which is happening.
Well, thank you very much for organizing and thanking me. This is my pleasure to be allowed this audience, and it's somewhat intimidating to follow Andreas.
Vikesh, we can't see you. Can you switch on your?
Actually, this might be the most stable way of conducting the talk.
Okay. Okay.
Yeah. But am I audible and is the screen visible?
Yes. Yes.
Okay. 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 Yes. So what I want to talk to you about is this issue of non-additivity in quantum communication. But essentially what this talk about is generalizing our notions of information given that we know that the world is now quantum mechanical. Well, we've known that for quite a few years, but it's sort of a curiosity in some sense to understand what the effect of this is on the theory of information. Next, of course, one would have some sort of theoretical motivation to study these, that there's a theory of communication and information which is quantum mechanical and it is under construction. And one would like to sort of, as a researcher, it's a sort of a fertile place to develop new conceptual and theoretical ideas. Next, of course, there's somewhat practical motivation to care about these things, that there are quantum mechanical devices for computing and communication that are being built, and there is some need for theory which supports this experimental and technological advance. Well, to discuss about this technological advance, let's start first with classical information theory. Well, and in particular, one would like to see what is classical information. Well, it's the kind of ordinary classical information that you obtain if you toss an unbiased coin. You obtain an outcome and it gives you some information. This has a very straightforward property that when you read this outcome, the outcome of this coin toss, you do not disturb the coin toss itself. In fact, you can also copy this kind of information and you will not disturb the information that you copy. This is an operation, copying of information is something that we do all the time in the classical world, where we copy files on our computers, attach them in emails, and so on. Quantum information is not stored in coins, but it's stored in quantum mechanical objects. One of the examples is the polarization state of a photon, about which we just heard a talk. And the polarization of a photon can be represented geometrically. And here I've given the qubit block sphere picture, where on the top of the sphere I have mentioned square bracket 0, and the bottom is square bracket 1, which represents vertical and horizontal polarizations respectively. And then on the right and left of the sphere, I have right diagonal and left diagonal represented as plus and minus states. And this sort of square bracket notation is essentially by notation for a projector onto a pure state. Turns out that whatever this information is, which is stored in this quantum mechanical object, it cannot be read without being disturbed, and it cannot be copied without being disturbed. And this is a surprisingly, this differentiates how classical information works from quantum information, or quantum information works from classical information. And in that sense, there's a quote which says that quantum information is more like the information in a dream. If you start telling your dream, you eventually forget what your actual dream was, but only remember what you said. And in that sense, you've disturbed your original dream, at least your memory of it. And one would like to understand how this information is transmitted, and information is sent across channels. For instance, I'm communicating to you right now through a sequence of channels. The first one, of course, is from my vocal cords to the mic of this computer, and the medium there is air, and somehow this my voice is encoded into air and then decoded by the mic. And then the mic further encodes this information to be sent electronically through the internet. And then there is a sequence of cables, one from my internet provider, one from my computer to my router, router to internet provider to perhaps the transatlantic cables, and then that goes to somewhere perhaps in Bombay or Visakhapatnam, where this cable might arrive, and then it gets routed further. So there's sort of this network of physical devices connecting us, and all of these are channels. And essentially, these channels send classical information, and so they take distinguishable states to distinguishable states. Now there's sort of a push to build similar networks for, say, sending quantum information, and these would, well, send quantum states to quantum states. And while this is the physical description, one would like to understand the mathematical description and understand the properties of this channel of sending information. For instance, for a classical channel, you can understand these channels using what is called a conditional probability distribution, P of y given x, where y is the output of the channel, x is the input. And these channels essentially take an input probability distribution to an output probability distribution. Quantum channels, well, you can think of it that way as well. It takes the quantum generalization of a distribution, which is a density operator rho a, to an output density operator rho b, where, of course, this density operator is this, complex positive semi-definite operator, unit trace, all the nice stuff. And the point is that these channels are noisy, and one would like to understand where this noise comes from. And the source of noise is the interaction with an environment. The way we model this quantum mechanically is we start with an input quantum system, say rho a, and we model the noisy interaction using an isometry which takes the input, the joint output between an output rho b and an environment, say, environment system here, C. This joint output environment state may be entangled, and so part of the information might be flowing out into the environment, which you intended to send from the input. Of course, the environment is by definition something you don't have access to, so you trace out the environment to get a map that takes you from the input to the output, here represented by B. Mathematically, of course, you can also trace out the output and then get a map from the input to the environment. In that sense, quantum channels come in pairs. One channel from the input to the output, the other to the environment. And let me give you the simplest examples of these pairs. So think of a qubit input and think of a qubit output and a qubit environment. Then on the right side, I've geometrically shown how, say, a phase damping channel, which does nothing, say, to the 0 and 1 states, but squishes the other states to make this spindle-like object. Its complement C is a measure and prepare channel. Its action is to take the Bloch sphere and squish it down to a single line. And this line can always be drawn tangent, actually, to the original spindle. Similarly, you can have amplitude damping channels. For instance, in the left-hand side, the action of the B channel is to take the 1 state with some probability to the 0 state and keep the 0 state fixed. And its complement actually is also an amplitude damping channel where the 1 state is fixed. And these can always be plotted in a Bloch sphere such that they touch at a point. These channels are of some experimental relevance, actually. The phase damping and amplitude damping noise occurs in a variety of experimental setups where qubits are initialized. And one would like to study how one can protect against, how one can encode information in these quantum states and protect them from noise. Well, in order to understand how to encode this information, how to encode information and how much of it can be sent, you have to sort of discuss what type of information one is speaking of. For instance, classic quantum systems can send classical information in the form of bits. This was, for some time, people thought that, well, since the quantum states grow exponentially, so if you have n qubits, the Hilbert space of that system is 2 to the n dimensional, perhaps one can retrieve an exponential amount of classical information from quantum systems. A theory of information was developed by Oliver, Schumacher, and Westmoreland, who were able to, well, Oliver at least showed that you cannot recover more than n bits of information from n qubits. And then a sort of a theory of this was developed by Oliver, Schumacher, and Westmoreland, which gave you the capacity of noisy quantum systems for sending classical information. Another kind of information can be sent across a quantum channel, which is private information, where the information, there's classical information being sent, but it is hidden from the environment of the channel. It was not thought that one could actually do something like this unless someone put forward a protocol in 1984. So Bennett and Bresard did that at a conference in Bangalore, where they wrote down explicitly a protocol for sending classical information using quantum states such that the environment, such that this information is hidden from the environment or the eavesdropper who is listening to this. Again, an information theory of this was built up, which characterizes how well you can do this. The key contributors actually are Winters, Devitak, who built up this theory of information. Next, of course, is you can try and send qubits perfectly. Again, and I think the skepticism continues that you can do this in an error-free way. And the first protocol to do this was perhaps by Shor and Steen, later added to these protocols of correcting information being sent in quantum information being sent through quantum states. And then a theory of information of this was built up, which characterizes how well you can do this. Again, the fundamental contributions are from Knill, Shor, Lloyd, and Vivitzak. And all of these people in some sense, this is the most amongst the most fundamental theories that we have in quantum information, which is called quantum Shannon theory, when we try to understand the capacity for sending information. In this talk, I will majorly focus on the quantum capacity, which is the ability of channels for sending qubits or quantum information. In order to have a discussion about how much information can be sent, we need to quantify somehow how well error-free communication can take place over a channel. So let's think of a canonical setup where you have Alice who is trying to send some units of information, say k times r units of information over k joint users of a channel B. And Alice encodes this information through some encoding map into the input, in the joint input of the channel. And then at the output, Bob is to decode. And suppose Bob and Alice are able to establish a protocol in which they can send kr units of information with vanishing errors, the number of channel users k tends to infinity. Then one says is R is an achievable rate of correcting errors in the information being sent. Well, if the information being sent is classical, then the units of information is bits, and so R will be an achievable rate for transmission of classical information. If you're trying to send private information, then the unit will be private bits. And if you're trying to send quantum information, then the unit of information will be qubits, which is what will be the focus of this talk. Of course, this is just one way of sort of, R is just an achievable rate of sending information from Alice to Bob. And there's a particular encoding and decoding that does that. One would like to understand what is the ultimate limit of the channel that is being used. And so you maximize over all possible encodings and decodings, and you get what is called the asymptotic quantum capacity of this channel. Having defined the achievable rate and the capacity, one would like to compute these numbers. The way to compute these numbers is to first compute them for classical channels. So suppose you have a classical channel which sends input symbols to output symbols with some probability P of Y of the output given X the input. Then Shannon actually in his seminal work laid down how one does this. You compute what is called the Shannon entropy of the random variable X, which depends where the random variable follows the probability distribution Px. And the second ingredient to Shannon's work is computing the mutual information, which is the mutual information between the channel output Y and the input X. And it can be computed by just summing the entropies of X and Y and subtracting the joint entropy. Next, you maximize this mutual information over all possible distributions, and you get a number. And this number, which I've referred to here in this talk as the channel mutual information, is an achievable rate of sending classical information across a classical channel. In the quantum world, you essentially try to replicate this recipe by changing the key ingredients in the proper way. And the proper key ingredients are the following. You change the Shannon entropy to the von Neumann entropy, which is computed by this trace of rho log rho with a negative sign. The proper quantum analog of the mutual information for this case is the current information, which is just the difference of the output and the environment entropies. And then you maximize this just as the channel mutual information was obtained by maximizing over input classical distributions. The current information of the channel is obtained by maximizing over the quantum analog of classical distribution, which is density operators, and you get an achievable rate of quantum communication. So far, so good. Now you have achievable rates, and we want the ultimate capacities. And so in the classical case, you use three key properties. The first is called additivity, joint use of two channels n and n prime. The mutual information of that is simply the sum of the individual mutual informations. And then the capacity can be written as a limit over k users of the channel, and you regularize by k, and then you take k to infinity. Turns out because of additivity, this limit is straightforward, and you just get the channel mutual information. And then you can also ask, well, what is the capacity of two channels used together? N and n prime, it's just simply the sum of the capacities of the individual channels, which also follows from additivity. In some sense, this is all very nice and intuitive. You have, I'm communicating to you with this through this device, and if I try to call you over the phone, then the maximum information I can send to you is the maximum information I can send to you through each device. This doesn't quite work in the quantum world. Additivity fails, so the current information of two channels P and P prime used together can be greater than the sum of the current informations of the individual channels P and P prime. As a result, the quantum capacity, which again can be written as a similar limit in the classical world, now becomes difficult to compute because it can be strictly larger than the current information of the channel. And this kind of non-additivity permeates all the way to the actual quantum capacity. It's present in the current information, but it permeates to the quantum capacity as well. So two quantum channels used together can have strictly greater capacity than the individual channels, than the sum of the capacities of the individual channels. Well, what do these non-additivities do? Well, they present some challenges. For instance, the quantum capacity, this limit, is somewhat difficult to compute because, you have to compute current information over asymptotically many channel uses. And actually computing the current information is a non-convex optimization problem. And so it's this limit is somewhat intractable. Computing the limit is intractable in some sense. Next, you can ask some questions about capacities which are then become hard to answer. For instance, if you have a channel, can you tell me if its capacity is positive or not? Well, if you try to follow this limit, there are somewhat stunning examples of non-additivity where for each integer n, the current information over n joint uses is 0, but over n plus 1 uses is positive. Then you can say, well, suppose the channel has 0 quantum capacity. Is it useless? That's also false. You can have examples where two channels each have no capacity, but the joint channel has capacity. This is called superactivation. And so finally, you have to ask, well, when and why are these non-additivities present? There, the answer is unknown, actually. You have examples, but much is unknown. While these are challenges presented by non-additivity, there are opportunities. The first opportunity is that you can develop new theoretical tools to understand quantum communication. Given that non-additivity challenges our understanding, there is an opportunity to develop tools to improve our understanding. Next, there may be opportunities to gain conceptual insights about quantum communication. Since the subject is since the subject is not very well understood, maybe there is some conceptual insights you can get. And next, of course, somewhat practical, maybe you can leverage non-additivity for quantum error correction. Well, why not? After all, quantum capacities are essentially a discussion of how well you can correct quantum information over noise. And the presence of non-additivity allows you to develop, strategies which are truly non-additive and are perhaps not possible in the classical case, where things are additive. What I want to talk to you about is one new theoretical tool, which one refers to as called logarithmic singularities in the von Neumann entropy. The essential idea behind this tool is pretty straightforward, so let me try and convey that. You start with the density operator rho, which depends on a parameter epsilon, and you look at its entropy, which can be written in terms of its eigenvalues lambda I here, and you basically sum lambda I log lambda I with a minus sign. Consider the case where one of the eigenvalues is exactly epsilon and the other is 1 minus epsilon. Notice then for small epsilon, the derivative of the entropy is logarithmic in epsilon. And this is what I essentially refer to as a logarithmic singularity. This occurs quite generally when you have a density operator whose eigenvalues increase sort of linearly from 0 to leading order in epsilon. You will get these singularities. When these singularities are present, they somehow, in the region that they are present, dominate the behavior of the von Neumann entropy. And if there is a physical quantity or a phenomena associated with the von Neumann entropy, that too will be dominated by the singularity. So in that sense, these are quite general and extend beyond quantum information. Of course, I have only applied them to two problems in quantum information, which is the problem of when you can send quantum information and when can you send it in a non-additive way. Using them, one can develop methods essentially to check if the current information of a channel is positive or non-additive. Let me give you a simple application. Let's start with what we call an incomplete erasure channel, CG. With probability lambda, it sends everything perfectly. With probability 1 minus lambda, it applies a channel C1. And suppose C1 is the qubit amplitude damping channel, which I introduced at the beginning of this talk, where the amplitude damping occurs with probability 1 minus p. Let's plot the current information of this. Oh, this figure has very many things. Let's focus our attention at p equal to 0, where you have the cyan line. At p equal to 0, this amplitude damping channel damps perfectly. So CG becomes an erasure channel, which transmits perfectly with probability lambda. For such channels, there's a well-known result that as long as the transmission probability is greater than a half, you have capacity and positive current information. When you have less than a half, you have no capacity. And now, so that comes out clearly here at p equal to 0. Now you make p a very small number, so 0.05. So let's focus on the green line. Intuitively, the threshold where the capacity goes to 0, one might expect perhaps it shifts slightly to the left of the threshold where p was 0. And so one runs some numerics and sees, okay, trace the green line. Since you're sending some p is larger, so the current information is slightly larger. And perhaps the threshold, if you trace all the way down, goes seemingly it goes to 0 at around 0.36 or 0.38. And so intuitively you expect something, numerically you see something. It seems like everything is correct. The answer is everything is not correct. The numerics are what the numerics seem to indicate and what the intuition seems to indicate is actually not correct. The current information remains positive for all values of lambda as long as p is positive. And to convince you of this fact, I have plotted in the inset the small values of lambda and computed the current information and put it on a logarithmic scale and then scale that logarithmic scale by a factor of 100 to get things to fit in this plot. And you see that the current information Q1 is log of it is minus 1000. And so current information is exponential minus 1000. So numerics were not going to catch it, or we're going to have a very hard time. The reason, the way to get the right answer is to pay attention to these logarithmic singularities. And you can actually do this analysis for any qubit channel, not just the amplitude damping channel, as long as the channel has no capacity, where the problem is interesting and its dimension, environment dimension is 2, you always get this effect. And the effect comes from analyzing log singularities. While this is a specific example, there are very general cases where this insight can be useful. So for instance, I've given one theorem here, difficult to sort of get into all the details, but the idea is if you have an input with dimension dA, channel output dimension dB, which is larger than the environment dimension dC, then you can essentially make some statement about when this channel sends information. The statement is that if there's a pure state that comes out with rank dC, the channel has positive current information. Corollaries of this are somewhat interesting. One of the corollaries is that as long as the output dimension is large in comparison to the input and the environment, the channel has positive current information. This, I think, is a one-of-a-kind result where you can just look at the dimensions of the channel and show that it has positive current information, hence positive capacity. If you apply this corollary to, say, qubit channels, you solve an open problem, which was that when does a qubit channel send information to its environment? The answer is, well, whenever DC is greater than 2, you can send it. DC equal to 2, you can actually explicitly work out the answer. Okay. Next, of course, there's some non-additivity where I've applied these logarithmic singularities too. And here, the idea is that you can start again with the qubit amplitude damping channel that I presented in the first few slides and say the channel has 0 quantum capacity. For somehow you are able to find that. Then actually you can construct a simple Q-trade channel and use it in parallel with this 0 capacity channel and find that the joint channel has larger current information than the sum of the individual channels. In some sense, you could say that a simple 0 capacity channel boosts error correction rates when used as part of a larger, when used along with the larger Q-trade channel. And so this is a sort of a new type of non-additivity. Well, it was perhaps an unexplored type of non-additivity, which you can find using these logarithmic singularities. Next, I want to give you a small result about a conceptual sort of surprise that comes from non-additivities. And the conceptual surprise is based on the following belief. The belief is that if you leak quantum information to a channel's environment, then this is detrimental for the transmission of quantum, detrimental for quantum and private communication. This belief actually has very strong ground. The strong ground being that quantum information cannot be sent in such a way that it appears in more than one place perfectly. This is the object of no cloning. So if you're leaking information to the environment, you believe that information is perhaps completely lost, and such channels, for that reason, are not good for sending, or such leakage is perhaps not good for sending information. And the belief that private communication, that you try to send information which is hidden from the environment, is hindered by the leakage to the environment, of course, is also somewhat strong, where of course the task is to hide the transmission of information from the environment. Of course, the task is to hide classical information. It doesn't say anything about quantum, but the thing is that quantum information is much stronger in that, in some sense. So if you are sending quantum information to, or leaking quantum information, you're definitely also leaking classical information. And the result actually is that there is a way to take a channel whose quantum and private capacities, which is their ability to communicate quantum and private information, can be computed. So you somehow bypass the non-additivity problems that I have been talking about. And then you put in a leak into the channel, which leaks in such a way that almost all quantum information gets leaked to the channel's environment. Turns out that despite the fact that this leak exists, you can boost the communication more than what you were doing previously by establishing this leak. And these boosts come from non-additivity. So in that sense, this is a somewhat of a conceptual surprise that arises because of non-additivity. And that's covered in the archive reference mentioned below. And so in closing, what I want to tell you is that I have somehow, well, over the course of this talk, even if I've not given you all the details, I've given you an advertisement to somewhat look at the details. And the first detail I give you was this generalization of an erasure channel. This is joint work with Bob Griffiths and is in this archive reference. And that has quite a bit more, but I've only picked out this one particular thing to fit into this talk. Next, I also talk to you about this new theoretical tool, which is logarithmic singularities in the von Neumann entropy. Let me stress that these singularities are fundamental to the von Neumann entropy, and so in that sense, you can apply them wherever you see the von Neumann entropy. I have only applied them to problems of transmission of quantum information, and details about that are given in the archive reference listed here. Then this conceptual surprise that I briefly advertised in the last talk is you can see the details and convince yourself that what I was saying was actually true by having a look at this archive reference. And finally, what I want to end this talk is with the message that this issue of non-additivity, which I've only spoken about in the transmission of quantum information, is a fertile area, a bit somewhat complex, for developing sort of new theoretical and conceptual tools. And finally, I think I should definitely mention here that the non-additivities that I have spoken of were in the transmission of quantum information. These non-additivities or similar non-additivities occur in the transmission of private information and also are believed to occur in the transmission of classical information, where one of the non-additivities, finding whether it is there or not, is an open problem. And with that, I want to thank you for your attention and open the house in that way for post-talk conversation.
Thanks, Vikesh. Now we invite some questions, and Gaurav Saxena wants to ask the first question.
Okay, go ahead.
Gaurav?
Vikesh, can you hear me?
Yes.
Perfect. First of all, thank you for a great talk. This was very informative and a very lovely talk. I have a quick question. So regarding the last part of your talk, which is where you present the surprise, where you say that if we leak information to the environment, then we can boost quantum information. So is there a particular model of leakage that you consider, or are you saying it in a general way that if we generally leak information, then we can always boost this?
No, I am not making a general statement. The leakage is carefully constructed in some sense. And it works in a particular instance. But even so that it works in a particular instance is somewhat surprising. What the leakage does is essentially it appends states to the input that gets sent perfectly to the environment. I don't have the proper equations here. And this, if you open up this reference, 2003-10-367, then I explicitly write down what the channel is and how the leakage works. But if you look at that and you're still sort of, it's unclear what's happening, please feel free to email me. In fact, you should email me, then I will fix it.
Any other question? If not, let's thank the speaker. And also let's thank all the speakers of this session, Professor Winter and Vikesh. So with that, we end the fourth day of the conference. See you all tomorrow. And goodbye and have a good day.
Bye-bye.
Bye. Okay.
Very nice talk. Very nice.